People are like, why is it like this in Austin? And I'm like, I don't know.
Hello. Hello, everyone. Welcome to the Winter Climate Variability and Change Working Group meeting. And we are the co-chairs, Ayla, me, and Sarah. Today, I'm going to chair the morning session. Ayla will chair the afternoon session, and Sarah, she will watch the online part. And first of all, I want to make an announcement. And we are organizing a Dear Meal Symposium at the AMS meeting 2025, which is January 2025. And the symposium will be on Tuesday. We plan to have a whole day symposium, and also plan a dinner at 7 p.m. on Tuesday. And I welcome everybody to submit your abstract. And now, give the CVCWG working group update.
Thanks. So yeah, thank you all for coming in the room and online. So we're going to kick things off with the first half an hour. We're going to just have some updates of the working group activities and the plans for the working group moving forward. And maybe some time for discussion at the end of that, but we're going to have more time for discussion at the end of the day. So if you have thoughts and you don't voice them right now, we have plenty of time for that later on. So first of all, this is the CGD Code of Conduct. Please be respectful to everyone and allow everyone to have their chance to talk and give constructive feedback on all the presentations. So just a few logistical things. We have people online and in person. And so for the people online, hopefully you can hear us. And if you have questions, feel free to either raise your hand or post in the chat. We're going to be monitoring online in the room as well. The meeting is being recorded and live streamed on YouTube. So I sent a message to the speakers. If you don't want your talk recorded, please let us know immediately, because I think it's a little hard to change kind of on the fly. And make sure you don't have any copyright issues in your presentations, because I think YouTube doesn't like that. And if you want to make any last minute changes to your presentations, we have the ones that have been uploaded so far here. So let me know if you do make any changes kind of over the course of the day. We are planning to go down to Under the Sun at the end of the day for a happy hour, and I'm just wondering who is interested in that. This is not a firm commitment, but just we might try and book a table. So we've got 1, 2, 3, 4, 5, 6. Okay, at least enough to warrant booking a table. So I'll try and do that at lunchtime. I feel like there were other things I wanted to mention that weren't on here, but maybe I've mentioned them already. Okay, well, maybe they'll come back to me.
I have a question.
Oh, yeah.
About copyright laws.
Yeah.
Can I include figures from other papers if they're properly cited?
Yeah,
Okay.
I think that's fine. Yeah.
Thanks. Just making sure.
Okay, so some of you maybe are not familiar with the working group and all its activities, so I just want to, before we mention all the new things that have happened, mention a couple of big data sets. These are not new, but these are big data sets that are kind of available for everyone to use. So there's the CSM2 large ensemble. This was not run by the working group, but it was many of the working group members participated in that. And so this was run in collaboration with the group at IBS in Busan in South Korea. And so this is a 100-member ensemble of simulations with CSM2 that are run over the historical period from 1850 to 2014, and then into the SSP 370 scenario period out to 2100. So that's a resource that's available. If you go on the Climate Variability and Change Working Group webpage, the information's there. You can just Google Climate Variability and Change Working Group CSM and it should come up. In addition to that, on the right is a data set that was produced. The paper came out last year. It's kind of complementary to the large ensemble, but it's a single forcing large ensemble. So these are smaller ensembles of 15-ish members each, where you can decompose the influence of all the forcings in the large ensemble into the contributions from anthropogenic aerosols, greenhouse gases, biomass burning aerosols, and then everything else. So you can kind of sum up the contributions. We also have an everything except aerosol ensemble because we find there were pretty big nonlinearities in the response to aerosol forcing, and it matters what method you use. So just in case you were not aware, these two big data sets are there and available for everyone to use. So now we'll move on to kind of the newer stuff, the things that have happened since the last update, which was during the summer meeting. So one thing that I'm pretty excited about, but I haven't really had a chance to look at yet, is this regionally refined North Atlantic AMIP simulation. So this is using the CAM spectral element dynamical core to do regional refinement. I just remembered one of the things I wanted to say at the beginning about the laser pointer. So there is, for the speakers, there is a laser pointer here. And I think if you like hold it down long enough, oh, it's there, okay. Yeah, it works. So, so this is going from 1 degree everywhere except it's regionally refined down to 1/8 degree in the North Atlantic region. And so the motivation here is that there's kind of growing body of evidence that we don't get jet stream variability in the North Atlantic right, and that resolution might matter for ocean-atmosphere coupling. And so this simulation goes from the late 1950s to present day. It's out to 2014 at this point, which is the end of the historical period. So this is using sea surface temperatures taken from a 1/10 degree forced ocean sea ice simulation. So using the ocean and the sea ice models offline, forced with observed meteorology. And what that means is that we can get high resolution SST variability, higher resolution than you really have in the observations over this time period, but it's still kind of following the observed low frequency Atlantic multi-decadal variability. So we're gonna start looking at this hopefully soon and come up with a description paper and try and make this data available. The goal is sometime by the end of this year, but that really depends on how things go. But this should be a pretty useful data set for anyone who wants to look at high resolution features in the North Atlantic over the full historical record. Sticking with the theme of regional refinement, Brian Medeiros has been doing this tropical belt simulation, which is a similar idea. So there's 1 degree resolution and then regionally refined into about, oh, that should not be 1 kilometer, that should be 100 kilometers. Regionally refined to 15 kilometers in the tropics. These are pretty short runs, but they're long enough. I think there's basically 7 years and 2 years of spin up, but 5 years in which to look at things like tropical waves and see how they depend on resolution. And the figure here is showing the precipitation distribution in this run. So the gray is the low res model, the blue is the observations, and then the red is the regionally refined model. And so you can see that as you might expect, you're doing a much better job at capturing the precipitation distribution over West Africa here, particularly in the high intensity precipitation rates. A new ensemble that's been available now since the last meeting is an SSP 585 ensemble. So the large ensemble was using the SSP 370 scenario. We had previously run an SSP 245 medium ensemble of 16 members. And now we have an SSP 585 ensemble of 15 members. So we can span this range of scenarios, and you can look at how the scenario impacts future projections across these ensembles. And again, go to the working group webpage to find out how to access those. We've also run an RF MIP type simulation. So this is basically following the protocols of the PI Klim Hist-All experiment of CMIP6. So this is where you run with prescribed climatological sea surface temperatures from the pre-industrial control, and then you run with only the external forcing. So you can look at the direct impact of the external forcings absent any SST changes. So this is useful for if you want to diagnose a transient effective radiative forcing, or just look at what is the direct impacts of the forcings. And this is run with forcings analogous to the second 50 members of the large ensemble. So if you want to diagnose a radiative forcing in the large ensemble, this is run, there's 3 members that run over the historical period, and we may run, I know UA is interested in this, running single forcing versions of this or scenario versions of this, and so keep that in mind for the discussion if there are ones of those that you're particularly interested in. We'd like to hear about that. Another set of simulations is using this new vertical grid. So CAM is going to go to higher vertical resolution in CSM3. So what you're seeing here is the grid spacing on the x-axis, and then the height of the model in the y-axis. So the black points here are the current CAM grid. The model top is at 40 kilometers. And the resolution here in the troposphere and lower stratosphere is about 1,100 meters. And the new grid is going to go to 80 kilometers and has a resolution here of 500 meters. And what that means is that we can now represent the quasi-biennial oscillation of zonal mean, zonal wind in the equatorial stratosphere. So this is what CAM looks like in equatorial zonal mean, zonal winds. There's no QBO. And this is what this new vertical grid looks like. So we can now explore what is the impact of that on climate variability. And this has a better representation of the polar vortices as well, which I think people have shown matter for things like ENSO teleconnections. So we have a suite of simulations which are using this enhanced vertical resolution. So but everything else is the same. And the next version of CAM is also going to change the resolution in the boundary layer, but we haven't changed that because when you do that, you have to change all of the tuning and the physics. So really everything else is the same except the grid here. And we have pre-industrial control, 3 coupled simulations over the historical period that go to the end of the 21st century under the same forcings as the large ensemble, and 3 AMIP simulations. And if you're really into the QBO, there's also some nudged QBO simulations that were run for the QBO intercomparison project, where the QBO is being nudged towards observations, despite the fact that we now have our own beautiful QBO in these simulations. There's also been some work going on with our collaborators at Cornell. So Flavio Lehner and Yaning Kuo are leading this project. And they've run a suite of TOGA-type simulations. This is where you put time-varying sea surface temperatures in the tropics, and you have climatological sea surface temperatures in the extratropics. And normally we just do this with observed sea surface temperatures, but they've been investigating what could have happened in the past if we had had a different realization of internal variability. So, some of the sea surface temperature evolution we've seen is forced, some of it is internal, and they've been using SST variability from a linear inverse model to look at different potential histories that could have happened. So the one on the top here is the observations. This is a kind of extreme La Nina trend scenario, and then this is more of an El Nino-like scenario. And so they're looking at the connections to the extratropics, and in particular to precipitation over the western US. And so it's been argued in the past that this kind of La Nina-like trend in the observations has been leading to this drying over the western US. And these experiments suggest that, if we'd had a different realization of internal variability, that could have been more severe if we'd had a La Nina type trend. But interestingly, even if you have the kind of extreme El Nino trend due to internal variability, you still end up with this anomalous high pressure over the Northwest Pacific and the drying over the American West. So it's kind of like it's all, no matter what the internal variability would have done, there's kind of a sense that the sea surface temperatures wanted to force drying over the American West. And they're trying to figure out exactly why you get that in this bottom case. It's not totally obvious. But it also shows that if we had had different internal variability, we could have had pretty different overall trends in the hydroclimate of the Western US. If you were at the seminar yesterday that was part of the Earth System Prediction Working Group, you would have heard Clara talking about this. With the working group resources, there's been these large ensembles run of the 2023-2024 El Nino event. So these are some figures from Steve showing the predictions of this year's El Nino with the initialized predictions with CSM, which we're calling SMILE for single to multi-year large ensemble. That's what that stands for. These are the August initializations and these are the November initializations. And what you see is that over the historical period, CSM2 does a really good job at predicting the wintertime ENSO index. And so back in August, Steve noticed that there was this prediction of a very strong El Nino, kind of as strong as the 97-98 El Nino. By the November initialization, that had gone down a bit, but it's still a pretty big El Nino. And this has verified pretty well against observations. And so then what Clara has been doing is been running ensembles with this El Nino event with the sea surface temperatures taken from those initialized predictions after some bias correction. So running kind of 50-member large ensembles of this one event, you can kind of get a sense of what are the uncertainties in the ENSO teleconnections associated with the event. And she's also been running these counterfactual cases under different climate kind of time periods. So on the top there, what you see are the sea surface temperature, precipitation, and sea level pressure anomalies for the 2023-2024 ensemble case. And in the middle is kind of a counterfactual case, which is run under 1979 radiative forcings, and also has the trend from 1979 to now removed. We don't know whether that trend is forced or internal. It's probably a bit of both. So not trying to make any claims about that, but trying to see how has the kind of evolution over the historical record changed how we might experience the anomalies due to an event like the one we're experiencing right now. And the difference between them is on the bottom, and you can see that the differences are pretty large. So changes in the sea surface temperature, mean state, and the radiative forcings have contributed to changing how we experience an El Nino event like the one we're experiencing now. And they're working to try and understand exactly the origins of those changes, at least as simulated by the model. Okay, I'm going to hand over to Aishu to describe the next couple of slides.
All right. Before I start this, I forgot to mention when I do the first announcement, we said we outlined in the Jeremy Symposium. We, that means include me, Yaga from UNCAR, and Xiangbing Xie from Scripps, and Theo Fader from DOE Lab, and Antonita from NOVA. Here I talk about this tropical basin interaction project. This is a clever research focus and talking about the interaction between different tropical ocean basins. And right now the experiment design is basically has been agreed on, and we are carrying out this experiment. For CVCWT working group, we are doing the first part, the historical pacemaker simulation. We're going to run 10 ensemble members from, I think right now we run it from 1880 to 2021 because we don't have a proper restart file for the earlier years. And we have run 10 ensemble members for a Pacific pacemaker simulation. They are ongoing, and I think we are finished. I need to confirm this with Nan. And for other pacemaker simulation, we're right now is setting up. hopefully we will get this done in the next few months. And for the pacemaker handcuffs experiment part, which is done by the Earth System Prediction Group, which was did by Steve Eager and Nan. Those simulations, they have 4 sets starting months. The main February 1st one has been finished, and Steve is working on to write the paper. After that, this data can be released. And before the AOGS meeting in late June, there will be a meeting about TBI. I think it will be 2 or 3 days meeting. So if anybody is interested in the TBI experiment or interested in the trouble-based interaction, you can contact Ingo Richter to join that meeting. Next is the hosting experiment. And firstly, we are doing the North Atlantic hosting model inter-comparison project. They have 6 models participating in this project. And right now in Europe, there's a new project called the tipping point model intercomparison. And this hosting map, right now we are going to be part of this tip map project. This tip map will start from this year, and for the first phase will be 3 years, 24, 25, 26, and they are planning for a second phase too. And for this tip map, mostly they want to do a few things. One is it's a baseline experiment analyzing the historical and projected response of selected tipping elements to different climate and land use change scenario. And also the second one is a commitment experiment to assess the long-term consequences of surpassing different temperature and CO2 levels. And third one is a reversibility experiment to prove the reversibility of impact and product hysteresis behavior. The experiment design is basically we want to run a 1% CO2 experiment, either driven by concentration or driven by emission. Right now, I think that this experiment design is still ongoing and it's not really finalized yet, because right now there's another European project called ESM, TIP ESM, the tipping point Earth System model. That one they propose to run simulation using emission-driven simulation. CSM may participate, right? Okay. Initially, for the tip map, there's 6 tipping elements will be focused on: the tropical rainforest, Greenland ice sheet, Antarctic ice sheet, AMOC, boreal forest, and permafrost. Right now, I'm getting involved in this AMOC, and will co-lead on the experiment design related to the AMOC. And this will start the simulation, I think, in the next few months once we get this experiment design finalized. And this tip map may become part of the CMAP 7.
I just remembered the second thing I wanted to say at the beginning, I forgot. We're using those ceiling mics, and when they're green, people online can hear everything you say, so just be aware of that. People will hear when you ask questions and things using those ceiling mics. Okay. So now I just want to spend a couple of minutes talking about the plans for the next few months. So we have this computing allocation that lasts for 2 years, and we make a proposal for all the things we want to do over the course of that 2 years, and that goes until I think until September of this year. So I'm going to just kind of run through the things that we had proposed that are kind of still on the agenda, but of course the priorities can change. We can make adjustments. So glad to hear any thoughts on what people think about this. So one of the proposed ensembles we planned to do was to run another single forcing aerosol ensemble, but with the CMIC5 aerosol forcings that were used, because we had found pretty different responses to aerosols between CSM1 and CSM2, and you can see that here in the global mean temperature on the left. So, there's no legend here, sorry. So the solid lines are only aerosols, and the dashed lines are everything but aerosols. the green or teal is CSM1 and the maroon is CSM2. And so what you see is that in CSM2, we have a big dependence of the method, of the response on the method that is used. Whereas in CSM1, the difference between the teal lines, we have less of a dependence on the method that was used. On the right here is an example of the difference in the aerosol emissions between the CSM1 and CSM2 simulations. And part of that is because we use a different scenario. We use a high aerosol emission scenario in CSM2, which is the maroon one, and a low in CSM1. But there are also big differences over the historical period in the aerosol emissions. And so there was a project led by Marika Holland and Cecile Hane to run CSM2 with CMIP5 forcings. And so the plan here was to build on that and run an ensemble of only aerosol forcing so that we could look at what is the impact of the different emissions between CSM1 and CSM2. So that's still kind of on the agenda unless anyone objects, or it would also be good to hear if anyone's particularly interested in this type of experiment. Another plan was to run an ensemble of only volcanoes, and this is another thing that was motivated by the single forcing large ensemble. So if you look at the green line and the one on the left, that's the everything else run, which contains solar, volcanoes, ozone, land use, land cover change. And you see that there's a warming anomaly in that everything else run in the early 21st century. And it seemed like a likely candidate for producing that might be the volcanoes, which you see on the right in the red there, that we kind of transition from having this period punctuated by large volcanic eruptions to having this steady volcanic background. And so we were kind of interested in running on volcanoes only to see whether that really was the cause of that warming in the green line on the left. Here are a few of the other things that were planned. One was to run some simulations with new interactive biomass burning emissions, which is a capability that's under development. I don't know if Dave can speak to whether that's likely to be ready or not. I did email some people, but didn't hear back yet. We were going to do some more investigation with the regionally refined North Atlantic setup, but I think we really need to just spend some time looking at the run that we have before we think about what to do with that next. There were some regionally refined North Pacific plans. I don't know if Pedro, if you still have plans in that area, we can talk about that later. And then there's this pencil model, which is kind of in between a slab ocean and a coupled model. This is being developed by Young-Oh Kwan and Gokhan. So this is basically a single column ocean model at every grid point, which allows you to have prognostic mixed layer depths, which is not something you have in a slab ocean. So it's kind of a nice intermediary between the slab ocean and the fully coupled model. And that was in our previous allocation, but there were many technical difficulties in setting it up. And Young-Oh thinks they're almost there and might be ready to run a pre-industrial control with that configuration in the next few months. So that's kind of what we have on the agenda, but definitely happy to hear any thoughts. And so we only have a couple of minutes at this point for discussion, but we have time at the end of the day for more discussion. So those are some of the questions that I had for any of you based on what we're going to do over the next few months. But also it'd be great if over the course of the day you could think about experiments that you would like to see the working group run in the next allocation, because we'll be planning that in the summertime. So we have this meeting, and then the summer meeting is the chance to kind of discuss that more. So I'll end there. We have 2 minutes. If anyone has any things they'd like to bring up at this point, please feel free, or be thinking about what you'd like to bring up in the discussion session at the end.
I can bring it up later. We're still planning to do those simulations. We're still struggling with some design choices.
Okay.
But the other thing I'm thinking of doing, and I've talked to people doing ocean sciences, is, and I'm sure everyone knows that the high resolution CSM has all these unique responses, regional responses, that I think this community, I'm sure, is excited to look into. And perhaps there's some, and all that is doing by people here at NCAR and Ping Chang at Texas A&M, but I think there's perhaps room for this group to think of maybe pacemaker runs. I mean, those are going to be like extremely expensive, but perhaps not every single pacemaker run with a high res, and the computer allocations are gonna be massive, so perhaps there's other mechanisms. TAC has these big allocations that were used to run the fully coupled simulations. Perhaps we can also meet a computer time proposal, or anyone that is interested. I'm happy to coordinate and lead it. It's something I've discussed with Kay McMonigal in Ocean Sciences, and we're thinking of proposing defining a subset of all these experiments that we normally do, perhaps single forcing. There's none of that with that version of the model.
Yeah.
So we need to be strategic because it's so expensive to run.
Yeah, but we should definitely pull apart all of the origins of those different.
Yeah, even the mixed resolution, like these are full increased resolution in both the ocean and the atmosphere, horizontal, and some of the responses come from the ocean, others from the atmosphere, and I think even learning that would be useful.
Yeah, definitely. I mean, I know there are a number of proposals in, and Steve has one, and I think you have.
No, I have one, yeah, but they're more specific. I'm thinking of more community resources beyond what we probably will do in
we should probably at some time get all of the interested people together and think about what would be the right experiment.
That's what I was thinking, yeah. With Kay, we were thinking of proposing a mechanically decoupled, like, ensemble. But everything you do is super expensive. It's like climate modeling 20 years ago. Yeah. I was not here. I can't imagine it.
Just briefly, that biomass burning emissions, we have that. Peter Lawrence is actually running that now. So outside of the climate variability and change, and he's testing an historical for this NSF Growing Convergence project on climate interventions. So you could maybe take it off the list of things you need to do, but hopefully it'll be some simulations that'll be available this year if it goes well.
Yeah. So yeah, I mean, we definitely have allocations set aside. So if there was interest in running more members or, we could.
Okay, yeah, I'll let Peter know that if it's allocation starts becoming an issue, then we'll come back to you. Maybe, I don't know if I'll be here this afternoon for the discussion. In general, just, this is an obvious point, but there's a lot of simulations that are available, right? And so how are you tracking those? And one idea is that we can advertise some of these through the newsletter, but having a webpage, maybe it already exists that I don't already know about.
Yeah, we have the Climate Variability and Change Working Group webpage that has links. Adam maintains it, has all of the simulations. And if you go in there, there's step-by-step instructions of how to get at them. Some of them are not on the Earth System, Climate Data Gateway. So some of them you just need to email Adam to get it. But I guess if there's many people emailing, then maybe we would change that and put them on the.
So let's just take advantage of a newsletter to give a brief overview of that and point people to the webpage, just because some people don't know about it.
Yeah, sounds good. Cool, we're already 2 minutes behind, so let's move on to the talks, and please keep all your thoughts for the discussion at the end of the day. So I'll hand it over to Aishu to chair.
The talk will be given by Ariana.
We'll just give you a 12-minute warning, which is kind of time to wrap up.
Perfect, thank you. Good morning, everyone. I'm really excited to be here. I'm a relatively new postdoc here working with Jen K at CU Boulder, and then Brian Medeiros up here as a NOAA Climate and Global Change postdoc. So I'm excited to share with you some of my very work in progress, ongoing work in exploring mid-latitude precipitation change. I'm interested in this because during my PhD, I was focused on trying to understand what drove this large increase in summertime rainfall in South and South America. So I'm kind of motivated by these broad hydroclimate trends and changes questions. I wanted to start by looking at this IPCC figure to orient everyone. I'm sure many of you have seen this, but this just shows the annual mean precipitation change in percent relative to the 1850 to 1900 mean at different levels of global warming. I apologize to everyone really excited about the tropical Pacific and what's going on there, but I blocked out that region just to compare better with my later work that is just focused on the mid-latitudes. But so we can see the broad strokes increases in rainfall or precipitation over the mid to high latitudes and kind of warming or drying over the subtropics. Oh, there we are. It's really hard. It is really hard, wow.
I think once you get it pointing to there, you can then move it over to the screen. Well, but I've seen that work. I've seen it work.
Okay. And so, yeah, so we have wetting kind of in the mid to high latitudes, drying kind of over the subtropical regions. And these kind of patterns increase or become stronger as you increase to higher levels of global warming. So I'm really interested in what mechanisms drive future precipitation change, and then more specifically, I want to think about what are the relative contributions of dynamics versus thermodynamics to mid-latitude precipitation change specifically. And so in order to do that, there's lots of different ways to think about this, right? I just want to tease apart the dynamic versus thermodynamics to precipitation change, and I want to use this methodology that was set in place by Boney et al. Some 20 years ago now, where they were looking at the dynamics versus thermodynamic contribution to cloud change, and then just a year later, Emery and Brown used the same methodology, but to specifically look at precipitation change. So in order to do this, we consider daily 500 hectopascal vertical velocity, or omega, as a proxy for the strength of dynamic disturbance. This is just one metric that we can use, right? So I'm curious of people's feedback on a different method that we can use. One thing might be like eddy kinetic energy, for instance. But anyway, starting here, what we do is we obtain the probability distribution, or PDF, of omega for a historical period. Here we're considering 1981 to 2000 compared to a future period, 2081 to 2100. And so we get this PDF. So we have the daily vertical velocity on the x-axis, and then the relative frequency on the y-axis. Black is the historical period, and the gray bars is the future period. And then we composite the daily precipitation for each omega bin for both periods. So now we're looking at the vertical velocity again on the x-axis, but now the y-axis is the daily precipitation bin for each of these omega. So you can see the historical period in black, and then the gray dash is the future period, so we're getting more precipitation occurring at these higher vertical velocity values. And so what we do is we, and this is just an example, averaged over 20 to 70 degrees south, but we can find these distributions at each grid point, and then we can consider the dynamic term to be where we take the historical precipitation distribution and multiply it by the difference in the vertical velocity distribution. And then the thermodynamic term is where the circulation doesn't change, but then we're considering these two different precipitation distributions. We do that at each point, and we can get these nice maps, like from Emery and Brown, that show you that you can get the total precipitation, which is the combination of the dynamic term and the thermodynamic term, and the residual or covariability, which they did not show. And so I'll talk a little bit more about these results that they presented later on, but this is the methodology that we're following for now. And so following this methodology, what are we doing different from this Emery and Brown EB 2005 paper? So first of all, they were just considering 6 different models. We're focusing on one model for now, CESM2, of course. And they, in Emery and Brown, just looked at one run from each model, so only 6 runs total. And so we're considering 50 for now. What I'll show today, just the CMUP6 configuration of the CESM2 large ensemble, but soon I'll include all 100 runs. And then they, in the 2005 paper, just considered annual precipitation, and I'll be focusing on all seasons, specifically winter and summer, since that gives us kind of the most extremes of these different mechanisms that drive precipitation. And so by the differences in 1 and 2 kind of afford us the opportunity to better quantify the force response, right, and explore the ensemble spread, which is something I'm really excited about. And then different seasons are driven by different physical mechanisms, of course, right? So in winter, we have more large-scale precipitation versus the more convective precipitation during the summer. Okay, so I'm going to start with the annual mean precipitation and force response, and then compare that to Emery and Brown before I dive into the different seasons. So starting with the annual climatology for 1981 to 2000, we can see we get the nice storm tracks over the oceans. We get the Asian monsoon popping out really well. And then we're just showing the differences, so 2081 to 2100 minus the 1981 to 2000 period. And I'm showing in millimeters per day as well as the percent change. And you can see, similar to what we saw in that IPCC figure, we get this increase in rainfall across the mid to high latitudes, some drying in the subtropics, especially in kind of the southern hemisphere oceans. And then we can look at the contributions from the dynamics versus the thermodynamics. And what we see is that the dynamic term is really contributing to some drying in this region, whereas the thermodynamic term is contributing to a wetting signal, which makes sense when we think about Clausius-Clapeyron and the theory behind all of this. And then this change in precipitation total is the linear combination of the dynamics and the thermodynamics and the covariability, which I'm not showing, but should be quite comparable to this top panel here, which was the actual calculated difference. And so what you can see in this is that the total really reflects more of the thermodynamics, especially throughout the kind of continents and in the northern hemisphere. We have some stronger dynamic signal being reflected in the total terms over like Australia, for instance. And again, this is like some of these results are hot off the press, so I don't want to interpret them too much, but just to kind of highlight the methodology. And then just to compare, so now these are the results from Emery and Brown. So we can see that CESM, the results from CESM2 look quite comparable to these earlier models, where the dynamic term is really contributing to some drying. Thermodynamics is contributing to more of the wetting signal, and then the result is, especially in the northern hemisphere over land, definitely driven a lot by the thermodynamic term. Okay, so now we want to break it down into seasons, so we can start with thinking about the winter precipitation climatology. And so as I do the seasons, the northern hemisphere, this is DJF, and the southern hemisphere is JJA. So we can see the really clear storm track features popping out in the climatology. And then I've just broken it down into the large scale precipitation versus the convective precipitation, just to kind of highlight that when we're thinking about the convective precipitation in the models, of course, that's going to be something that's parameterized, so hard to kind of nail down at this resolution. And then the summer precipitation climatology, of course, looks quite different from the winter precip. We're getting more of the monsoon signal over Asia, a little bit of the North American monsoon, which I did some of my master's research on, and then the kind of poleward effects of the South American monsoon. We see this as well in the large scale, but then of course way more convective precipitation over the continents during the summer. So considering these differences, let's dive into what's driving the winter versus summer precipitation changes for the end of the century. So here's this panel stay the same, winter precipitation climatology, and then the change in precipitation, again in millimeters per day versus the percent. So we can see real increases throughout the northern hemisphere mid-latitudes, real drying over Australia and South America based on the percentages, but then when you look at the raw values, you see these are kind of dry places that are just getting a little bit wetter. And then when we break it down by the dynamics, you can see kind of, again, the dynamic signal overall is a drying trend or pattern. Thermodynamics is very, lots of wetting, and then the combined, we're seeing some of this drying signal through the storm track region kind of coming from the dynamics. Again, it's really messy to me. Australia definitely is being driven by the dynamic signal versus the thermodynamic signal. And then we can go to the summer. So we saw this panel already, and now looking at the changes. These changes are way kind of less homogeneous compared to what we saw in the winter, kind of overall increases in this region, but we have some drying over North America and Europe and Eurasia. There's some clear wetting throughout the storm track region. And then when we look at the differences, there's definitely a strong thermodynamic signal, but lots of kind of drying from the dynamics that are definitely reflected over the northern hemisphere continents. And again, you have this kind of drying signal over Australia, also maybe over South Africa, coming out through in the total precipitation change. So that's kind of just a fast pass and introduction to the work or what I've been working towards. And so now I'm interested in why these patterns look the way they do. So I want to investigate the different thermodynamic and dynamic contributions specifically across ensemble members. Specifically, I mentioned Australia a lot, so the dynamic precipitation change there seems to outweigh the thermodynamic precipitation change. Why is that? And how does that look across different models or members? How do the thermodynamic versus dynamic contributions evolve through time? So all of what I've showed now is just looking at this 1981 to 2000 period compared to the 2081 to 2100 period, but what's kind of the response through time or thinking about these specific global warming levels, like in the IPCC figure that I started with. I've just used this single level 500 hectopascal vertical velocity index for now, but I'm interested in using a vertically integrated moisture budget or maybe thinking about, eddy kinetic energy as a different metric, so different ways to kind of tease apart dynamics and thermodynamics and also thinking about what that means when we're doing that decomposition, like how perfect is it, what dynamics might we be missing, and then maybe a way to get at that is some idealized simulations. One that we've talked about and that I'm most excited about now would be some kind of wind nudging experiments that can really then set the dynamics, then we can see what the thermodynamics kind of look about that. And so with that, thanks for your time and I'll take any questions.
Any questions?
Hi, that was really cool. I was wondering, like, kind of the areas that are drying in your, kind of when you look at just the thermodynamic portion, is that because you're not including, like the, I don't know what to call it, horizontal dynamics in the dynamic portion? And that's kind of where it's coming from?
That's a good question. Yeah, I guess with like Australia, maybe we would just think that that's happening because of an increase in subsidence, but that's a good point of thinking about like what are the other terms and what kind of role would they be?
Right, because you would think about those in a kind of more dynamic framework than the thermodynamic.
Right, exactly. Yeah. So this, and part of doing this, it's helpful for me to like get a bigger picture sense of where the dynamics are most important, with the idea that the greenhouse or like the thermodynamic term is really that forcing term. So it's probably going to be consistent across the models, but can we find or elucidate biases within models by following these kind of dynamic and circulation features? Cool. Thanks.
Okay, let's move on.
Thank you.
Let's move on to the next one.
While he's setting this up, I'm just going to introduce myself. My name's Tim. I'm a fourth-year PhD student at the University of Colorado Boulder Department of Atmospheric and Oceanic Sciences. And as of Friday of last week, I am an ASP graduate student visitor here at NCAR, so some of you are going to see more of me in the next 6 months.
Just click on hide.
Hi.
Great, thank you. So for this project, I focused on trying to understand some of the changes to rare extreme atmospheric river events in different warming scenarios. And I'd also like to give a special thanks to both of my co-authors, Anish and Peter. So to do this experiment, I used two different models. I used Cesm large ensemble. And to get data for the variables that I needed at the temporal resolution that I needed to do this experiment, I had 40 members of CSM in the historical scenario, and I used early 21st century forcing for that. And I also used 50 members from the SSP 370 scenario. So I had 8 years per ensemble member that I used for this. So 320 total seasons for the historical scenario and 400 seasons for the SSP 370 warming scenario. And I used only December, January, and February months because those are the months that are active for extreme ARs. And it had a 1.25 by 0.94 horizontal grid resolution. The other model that I used came from the Weather at Home project, which used computing power from volunteers' computers to run large ensemble simulations of the climate. This particular experiment used the HAD-AM4 uncoupled atmospheric model. I had 3 different warming scenarios. So I had a historical scenario with early 21st century forcing a 1.5 degree increase scenario from pre-industrial levels and a 2 degree increase using the HAPPY framework. I had 1 season per ensemble member, so November, December, January, and February months. I discarded November as spin up, so I only used DJF. And I had over 1,000 seasons for each of these warming scenarios. And there was a little bit of a higher resolution with this model output. It had 0.83 by 0.56 horizontal grid resolution. So I wanted to track ARs in this, both of these models, and I immediately ran into some issues. So there is an atmospheric river tracking methods intercomparison project that sort of organized a lot of commonly used AR tracking methods, but I needed a lot of computational power to do this task because I had so much data. And there were also some other issues. I didn't have the variables that I needed to calculate integrated vapor transport, which is necessary to run the majority of AR tracking methods. And I also only had data that was stored in a regional domain for this Weather at Home output. So I applied a convolutional neural network. I named it CG Climate. It's trained on human hand labels from the ClimateNet dataset. And I found that it's reasonably consistent with ArtMap. It is computationally efficient, and it is highly flexible with data. So that's what I decided to use. I did find that while it is very consistent in tracking the same ARs as other methods, it often has a decent amount of disagreement with the exact grid points that it tracks. And the reasoning for that is shown in this figure here in Inda Diaz 2021 that compares AR area across various different tracking methods. And ClimateNet, which is the hand labels that I used to train this model, had the highest AR area. And that doesn't mean it's wrong, but it's just different than other common methods. And it's also important to note a finding from Shields et al. 2023 that uncertainty across AR detection methods exceeds climate model uncertainty itself. So I had to be very sensitive to the fact that I'm using this one AR tracking method. And I want to also point out that AR area is shown on a log scale on the y-axis. So since I was only using AR extremes, I had a little bit more confidence in using this method. An example of this is shown in this figure from Rutz et al. 2019. There are arguably 2 ARs on this screen, one towards the south and one towards the north. And you can see the more restrictive methods are more commonly going to agree that the more extreme ARs are actually ARs. You can see that almost probably maybe all the methods in the AR to the south detect an AR for that AR, and then for the AR to the north, maybe about half of the methods detected an AR. And then for my severity metric, I only used the maximum landfalling AR IWV. That occurs less than once per year on average in the historical simulations. And there was a similar value for that between the Weather at Home simulations and CSM, between 32 and 33 millimeters. So I calculated the changes to the period, which is on the x-axis, for different severities of ARs here. And so in the dotted lines, you see CSM2 results, and in the solid lines, you see the weather at home simulations. So there's first of all a decent amount of agreement for AR extremes between CSM and weather at home simulations, particularly shown in California. It's working. Sorry, I can't get this. Is it the top button?
Yeah, you have to, I think, hold it for some time at the screen and then maybe try and transfer it over.
Is that not working? Oh, here we go. Yeah, so I'm referring to this dotted blue line and the solid yellow line are both the historical simulations for extremes in California. And we see a decent amount of agreement between them, even despite having a little bit of a different resolution. So this same result did not really come up when I looked at precipitation extremes due to these resolution differences. And then we see for these SSP 370 scenario, certainly many events happening once every 10 years or so that are completely unprecedented and we've never seen before. And then looking at just these weather at home simulations, we see almost an order of magnitude increase in frequency for an AR at any given severity. So a once every 10-year event here happens about once every 2 to 3 years. And this 2-degree increase from pre-industrial levels. Then I also wanted to look at changes to seasonal extremes. So here, I'm not showing the percent difference, but the difference in percentage of years in which we see X amount of events in the same season, X amount of extreme events. So the overall takeaway here is that when we use the warming scenarios, whether it's the SSP 370 or the more mild 1.5 degree or 2 degree increase scenarios, we see far less seasons in both the Pacific Northwest and California where there are 0 extreme events in one season, and far more seasons where there are 2+ extreme events in any given season. Then I was curious to see how these AR extremes would change in different weather regimes. So I used this self-organizing map called MiniSOM to input mean sea level pressure anomaly fields and calculate 5 different weather regimes. And the percentages you can see here are the percentage of the data in each simulation that each regime occurs in. So for example, regime 1 came up 28% of the time in the historical scenario. And the unshaded contours represent the change in mean sea level pressure for each regime. So there really wasn't a whole lot of change, 1, maybe 2 millibars in some regimes. And then the change in percentage of regimes also did not fluctuate too much. One I will note is regime number 2 went from 23.4% of the data to 26.4% of the data. And that is also a very active regime for extreme AR activity. So looking at these extremes during regimes, I plotted change in number of events per season. And I used dotted marks to indicate 95% significance using a student t-test. And then these numbers at the top are the number of extreme events that occurred. And then the percent change is the percent change in the number of events per season. So overall what we see here is that regime 4, for example, which was not a very active regime for AR activity, had the lowest percentage change in extreme ARs. Whereas regime 2, which was the most active regime for AR activity, had the largest percentage change in ARs with 117% change in the number of ARs. So to summarize here, in just a 2-degree temperature increase scenario, extreme ARs at various severities increased in frequency almost 1/4 of magnitude compared to early 21st century forcing. I found that in all warming scenarios, the percentage of seasons with 0 extreme AR events decreases, while the percentage of seasons with 2+ extreme ARs increases. And I found that the extreme AR frequencies increase disproportionately during regimes with low pressure anomalies near the coast. And that's all I have. Thank you for listening, and I'm happy to take any questions.
I'm just wondering if you have a sense of like ensemble spread and whether there's any chance of detecting changes already in that one observational record.
It was kind of difficult to look at ensemble spread with these rare extreme events because they happen so infrequently.
Yeah.
So it was hard to really get a robust metric on that.
Okay, so you think it would be kind of impossible to see a change in observations?
I guess you would need a longer, like more ensembles and longer ensembles
Right.
with like kind of the same consistent forcing. Over here.
Yeah, I guess I'm curious how many ensembles you need, and then I'm also curious about resolution. So I'm wondering what would happen if you looked at this in this quarter degree atmosphere, 10th degree ocean ensemble for CSM1 that we're putting together, and we're going to get up to 10 ensemble numbers there. So very computationally expensive experiments that Pedro was talking about. Would that be sufficient, and whether or not you expect a different signal in a much higher resolution?
So the spatial resolution, I think if we're just looking at IWV extremes, integrated water vapor extremes, I wouldn't necessarily expect to see a completely different result with increasing the resolution, but if you wanted to look at precipitation rate extremes, a quarter degree would certainly give you a much more realistic idea of how those extremes could change. Does that answer your question? Anyone else?
Right. No more questions. Let's move on to next one. Thank you.
Great, thank you.
Next talk will be given by Megan Brent.
Frankie, yeah, thank you. Thank you so much. Hello, everyone. Good morning. Again, my name is Megan Frankie, and I am a PhD student at Colorado State University working in Jim Hurl's group. So just want to take a moment to thank the Climate Variability and Change Working Group for putting this session on for us today and giving me the opportunity to present. So with that, I'll go ahead and dive right on in. I guess I didn't realize that it had moved on without me. So yeah, hopping on in. As we can see, over the last several years, the number of severe weather events has been increasing quite substantially over the United States. We can see here in these green columns, or the green in the columns are specifically severe weather events, and then the other colors represent different types of disastrous weather. So here this figure shows the number of billion-dollar severe weather events per year. So for the year 2023 alone, just last year, there were 19 severe weather events costing more than $1 billion in damage over the United States. So interestingly enough, well, I guess consequently, these events tend to occur in areas over the Midwest of the United States and the Eastern United States, which cause a substantial threat to the population, human life in those areas, and the infrastructure, as well as the agriculturally rich lands. So these costly events are expected to continue to rise as global temperatures continue to increase due to the Clausius-Capron scaling. So because of that, it is paramount that we take the time to understand how thunderstorms and these convective environments are likely to evolve in future warmer climates. Okay, so there has been some prior research that has looked at this, but most of this research has focused mainly on the forced response. Particularly Diffenbaugh et al. 2013 used the CMIP5 ensemble mean to look at changes in convective available potential energy by the end of the century, as well as a 0 to 6 kilometer wind shear, both of which are critical for convection to occur. And that can be seen here in these two figures on the left. Additionally, another study done by Rasmussen et al. In 2017
investigated changes in convective population as well as thermodynamic environments by the end of the century, but they used convection permitting regional climate models instead. Although one thing we can see is even though both of these methodologies were quite different, changes in CAPE, which can be seen here on the left, well, right here in this column as well as here on the left, changes in CAPE by the end of the century are quite comparable between these two studies, with higher CAPE and indicating more explosive energy for these thunderstorms to develop. So as I mentioned, most prior research has focused on changes in the force response using either a small set of ensemble members, analyzing a limited time period, or using a multi-model ensemble mean that has various forcing future scenarios mixed in. Quite less attention has been given to the impact of internal variability, and the attention that it does receive frequently focuses on specific modes of variability. So for instance, this study by Allen et al. In 2015 investigated how the El Niño Southern Oscillation impacts different convective variables over the United States in this boreal spring season. So we can see that during El Niño events in the left column here, winds aloft at 300 hectopascals typically tend to be a lot slower than normal. Winds at the surface, a little bit slower, but not much of a change. And then the values of CAPE during springtime in El Niño events are anonymously lower as well. And then of course the opposite is true during La Niña events, which we can see in the right column. So as I mentioned, very little attention to that internal variability aspect with looking at these studies. And particularly there has been really no attention given to how the full spectrum of internal variability is going to impact these convective environments. Which fortunately, that gives me a great opportunity to utilize the large ensemble approach to really investigate how both of these components of our climate system work together to modulate the convective environment over the United States. So with that, I'll go ahead and dive on into the objectives of this study. We wanted to leverage the CESM2 large ensemble to analyze the historical and projected future evolution of both forced and internal climate variability on convective environments over the United States. In particularly, we wanted to answer these few questions. How do projected changes in climate impact the environmental conditions most critical for convection? And furthermore, to what extent does internal climate variability modulate the forced response of convective environments over the coming decades? So just getting into some of the details of this project here. As I mentioned, we used the CESM2 large ensemble, specifically the first 50 members of this ensemble, the monthly mean data. We used the periods 1870 to 2100, pretty much that full time period that the data set was available at the time. And specifically, we were interested in the months of March, April, May, June, as this season is the most convectively active season in our region of interest, which is highlighted here in this red box in the figure. I do want to note that the ocean regions were masked out for this whole analysis. So in particular, to analyze our convective environments, we looked at these 4 different variables. I'm sure a lot of you are familiar with them, but I'll just give a quick overview in case. I know this is more of like a climate-focused talk. So there's convective available potential energy, or CAPE, which is just the integrated measure of buoyancy in the atmosphere. The convective inhibition, or the SIN, which is just the energy a parcel needs to overcome to be able to freely convect. The 0 to 6 kilometer wind shear, bulk vertical wind shear, so just the difference of the wind speed at the surface in 6 kilometers. And then finally, the product of CAPE and SO6, which is commonly used to distinguish and diagnose between different storm severities. I do want to make a quick note on the convective inhibition. As this parameter is typically defined as a negative value, any time we see a decrease in this means that we are actually obtaining more SIN in the atmosphere and therefore a more stable atmosphere. So before we dive quickly into the results, just wanted to evaluate exactly how well does the CESM2 do at capturing these variables we're interested in. So here we have just the March, April, May, June CAPE SO6 climatology for the full reanalysis record, 1980 to 2019. And as we can see, there is pretty spatially coherent similarities between these two models, ERA5 and CESM2 large ensemble. As well as similarity between their magnitudes. I do want to note that although CESM2 large ensemble looks like it has a lot more of a robust signal, particularly over eastern Texas and the central Great Plains, This was created using the 50-member ensemble mean. So there's 50 members comprised in this calculation, whereas ERA 5 is obviously just one single representation of reality. So here we have our time series of different anomalies for our convective parameters, all relative to the 1971 to 2000 climatology. We can see in the light gray in the background that there is a pretty substantial deviation between interannual and decadal variability in our like I said, the light gray lines, and those all represent the single 50 members. If we turn our attention instead to the solid black line, that represents our ensemble mean. We can see there's very little deviation of our ensemble mean signal throughout the historical record up until just prior to the year 2000, where that signal begins to emerge. And then just kind of taking another look at that same thing, this is just the anomalies of our convective parameters over time plotted spatially. So up in that first row, we can see there are coherent increases in both CAPE and CAPE SO6 in the near term, with decreases in SO6 and SYN. And we can also see that these changes in CAPE SO6 look to be particularly driven by the changes in CAPE rather than SO6, which I think is something to keep in mind. As we move forward time to the middle of the century, which is seen here in our middle row, we can see that these changes just continue to strengthen for all four of our indices. And then finally, by the end of the century, in 2021, we can really see these strong increases in CAPE and CAPE SO6 along our Gulf Coast and the Southern Plains, and then large decreasing swaths of SO6 to the northeastern United States over the whole country, really, and then a main target of decreasing or higher magnitudes of SYN over the central and northern Great Plains. So taking this a little step further, I calculated the linear decadal trends for each of these convective indices for all 50 of the ensemble members. So here in these histograms, it just kind of gives us an idea of exactly how many ensemble members project the different types of trends. So for CAPE, for instance, all 50 members are projecting a positive trend in the next 30 years, whereas for SO6, only about a third of the ensemble members project positive trends. If we move down to SYN, we can see that it's pretty much a 50-50 split between positive and negative trends over the next 30 years. And then finally, with CAPE SO6, sorry about that, nearly 17 of our ensemble members, or nearly 7 of the ensemble members produce a negative trend, whereas the other 43 members are all projecting positive trends over the next 30 years. So, as I mentioned, a goal of this research was to really investigate the role of internal climate variability in modulating the forced response. So to do this, we selected the two most extreme ensemble members of the 50. So we can see here ensemble member 23, which represents the strongest trend over the next 30 years of CAPE SO6, and ensemble member 25, with the smallest trend of CAPE SO6 over the next 30 years. So here, as I mentioned, we have ensemble number 25, that low trend, and number 23 on the left-hand side. If we simply subtract our forced response, or the ensemble mean, from each of these members, then we're left purely with the changes due to internal variability, which we can see on the right-hand side in our column. Specifically, kind of diving into this and looking at how internal variability impacts this, on the top row, we can see over the southeastern United States, that negative trend from internal variability tends to counteract the positive trend due to the ensemble mean, leaving us with overall a negative trends of CAPE SO6 and ensemble member 25 in this simulation. Similarly, if we move down to our maximum linear trend, we can see that the internal variability actually acts to augment the forced response, leaving us with an even higher trend for CAPE SO6 over the next 30 years, particularly over Texas and the Southern Plains. So with that, I'll go ahead and leave you with a few of our conclusions and findings for this study. First of all, the signal of climate change in large-scale convective environments over the United States emerges from internal variability in the late 1990s, just prior to the year 2000. Number two, future convective environments over the eastern United States may be more supportive of less frequent and shorter-lived but more intense storms. And I come to this conclusion because, as I mentioned, we have really strong increases in CAPE, which I said is important for the buoyant energy of the storm, but we also have strong increases or decreases in the magnitude of SYN. So in the future, as we have a more stable atmosphere, but more accumulation of conductive available potential energy, once that energy is finally able to break through the cap, the storms can be potentially a lot more explosive and more intense. And then finally, our third point was that large-scale internal climate variability could significantly enhance or suppress the future anthropogenic-driven changes in climate. And I think that was really, really well demonstrated by the figure that I talked about in the last slide, which I've just kind of posted up right here to kind of keep in your minds as we go through the questions. So with that, I'll just thank you all again for joining us today, and thank you again to the Climate Variability and Change Working Group, and I'll go ahead and take questions.
I'm wondering what the time series of the internal variability part looks like. Is it like a steady linear trend going in that 30 period, or is it almost like a spike during the first or the second bit of that time series that lead to what looks like a trend but maybe doesn't have a strong R-squared value?
Right. So I actually didn't look at that, but that seems like something really interesting that I might dig into. The only time series that I really took the time to look at was that one that I showed you initially that showed all 50 of the ensemble members, the spread of that, as well as then the ensemble mean. But I think that is a really interesting idea, and I might dive into that and see what I can find. Thank you.
I'm wondering, you looked at the mean values. If you were to look at the extremes in like Cape Sin in that kind of product index, how do you think it would change, given that I guess the extreme events are more on like the tails of the distribution of this variable?
Like how do I think it would change in what sense?
Like if we were looking at Cape, but the 90% of Cape, do you think that the results would be consistent? Would there be like greater increases in Cape in the forced response?
I see. So I actually, on one of the figures I should have mentioned, I did use a statistical significance test on it. And it does appear that by the end of the century that those changes are really becoming more significant as time goes on. I don't know if that necessarily answers your question of what you're asking.
Yeah, I'll find a way to phrase it and I'll
Totally, yeah, we can talk later on or during happy hour.
I was wondering why you think you didn't see any changes going up to your baseline. So you're using like 1980 to something?
Yeah, to about 2000.
2000. And so I was wondering if you've thought about why you maybe didn't see any changes it seemed like you didn't see any changes in your variables leading up to that. Is there maybe like an aerosol signal in there or something like that?
Yeah, I think that we are kind of under the impression that at that point in time, that's when the external forcing from greenhouse gases really begins to take over and emerge from the background noise. And so that is kind of our hypothesis at the moment of why it didn't really change any time into the historical period up until that point. So, thank you.
I think it's the same kind of question that others are asking, which is I'm trying to understand, if you're looking at a trend, what's driving what are the mean state or the mean state trends are sort of driving that and asking the question whether or not that's what's controlling whether or not you're getting the increase in severe storms versus the extremes happening more frequently. I again also can't quite ask the question, but I kind of feel like there's something in there that maybe needs to be explored a little bit further to understand, what is it looking like on a season by season basis. You can imagine one season having a lot of severe events and the next one not having it, and it's showing up as a trend, but not really being a trend. And yeah, I'm sorry, I'm not asking. Also, can't quite ask it.
More like, is the distribution changing as well?
Yeah, maybe it's something like that. Yeah.
It's kind of there in your gray line plots. I guess it's where.
Yeah, and I guess I can pull that up and maybe go over that, but it doesn't appear that over time that distribution is really changing, at least the range from internal variability. It appears to stay pretty constant as we go through the last century and this future one here.
It kind of looks like it's getting a bit.
Yeah, for Cape I think it does a little bit, and then but like SO6 and Sin, maybe not quite as much.
Another thing, are you going to project the potential loss? And right now, the loss, like say 1 billion per year, and with this increase of severity of storms, you will see an increase loss due to these storms, right?
Oh, of like
So,
damages
yeah.
and loss. Yeah, I didn't really look into that a lot for this, but I think that can be expected with this. And I think like this framework that we've approached this with, of course, using this model is much too low of a resolution to say anything specific about specific storms and those losses that can occur with them. But overall, like I think that this kind of shows that those losses are expected to continue to increase.
Any other question? Okay, now
Great.
we'll have
Thank you.
our break, and we'll reconvene at 10:45.
So we do have coffee and cakes, we just have to get them from Adam's office.
The first presentation will be given by Yu Cheng. And okay, Yu Cheng, now you can go ahead.
Thank you. So good morning, everyone. My name is my topic today is anomalously darker land surfaces become water due to mesoscale circulation. First, I would like to thank my co-authors, Zoran and Kagan. So land radiative management has been used to reduce regional warming. Land radiative management typically increases the land surface temperature, thus typically increases land surface albedo, thus decreasing the absorption of net radiation reaching the surface, and thus decreasing the land surface temperature. So no-till farming and white roofs are two examples of land radiative management. No-till farming is practiced on approximately about 12% of global cropland area, and white roofs have been adopted in cities like Chicago and New York. White roofs have been shown to reduce land surface temperature from satellite images. And the role of the land radiative management on the local region with a high albedo is widely recognized. However, the impact of land radiative management on the surrounding region with relatively low albedo remains unknown. And here we would like to understand how land radiative management influences the surrounding region with relatively lower albedo. So we propose a hypothesis on the precipitation responses to a high albedo anomaly. So over an idealized land surface with heterogeneous albedo, net radiation is higher over the low albedo patch, and the higher net radiation can lead to higher latent heat flux and higher evaporation over the low albedo patch. The higher evaporation could further lead to more precipitation due to stronger precipitation recycling. And we call this mechanism the local mechanism. In addition, the higher net radiation over the low albedo patch can also lead to higher sensible heat fluxes. The higher sensible heat fluxes can further lead to mesoscale circulations, and the mesoscale circulation can promote precipitation over the low albedo patch, and we call this mechanism as the non-local mechanism. So then an important distinction between the local mechanism and the non-local mechanism is that there are no changes in soil moisture for the local mechanism since there are no net horizontal moisture transport. Here we would like to understand the equilibrium precipitation response to a mesoscale albedo anomaly in isolation. So this question has largely been neglected in previous studies. First, the integration timescales in previous studies are typically on the order of days, thus not reaching equilibrium state. Second, previous studies typically investigate multiple land surface heterogeneity like albedo and roughness simultaneously. Then we conducted a convection, idealized convection permitting models over a heterogeneous land surface with different albedo, and the size of the computational domain is 25 kilometer times 25 kilometer and times 22 kilometer. And then the horizontal resolution is 250 meter, and the simulation period is 500 days. We conduct numerous experiments prescribed with different albedo gradients and different initial soil moisture conditions. In addition, we conduct a control experiment where there are no prescribed albedo gradients. As expected, both sensible and latent heat fluxes are larger over the low albedo patch. And we can also find that as the prescribed albedo gradient increases, both the sensible heat difference and latent heat heat flux difference between the two patches increase. And we also find that the latent heat difference is much larger than the sensible heat flux difference when they are averaged in the long term. Thus, at equilibrium, the latent heat flux dominates. Then this is consistent with the local mechanism, since the latent heat flux difference is much larger than the sensible heat flux difference. And the positive differences in both sensible and latent heat flux can further lead to positive precipitation difference. That is to say, precipitation is larger over the low albedo patch. And as the prescribed albedo gradient increases, the precipitation difference between the two patches also increase. Although the long-term average sensible heat flux difference is much less than the long-term average latent heat flux difference, it can still lead to mesoscale circulations over relatively short time periods. And on the morning of a typical day in our numerical simulations, we can find that the sensible heat flux is larger over the low albedo patch. And this, the higher sensible heat flux over the low albedo patch can further lead to higher near-surface air temperature, and the near surface air temperature difference can further lead to a pressure difference and thus trigger mesoscale circulations. And here we can also find that as the prescribed albedo gradient increases, the soil moisture difference also increases. That is to say, the soil moisture over the low albedo patch is larger compared to that over the high albedo patch. And we can find that this is due to the fact that the mesoscale circulations can transport atmospheric moisture into the lower albedo patch and then increase soil moisture there. Then this is inconsistent with the local mechanism, because we would not expect a soil moisture difference just due to the local mechanism. But then to summarize here, we can find that neither the local mechanism nor the non-local mechanism can fully explain our numerical simulations. So then, instead, we propose a hybrid mechanism. And first, the higher net radiation over the low albedo patch can lead to higher latent heat flux and a higher operation. And the higher operation can further lead to higher precipitation. Second, the higher net radiation over the low albedo patch can further lead to higher sensible heat flux. And the higher sensible heat flux can also can further lead to mesoscale circulation. And the mesoscale circulation can transport atmospheric moisture into the lower albedo patch. So, and increase soil moisture there. The soil moisture accumulates over the lower albedo patch. At equilibrium, the soil moisture difference between the high albedo patch and low albedo patch becomes sufficiently large to significantly weaken the differential heating and mesoscale circulations driven by the prescribed albedo gradients. Therefore, at equilibrium, the latent heat flux difference and the higher and the evaporation difference dominate. However, they are water soiled caused by past mesoscale circulations. Our results have some implications for land radiative management. So land radiative management increases the land surface albedo over the local region. And here we showed that land radiative management can also increase soil moisture over the surrounding region, since they are water soiled caused by past mesoscale circulations. Therefore, the land radiative management can potentially cool the surrounding region, since more net radiation can be partitioned into latent heat flux rather than sensible heat fluxes. Thank you for your attention.
Question? Okay.
Thank you very much. I'm curious about how much you tried with the horizontal resolution or the spacing between bright and dark surface. So what was I guess the typical length scale here was 10 to 20 kilometers, but did you try other?
Yes, we actually tried different. So for example, the size of the domain, we tried the size of the domain to be like 50 kilometer times 50 kilometer, but then it doesn't seem to influence the major finding here especially for the precipitation response due to the prescribed albedo gradient. And then an important note is that the prescribed orbital heterogeneity should be sufficiently large. So typically, it should be like several times of the atmospheric boundary layer height for such kind of metascale circulation to be triggered.
Right. Thank you.
Yeah, so this is all happening on scales smaller than our CSM grid boxes. Do you have any thoughts about what the net effect of not having these subgrid scale mesoscale circulations and heterogeneity would be?
Yeah, thanks. That's a great question. And so I think so those kind of processes are not resolved by coarse resolution CSM. It seems that so there are already some land radiated management like white roof. So it seems that those kind of increasing soil moisture and precipitation over the surrounding region of the land radiated management seem to might have been neglected in current numeric simulations. So it might have some current CSM might have underestimated the precipitation and soil moisture over the surrounding region of such kind of land radiated management.
Yeah, I know they're trying to parameterize this. Are experiments like yours informing that?
You mean for the parameterization of such kind of subgrid scale land surface heterogeneity?
Yeah, exactly.
Yeah, that's a great question. So we have not done such kind of subgrid scale parameterizations considering the land surface heterogeneity, but we noticed that some other groups have done such kind of studies. As of now, we haven't really identified if they really could like observe what our finding here, because there still have been some ongoing processes in the parameterization of subgrid scale land surface processes. So typically when they parameterize such kind of subgrid scale land surface heterogeneity, they compute the surface fluxes using different types of land cover, and then they would use some kind of average method to compute the real fluxes. But I'm not sure if that's really could be correctly captured here. But it's a great question to look into later.
Oh, I have another question. Right now, from your schematic, it seems like you only have 2 patches in this model domain. What if you have multiple patches? Is the result going to change or not?
Yeah, that's also a great question. And here, so this is a highly idealized numeric setup, and then it's periodic in the horizontal direction. So then if you are allowing those kind of heterogeneities to occur infinitely in the horizontal direction, so it seems that this kind of soil moisture and precipitation might still occur. But if you prescribe some other kind of land surface condition, so then we we are not sure. So it would really depend on the exact parameterization of the land surface condition. Thank you.
Right, thanks. Okay, let's move on to the next talk. Next talk will also be online. It's presented by Daniela.
She's here.
Oh, she's here?
Yeah.
Oh, okay.
I appeared.
Okay, this
Our
year.
presentation should be, I sent it. There we go. All right, thanks for having me. Good to be here in person. Today I'll be talking about work I've been doing in the past year and a half or so. I started as a postdoc here with Clara Desser, and now continuing on at UT Austin. So I've been really interested in extreme fire weather events in the past. I've been looking at them for the past 4 or 5 years now. And there's still some remaining questions that I'm trying to answer. So we know that extreme fire weather events, so conditions that are warm, dry, and windy, that can lead to large
Hold on a
wildfires.
second. I'm not sure they're seeing online.
Uh,
At least I'm not.
Pause.
No one online seemed to mention that, so maybe it's just me. I don't know.
Did you stop sharing?
I think, yeah. because,
Oh, we
Yeah,
didn't start
you got
sharing
previous
original
one.
previous
Yeah.
one. Okay. I don't know how to do it. Do you want to do it?
You seeing it now?
Yes.
Awesome, thanks. So you didn't miss any cool graphics yet, so I'll just continue. So we know that extreme fire weather events, so warm, dry, windy conditions, are expected to increase by the end of the 21st century in our future climate simulations. So this is an example of these projections using the CESM1 large ensemble under the RCP 8.5 scenario, and you can see that increases in extreme fire weather events are expected almost everywhere in the western U.S. Almost everywhere in the western U.S. Going into the future up to 2100. And other studies have also shown that the number of years with synchronous fire danger in the western U.S., so multiple regions having fire danger at the same time, is also expected to increase in the future. So not just the frequency, but kind of the concurrence or spatial extent of these events are expected to change or increase. And so one question I had is how does the baseline period that we choose in terms of defining extremes impact extreme fire weather event projections? So in this study, for example, we used 1980 to 2005 as the baseline period, and that's why probably we see so many increases going into the future. But there's been recent discussion among people who study extreme climate events in general to understand what the kind of impact of different baseline periods are. So you can either use a fixed baseline, so kind of looking at two sides of the spectrum, you can either use a fixed baseline, shown in this example here, where you kind of understand changes in your extreme events compared to this period, this historic period. Or you can use a continuously shifting baseline, which kind of allows you to understand extreme climate events if we were to adapt to them as we go along into the future. And this kind of also helps us understand why extreme events might be changing due to changes in the mean versus changes in the variability away from that mean. The second question I wanted to answer is, what is the role of mean changes in the variables that contribute to extreme fire weather events versus their changes in their variability across time? So previous studies, including mine, have kind of isolated the impacts of different variables on extreme fire weather event increases. And so we found that for the Western US, that temperature, increases in temperature and decreases in relative humidity are driving much of these changes in increases in extreme fire weather events. But I wanted to understand whether it was the mean changes on those variables or the changes in the variability of those variables or both. So we have a really nice data set that we can use to understand these questions. I'm using the CESM2 large ensemble. This is a 100-member ensemble, and I use run in the historic and SSB 3.7 scenarios, and I'm using the data from 1980 to 2100. And for each one of these members and each grid point across the Western US, I calculate the Canadian Forest Fire Weather Index, which takes into account, I don't know where my mouse is, takes into account maximum temperature, precipitation, relative humidity, and wind speed on daily scales. And using this index, we can kind of quantify what the weather conditions are in a given day and how that relates to fire weather, so weather that is conducive to wildfires to occur or to spread. And so I now have a fire weather index time series for each member and each grid point in the Western US. So diving into the first question, what is the impact of the baseline period on extreme fire weather event projections? So here I'm showing an example time series of the fire weather index for one simulation for one grid point over California. I don't remember where in California, but I can look it up if you guys are really curious. And here I've zoomed in to kind of like the top part of the y-axis to be able to look at just kind of extreme values of the fire weather index. And so I've defined two different baselines. One is the fixed baseline, which is this orange line, which is the 99th percentile of the historic distribution over 35 years centered on 1980. And this gives us this orange line, which is basically the same going across through time. And I've also defined the moving baseline, which takes the 99th percentile of the 35-year moving distribution across the full ensemble. So it moves every year through time and gives us a different 99th percentile that we use to define our extreme events. So this time series at the bottom kind of shows you the outcome of using these two different baselines. And you can see that using a fixed baseline generally gives you more events, especially going into the future. And we also wanted to identify spatio-temporally connected extreme fire weather events to also try to understand how extreme fire weather events are also expected, how the area and duration of these events are also expected to change. So this is an example of how I've defined events in these simulations. So here I'm showing an event that's centered over California. So I'm only looking at this event when it's over California. And you can see the shading is the fire weather index value on a given day. And the dots here, I don't know if you can see them, but the dots here show one event. So an event that's connected in space and time. And you can see how it starts off like a little baby event at the beginning and then moves going into the next days, it grows, expands, and moves around. And by the end of the 6th day, it kind of leaves California, so that's when I stopped counting it. So that's one example of one event. So I've identified all these events. I've identified over, I would say like 10,000 events, I think, using the CESM2 large ensemble. And they all have an area, duration, and multiple other characteristics you can dive into as well. So, here I'm showing the frequency of events for the historic period, 1980 to 2014. And these are events that are centered over Washington, Oregon, or California. So they have to have at least one grid point in one of these states at a given time. And you can see that most of them are centered over those states, but they're also centered kind of inland, which was interesting to me. And they also tend to spread a little bit eastwards as well. Going into the future, we see that, one, the frequency of these events increase, kind of what we've seen in previous studies already. So just kind of confirming that. So we see a greater number of events, but we also see that these events are starting to become more connected to locations in the Northeast of this region, especially not so much in the Southeast, but mostly in the Northeast. So I thought that was really interesting. When we use our moving threshold, we don't see much changes in the frequency, but we do see hints of maybe some more widespread events and more events maybe connected to these Northeast regions like we did in the fixed baseline. We also see some regional differences in the characteristics of these events. So we see that, for example, Washington has much larger differences in the duration, area, and frequency of events compared to Southern California, which has much smaller increases through time. And that's kind of what we can see from the maps as well. So what is underlying these events? So now the maps on the right are oriented in a different way, where you're going through time from the top to the bottom. And each column represents a different variable that goes into the fire weather index. And what we see is that going into the future, events are much warmer than they used to be using this fixed baseline. So it's really this increases in temperature that are driving these increases in extreme fire weather events over time. And there is some drier events as well, especially in the Pacific Northwest, and that's probably what's driving these larger increases up there as well. What's interesting is that with the moving baseline, even though we don't see much changes in the actual events, like the duration area or frequency of these events, we actually see that they're actually much drier relative to a moving baseline as well. So this might be what's leading to these events in the future years compared to the fixed baseline, which kind of relied just on the changes in temperature. So we wanted to keep going on with this question, and so we are trying to understand better how the changes in the mean of these variables lead to these changes in fire weather events, and how the changes in the variability of these variables might change to extreme fire weather events. So to do that, we recalculated the fire weather index for our ensemble members using 2 new time series. So I'll just quickly go through how we created these new time series. This is an example of an original, what we find in CSM2 large ensemble, for one ensemble, 1 grid point for maximum temperature. We then create a new time series with the changes in the mean removed. So these are, so you can see, can't really see, but you do see that the time series has kind of flattened, and on the right, I'm showing what that change in the mean that are removed actually is. And this is basically an estimate of the 35-year, 30-day, 100-member change in the mean compared to the historic period. So just kind of what the mean looks like compared to the historic period. And then I created a second time series using quantile mapping to kind of constrain the variability and mean of full time series to just the historic variability and mean. So this quantile mapping is borrowed from bias correction, but we can use it to kind of constrain our time series to just the historic period in both mean and distribution. So you can see what the difference looks like here. So you can see that it includes the change in the mean, but also includes change in the variability over time. And then we can kind of estimate by subtracting this teal line from the middle column from the orange line to get the change in variability of these time series. So what did we learn from this giant exercise is that if we look at the changes in the fold distribution, we find that relative humidity and maximum temperature are leading to the largest increases in the frequency of extreme fire weather events. So the column on the left is what I've already shown you in terms of the projected changes, and the columns all to the right is kind of showing the effect of each variable isolated. And then we look at the impact of the changes in the mean, and we find that again, the changes in the mean and the relative humidity are leading to most of these increases in extreme fire weather events. But what's interesting to me is that if we look at just the impact of the changes in the variability, we find that the changes in the variability of relative humidity is also causing much of these increases. So it's not just a change in the mean of relative humidity, but also kind of the day-to-day variability of relative humidity that is leading to much of these increases in extreme fire weather events. On the other hand, the changes in variability of other variables seem to have a much smaller impact compared to their changes in the mean. So I'll stop there and take any questions. Thank you.
So you can have one question.
Thank
Thank you very much. I'm curious about the definition of the fire weather index. Colleagues of mine in Zurich have Jan Kilkai and Fulden Batbenis have recently investigated how different daily values influence your fire weather index. So taking noon values versus daily maximum values and stuff like that. Did you spend thoughts on that, or did you just go for and focus on variability?
I just went, for this study, we just focused on variability. I have done some work with another data set, Cesm2 data set, and tried to, they didn't have a maximum temperature save, they only had temperature save, so I actually calculated it with just temperature. And we did see some differences where we're getting much lower fire weather index values if we only use temperature versus like average temperature versus maximum temperature. It would be, yeah, I think using noontime temperature would be great for all of these, or like using the actual definitions of, so this is a slightly modified version of the fire weather index, but I don't want to try to find noontime temperatures in the Cesm2 large ensemble, but if you have a time series that I could easily use, I'm happy to use it instead. Yeah. But yeah, there's a lot of different ways you can kind of modify this to suit your data set, but it definitely yields can yield some differences for different regions, yeah.
Okay, thank you.
Thank you.
And our next presentation will be given by Samu Miyawaki.
The graphics.
Oh, thank
Especially
you.
the cover page.
Oh yeah, that's like it's I found it online.
Nice.
Gee, I won't get copyright infringement. I put her name up.
Thanks. This is in collaboration with Isla, Brian here at NCAR, and Ching Kong and at Purdue, and Karen at UCLA. So a lot of climate science has focused historically on changes in the mean. Like what we see here, the US temperature in July averaged over all July days, so average temperature. And we have a lot of mechanistic understanding of how mean changes occur through things like feedback analyses. We know how Arctic amplification or land-ocean contrast and warming, all these behaviors about mean changes in climate, I would say is pretty mature. But from a societal point of view, we in a lot of cases, we care more about the extremes than the mean. So for things like heat waves and its impact on human health, wildfires, as we just heard about, and crop failure, all of these tend to be more disproportionately influenced by changes in extremes. So that motivates us to think about how extremes will also change in the future. And then we make, on this plot, show the hottest day change. So in July, just looking at the hottest 5% of day. At first glance, we see something that looks very similar. It's just offset from the mean warming. But maybe this is sort of a good lesson, and maybe we shouldn't just trust our eyes and seeing if there's any difference or not. Because if you take the difference here, up until about 2030, this is all model world, up until 2030, generally the hottest days are changing pretty much in lockstep with the average days. But beyond 2030, we see this pretty systematic rise in how much the hot days warm compared to the mean. And by 2100, we're seeing unprecedented levels of temperature increases in hot days compared to the mean. This is all just averaged throughout the continent, or the entire United States. But if we look at the spatial pattern of what this relative warming of hot versus mean days looks like, it's very messy, especially in the mid-latitudes. So in the US, there's a lot of cancellation going on, where some regions like the Northwest, you actually see hot days warm less than the mean, whereas in the Southeast, you see a very pronounced systematic increase, amplification of warming of hot days compared to the mean. So the mid-latitudes is really messy, but if we look in the tropics, you might kind of see that there's a systematic warming of hot days that's greater than the mean. And so why is this? And one way you can think about it is from the perspective of surface energy balance. And the idea goes that, well, first with surface energy balance, it's radiative heating balanced by sensible and latent cooling of the surface or heating of the atmosphere. And in a future warmer world where you have more water vapor, one of the things that we expect from just simple conceptual understanding is that precipitation comes in larger, more extreme bursts, interspersed by longer periods of dry and drought. So that leads to more runoff and a decrease in soil moisture. And since latent heating, to first order, you can think of it just as feeding off of the gradient in moisture between land and atmosphere. If the soil dries, then the latent heat flux will also decrease. And so if there still has to be a surface energy balance, radiative heating doesn't contribute to a change that much with climate change. So the idea here is that sensible heat flux increases to compensate for this decreasing soil moisture and latent heat flux. And this idea of the repartitioning of surface turbulent fluxes has been shown to explain the spatial pattern of this amplified hot day warming very well. This is work done with CMIP5 data by Suqin Duan. We're seeing this same kind of map of hot day warming relative to mean warming on the left, with the systematic amplification of the hot day warming in the tropics. And those same regions also show up as where on hot days you get a reduction in latent heating that's greater than in mean days. That's all the blue regions on the right panel. And that this decrease in latent heat flux on hot days is balanced by an enhanced sensible heating on those days. This is the center panel now. So this is sort of the understanding that we have for the spatial pattern during summertime. But one thing that hasn't been explored is the seasonal cycle of what this warming looks like, and I think it's important to generalize or think about what the summer amplified warming is in the context of what happens through the rest of the year. So if you look at the seasonal cycle of this behavior of amplified hot day warming in the tropics, so this is averaged from equator to 30 degrees, first looking at the northern hemisphere, the y-axis shows the amplified hot day warming metric that we've been looking at. We see that there's a very clear peak in summertime during JJA. If we now look at the southern hemisphere, we see the same kind of behavior, peak during summer in the southern hemisphere. So there's a robust seasonal cycle to amplified hot day warming. And to first order, you might just think is the same concept of decrease in latent heat flux being balanced by increase in sensible heat flux. Is that operating also for the seasonal cycle of amplified hot day warming? And this plot shows that yes, the answer to that question is yes. If you take the correlation of the seasonal variations in amplified hot day warming and against the change in hot day latent heat flux, we see a very strong negative correlation across the seasonal cycle. So this same mechanism is able to explain the seasonal cycle and amplified hot day warming. So the question becomes, why is there an amplified decrease in latent heat fluxes on hot days just during summertime, or more so than during the rest of the year? And so one way, we mentioned that soil moisture is a key variable in controlling latent heat flux. And if you actually do a more quantitative analysis of what the relationship between latent heat flux and soil moisture is, it's a very nonlinear function. So I said that latent heat flux scales with the gradient in moisture between the land and atmosphere. So all else equal, if you increase the soil moisture as you go to the right of this plot, you would expect a larger latent heat flux because you're increasing the gradient between the moisture in land and atmosphere. And that works. This positive slope to the very left of this plot, it works until a certain point, because after a certain point, your soil moisture is plentiful, but you actually don't have enough energy with the radiative heating, which is the other component that's important. So at some point you plateau and you actually get a negative relationship in really moist days, because in those days the atmosphere becomes saturated. So that's the relationship we have. And the key thing to get at here is that wherever you're to the left of this dashed line, you're going to have a large sensitivity of latent heat flux change to soil moisture changes. Wherever you're to the right, you're not going to have a large change. So we can envision larger changes in latent heat flux happening for hot days if those days are left of this critical soil moisture, this vertical line, but if the mean day is to the right. So if you plot the seasonal cycle of what part of that curve is the day in for the seasonal cycle, this right panel of this plot, I'm showing the deviation of the soil moisture on those days from the critical soil moisture. Wherever you're below this dashed line, you're in the water limited regime, and whenever you're above, you're in the energy limited regime. For hot days, it's always in the water limited regime throughout the year. But for the mean days, in the summertime, this is when you have the shift of the ITCZ towards the hemisphere where the insolation happens. That's the rainy season or the monsoon season in many parts of the tropics. So that moisture gives this push of the mean days up to the energy limited regime. And so you get this amplification in summertime because that's the unique time of the year when on the typical day is moist. And so it's insensitive. Latent heat flux is insensitive to changes in soil moisture, but hot days are sensitive to soil moisture changes. So that explains the seasonal cycle. In the tropics, this whole latent heat flux picture, but in the high latitudes, it's not that simple, and this whole hypothesis doesn't work at all anymore, in fact, because they're positively correlated. It's not a repartitioning at all. So what's going on in the high latitudes? Well, in the literature, the way we think about temperature variations, cold or warm anomalies in the mid and high latitudes where we live are these where the anomalies are coming from. So if you think about cold days, that's usually associated with troughs in the jet stream, where you have cold Arctic air coming in from the north. Warm days are the exact opposite, ridges in the jet stream, where you have warm tropical air coming in from the south. So then you can sort of get a very simple conceptual understanding of what might happen based on just the spatial structure of mean warming. So in the winter time, the maximum warming happens in higher latitudes. It's known as Arctic amplification. So what that means is that if wherever you're equatorward of the point of the maximum warming, you're going to feel a larger warming on cold days where the source of that cold air is coming from compared to any other day. And so in winter, we expect cold days to warm just from this very simple picture of what is a cold day in the extratropics. And in the summertime, you actually get largest warming in the mid-latitudes. And I guess you could call this mid-latitude amplification. And in that case, wherever you're poleward of this maximum warming, you expect warm days to warm more than any other day. So combined, the highest parts of the highest latitudes is this unique place where you expect this very strong seasonal shift in what day of the year you get the largest warming. So if you average all the grid points in land poleward of 50 degrees and look at the warming as a function of the percentile of the day, as a function of temperature percentile, you indeed see that during winter you get the largest warming on cold days, so below the 50th percentile, and during summertime it's the exact opposite. You get the largest warming during the warm days. There's a lot of open, and I'll end with a few open questions. This is still ongoing work, so I'm interested in hearing some ideas if you have any. If you look at the y-axis, there's a huge difference in the amount of warming. The amplification on cold days is much stronger in winter than the amplification of warming on hot days in summer. And this, I don't think this has been explained in the literature, and it's actually not, I don't think it's that simple, because if you look at the actual temperature advection, it looks seasonally symmetric. So that temperature advection seasonal cycle it's not consistent with what we see in terms of surface warming. So this is, I think, an open question there. And all of this has focused on the model world. So we obviously want to connect it back to observations. And if you look at this amplified hot day warming and historical trends, it really doesn't look anything like what climate models project into the future. And of course, this doesn't mean that we can't trust the models. We did say that there's a lot of noise going into this time series if we just go back to the US. So maybe it's just that the signal hasn't emerged yet. So we could explore these questions if you look at like large ensembles and look at the historical trends. Are any of those ensembles consistent with observations? And maybe that gives us some confidence that the models can be trusted. And if the models can be trusted, when do we expect the signal to emerge? So these are all open questions that I'm thinking about, and I'm happy to take any suggestions or questions now.
I have one question.
So Isla recently showed some work that the surface moisture is not following the models. And so I'm wondering, given that you're living in model world and we know that this bias exists, do you expect the hot day amplification to be even more, given that kind of inability of the models to capture like surface moisture decreases?
Right, so it's hard to say. So I kind of looked at the tropics and the highest latitudes, and those arid and dry regions, except for like maybe the Sahara, are generally in the latitudes I didn't focus on. So there's a work by Mike Byrne, where if you look at the tropics only, you expect more warming if if those days are drier, in terms of humidity, which is what Isla looked at. So if you just blindly apply Mike's theory, then I agree with you that models are maybe even underestimating what the amplification might be for hot days. But I don't know if we can extend that to the arid and semi-arid regions. And maybe, I can't remember, Isla, was that bias also like beyond arid and semi-arid regions? Is that bias there?
It was there in the most arid times of the year
Right.
in other locations. So it definitely needs to be dry. So the assumption is that the models just are keeping on evaporating, and reality doesn't seem to do that. So it seems like it could impact that, but
Right.
that we haven't looked at temperature effects. But yeah, I think there are some regions in the tropics like where it was an issue, like Somalia,
Right.
and Morocco maybe is in your area, but you're right that mostly it was in the subtropics.
Thank you. Next time we'll be doing Jonah Shaw. You have a video? Video? No? Let's see if I can do this.
Hi, I'm Jonah. I'm a student at CU, and I'll be talking today about something that I guess Cesm was mentioning a little bit, which is emergence and actually detecting changes. And specifically, I'll be looking at surface temperature trends from a regional perspective and being able to incorporate estimates of observational uncertainty into our ability to kind of detect and attribute these trends. And this is work that I've done with Professor Nathan Lenson at the School of Mines. So, sitting behind this figure, or this title, is this figure from the executive summary of the most recent IPCC report. And so what we're looking at here is that these IPCC regions and years in which we're able to kind of detect a surface temperature change. And what I'd like to point out here is that we tend to see this kind of spatial structure of earlier changes emerging in the tropics, and then in the northern hemisphere and high latitudes, we see a kind of lengthening amount of time for us to do detection. And what this is saying here is year of significant emergence is that our ability to detect and attribute changes is fundamentally a comparison of change in variability. So we know that we see rapid change in these polar regions, but that there's also high variability. So this is kind of can be simply thought about as a signal to noise question. What's really important is that we can detect changes at the global scale, and we've been able to do this for a while. But of course, we live on a small scale, a scale that's even much smaller than these IPCC regions. And so in our ability to kind of have granularity in detecting change, I think is important for communicating science and also thinking about the processes that are driving the changes themselves. And the last point that I'll make is that this figure from the IPCC report does not account for any observational uncertainty. So we assume that the record here, and this is the Berkeley Earth dataset, has no uncertainty associated with it. And so, our uncertainty is going to be spatially and temporally heterogeneous. And so we are going to incorporate that uncertainty into these estimates and see what happens. To briefly talk about this kind of signal to noise question of climate change detection or emergence, the simple kind of sentence that I'll give you is that emergence is when an observed trend exceeds natural variability. And so if we start with a time series of surface temperature, this is just in one of those IPCC regions, and we convert it to an observed trend by starting at 3 years, kind of regressing out a linear fit, taking that trend, going to a 4th year, recalculating our trend, and kind of iterating that forward in time. So now we've moved in the right panel to a trend space. And so what we can see here is that there's kind of a lot of noise, and initially there's a negative surface temperature trend in this time series. But as the length of our record increases, we see a pretty clear positive trend that actually kind of increases in the last 2 decades of the record. But to actually kind of complete the sentence is that we need to take this observed trend and compare it to natural variability. And how we get that here is by using a pre-industrial control run of a climate model simulation. So this is the CSM1 pre-industrial control simulation, and we've kind of created this now cone of internal variability that we're comparing our trend against. And we do this effectively by resampling trends in the pre-industrial control and then explicitly determining confidence intervals. So for example, we have a 10-year trend from our time series from 1960 to 1970, but we can resample all 10-year trends from 1800 years of the pre-industrial control simulation and then just construct our 95% confidence interval from all of those trends. So now we can look and say, when does our trend exceed natural variability? And it turns out that it's right here, we can kind of visually identify it. And so this TOE is our time of emergence. But now what we're kind of adding to this kind of standard format for looking at detection is that our surface temperature trends don't look like that, they look like this. They're uncertain. And so a more robust and strict method of detecting climate change means that we need to construct a confidence interval on our trends as well. And now we can wait until all of those trends are detectable. And this is like actually kind of accounting for what our surface temperature records actually look like. And how we do this, just to kind of explicitly describe it, is that this data is from the GISTemp uncertainty ensemble, which gives us 200 equally likely surface temperature members. And so we calculate the trends for each of those 200 members, and we calculate the time of emergence for all those members, and our strict time of emergence is when 95% of them are distinct from the pre-industrial. And so we can see here, to kind of answer the question or motivate the title of the presentation, is that there's a delay between our mean and our strict. In this case, it's about 4 years. And so you can kind of have your own opinion about how much that matters, but I'd say it's not something we should ignore. And so we are getting delays in our ability to detect these surface temperature trends just from the observational uncertainty. So now we can take this analysis, we've done it here, this was just kind of picking the Tibetan Plateau region for no specific reason, and we can repeat this analysis for all those IPCC regions and see what kind of spatial features we get in our time of emergence and our delay. And so that's exactly what we're looking at here. We have this mean, kind of standard previous definition of time of emergence, our strict time of emergence, and then the difference between the two is our delay. And so I think what I'll point out here is that for much of the globe, our delay is in kind of that 1 to 5 year region that we saw with that example region. But if we look, there's regions that are kind of specifically in the tropics and also in Antarctica where we're seeing delays that are 5 to upwards of 20 years. So the inclusion of this observational uncertainty is really important in specific regions. And additionally, in that IPCC plot, we saw that these regions are actually tend to emerge earlier when we ignore observational uncertainty. And so the expect for accounting observational uncertainty is flattening a bit of that spatial structure that we were seeing in our time of emergence. But kind of going back to the point that granularity is actually really important for understanding climate processes and doing communication, is that these IPCC regions are really big and they're maybe not that relevant to us. And so we can repeat this analysis on the native resolution of our uncertainty product, which is 5 by 5 degrees, and we can look at the results there. And so this is the same data, just repeated at a smaller scale. And so we can see there's a lot more kind of features going on, and there's also a lot more kind of white, which means that we haven't detected a change here. So that kind of first conclusion there is that the smaller scale we go to, it becomes harder to detect changes. And this makes sense, of course, because there's going to be some kind of temporal and spatial time scale of our variability, and the larger our region is, the more noise we're averaging out. We can also see that the delays are greater in this finer resolution. So we're seeing kind of more red and pinks, but they're also still concentrated towards kind of the tropics. And so our effect of accounting for this, or changing our spatial scale, is both to kind of delay things by reducing our ability to average out noise, and also we get an enhanced delay from the observational uncertainty itself, which has its own kind of scales that we're averaging over. And what we're going to do now is basically take this data and aggregate it using histograms to think about what fraction of the Earth's surface is kind of being delayed and when is our detection occurring. So we're looking at here is this histogram. These are those IPCC regions, and these boxes are all 5-year periods where a portion of the Earth could emerge. And on the y-axis, this probability is effectively kind of the fraction of the Earth's surface. So we're taking those IPCC regions and putting them in a histogram, but weighting by the size of those regions as well. And so effectively what we see here is that our mean sense, that kind of ignoring observational uncertainty sense, and our strict sense are offset. So our blue histogram is offset to the right, indicating our delay in our time of emergence. We can also see that these cumulative histograms in the lines is that we're reduced kind of at the end of our observational period in 2020. We detect about 90% of the Earth's surface emerging when we ignore observational uncertainty, and it's reduced by 5% when we account for the observational uncertainty. So just an indicator that this really does affect our ability to attribute these surface temperature changes. When we look at our 5 by 5 degree regions, first of all, we see the histogram looks a little nicer just because those regions are nice little boxes and are not these big kind of clunky regions. But we also see that the histograms are offset to the right because our spatial scale makes it harder to detect the changes. And also that in the cumulative histograms, there's a larger difference between our mean and our strict. And so going to a smaller scale and then accounting for observational uncertainty makes it harder for us to detect these changes. But we want to make sure that these results are robust to our choice of data. And so here we use the GIS-10 uncertainty ensemble and the CSM1 pre-industrial control simulation. But of course, there's all kinds of data sets for this information out there. And so we want to repeat our analysis and see how robust it is to the data set. And so there's actually only one other uncertainty product that we're familiar with, which is the HAG4T uncertainty ensemble. But we also use 4 different estimates of internal variability from different climate models and 1 estimate of internal variability from observations, which is the McKinnon observational ensemble, where we've removed the forced trend and just resampled the internal variability. And so given that we can kind of mix and match our observations and internal variability now 10 ways, we're kind of enhancing our data and looking at the robustness of our results. And so the conclusion here is that these look very similar. So the results are robust to our choice of internal variability and observational product. Finally, what we'll do is we'll take our histograms and we'll extend them to the delays itself. And so now we're looking at where do we experience delays of 0 years, of 1 to 5 years, of 10 to 15 years. And instead of looking at a cumulative histogram, we're looking at 1 minus our cumulative histogram, so we can understand what fraction of the Earth's surface is delayed by more than X many years. So effectively, what this histogram is telling us is that the most common delay is between 0 and 5 years, but there's a pretty long tail here. So there's lots of regions that are delayed in excess of 5 years. And by looking at these kind of 1 minus our cumulative histogram, we can see that in excess of 5 years, almost 40% of the Earth's surface in this kind of 5 by 5 degree resolution is delayed, and over 15 years, more than 10% of the Earth's surface is delayed. And so accounting for the observational uncertainty is affecting, it's not a small fraction of the Earth's surface. It's basically everywhere, and in a significant portion of the Earth is pretty large. So just kind of wrap things up, we are still detecting surface warming. I don't want to provide fodder for climate change deniers, but observational uncertainty is really important because it delays our ability to detect these changes, and those delays have a spatial structure that I could talk about more later. There's a reason that the delays are more in the tropics and less in the extratropics and polar regions. And specifically, I kind of gave these numbers for delays, and that this work is really made possible by these uncertainty ensembles. And so having uncertainty ensemble, maybe for extremes or for precipitation, enables this kind of work. Thanks so much for your time.
Really nice talk, thank you. I'm curious to know, I'm sort of extrapolating your results out with going from the large regions to the 5 by 5. If you were to continue increasing that resolution down to like, I mean, some of these new climate models are running at like 1 kilometer, right? Would you expect your distribution to continue to shift to the right? Or would it asymptote out at some point, do you think?
That's a really good question.
Yeah.
We haven't been able to do that. I think that I don't think it would indefinitely increase, but I would say that at a finer resolution, like we don't have observational records at that kind of resolution. So there's a reason that these uncertainty products are at 5 by 5 degrees, and it's because in some regions there's like the uncertainty product just gives you like a nan or something because it doesn't know the surface temperature. So I'd say it could depend a lot on where observations are for that kind of specific granule that you're interested in.
You mentioned you have 2 products with the spread, but I'm wondering how does that spread compare to the difference between just individual products? Is it similar?
Yes. So you're saying like within the Had-Crew-T ensemble, there's a spread. Within the GIS ensemble, there's a spread. But how does that compare to the?
Yeah, and then other products that might not have a spread, like VEST or.
Yeah. We haven't looked at that question specifically. What we have looked at is the spread between observational ensembles and the spread, or between the observational products and the spread in the models that are used for the internal variability. So this doesn't explicitly answer your question, but maybe it gets at it a little bit, which is that the uncertainty from the ensemble methods is like also concentrated, or like it has a clear spatial structure, whereas the models tend to be a little more like they're actually add spread in the polar regions for the observations don't. But that's not really, I don't know, I'm not really answering your question.
So the one in the middle is like internal variability included in the spread, and the spread is kind of your structural uncertainty.
So this is like uncertainty resulting from which choice of model you use to estimate your internal variability.
Oh, I see.
And this is spread from which observational product you choose.
Okay.
So it's not really answering.
Right. But yeah, it seems like that would be if the spread among observational products is big, that could also be a big contributor to the time, like different separate products, not the spread within one product.
Yeah.
That could be a big contributor to it.
And just looking, I don't have like individual maps for the products, but we've made them and looked at them, and they are pretty, they just have like kind of some interesting features that we haven't fully explained yet. Because these products, the way that they go about creating 200 different realizations is really different. Some of them assume kind of a constant length scale over the entire surface of the planet. Some have more complex handlings of it. And so this means that the way that things average down look really different as well.
Thank you. Now we need to move on to our last talk. We'll begin by Will Chapman.
Oh my gosh, this is gonna be tough.
Yeah,
Okay,
that's really
cool. Great, so thanks y'all. One more talk between you and lunch. I'll try to get through it quick. Today we're going to be talking about, do a little bit of a shift and talk about some model representation and trying to improve some of the representation of some fields within our models. And particularly we're going to be looking at two, we call them data assimilation techniques. One of them is actually a very strict data assimilation technique, and one is just a linear relaxation back to observations known as nudging. And we'll kind of go through these so we're all on the same page. The first thing I want to do is just acknowledge my co-author on this manuscript, so Judith Berner, and give special thanks to some of the folks here, particularly in the DA sections and also in CGD, that helped me out a lot, figuring out what these increments mean or these data assimilation systems mean. This whole project is funded under the M² Lines project, which stands for Multiscale Machine Learning in Coupled Earth System Models, in which we're trying to use machine learning to improve the representation of different fields within our coupled model claimants. For today, we're only going to be focused on the atmosphere component of the model, so it's not coupled yet, but we're moving in that direction. So, and if you want to know more about what you're going to see today, the first part of this talk before we move into what we're doing now is all summarized in this paper that just came out in KJ on this. So I encourage you to look at it if you are confused. And it may confuse you more, so I encourage you to email me if you're further confused. Great. So just a little bit of background. What is data assimilation? So really, data assimilation is the process in which we confront our weather prediction models with observations, and we make some sort of optimal mapping between the observation space and the model space such that we can pull the model towards the observations in some optimal way. And what's been shown is that you can use these data assimilation systems in order to assess the health of a model. So on the figure on the top there, this is a healthy model, or an example of a healthy model, in which you have the gray line, which is our observations, and the data assimilation system is taking the forecasts, which are shown in the little dashed lines, and pushing it randomly in different directions, right? So it's always going either up or down or towards the different observation space. On the bottom, we show an unhealthy model. And the way you can tell is the data assimilation is always trying to pull it in one direction. So you can imagine if this were sea surface temperatures in the tropics that were too cold, and the DA is like, come on, let's warm these things up, always. So this is evident of some systematic model error. And the big idea behind this and how this leads to downstream bias is kind of summarized here. It says, although the amplification of some forcing on some bias process will occur on the timescale of decades, meaning you need to look at a 30-year run in order to assess model bias or longer. The intrinsic timescale of those bias processes are likely happening in the fast physics, or at least some portion of it. So it's time step to time step, and it's an accumulation of these errors that lead to some bias state that then lead to a bias model. And I really like to show this figure. This is by my colleague Will Gregory, in which he is looking at the average increment in a sea ice model, so this is CIS2, and looking at the bias on the left. And that's the sea ice concentration bias, and it's the increment of the data assimilation on the right. You can see it's sort of a perfect one-to-one matching there. So if he was able to improve the increment representation, you would imagine that the bias would be fixed there. And he's shown in a nice paper that you can actually do this in the sea ice system. So the second system we're going to be using is called nudging. So this is just a linear relaxation back to some observed state. In this case, we're using the ERA interim product, and we are taking our model run and we're just constantly applying this relaxation term to try to have it hold the observational trajectory there. So you just add this to the prognostic equations in the model, and it then follows the observed trajectory there. And you collect those tendencies, and you can say these are the increments that we're using on that side. So essentially, in this paper, we have two learning pathways that we're doing. So we're taking some observational state, we're applying some sort of DA product, either nudging or data assimilation. And then what we're doing is we're saying, give us now the mean or the climatology of those nudging increments, and and we are collecting a stochastic component also, which is just represented by individual increments on each day. And we want to say, by taking the climatology of these increments and pushing them back into a model run, can we improve the model state? So essentially, we take 10 years of assimilated data, we then move to a different 30 years, and we say, by applying those increments in those 30 years, can we improve the bias in those systems, right? So the first thing we want to do is say, so does a nudging system and a data assimilation system, do they look like each other? Do the increments sort of result in the same representation across the field? And I would say largely no. In some regions, yes, though. So particularly in the tropics, particularly in the lower latitudes here, you can see across the DA and the nudging systems that they do look very similar. Also in the representation of some of the jet regions up near 200 millibars, there are also areas that project on each other well, but there are also significant differences between the space. However, we went and we applied both of these systems, and what resulted in our 30-year climate runs is shown here, and these are represented by the improvements or deficiencies that reinserting these increments led to in 30-year climate runs within CAM. And this is a lot to look at, but essentially what you want to see is green. If it's green, we are improving the model in some way. If it's red, we are leading to some deficiency here. And essentially what we were able to show is that across all of the systems, at least all of the nudging systems, we were able to improve the model, and in many areas the DA system did also. Where we saw some deficiencies was in the upper level temperature fields, particularly when we were reintroducing the dark increments, or the DA increments rather than the nudging increments. But largely, we're leading to drastically improved models, or drastically improved model representation, at least across all seasons and obviously annually too, when you reintroduce these tendencies. So we're really happy about this. However, we noticed that when we were just doing this deterministically and we didn't have any sort of stochastic physics in there, we were significantly altering the large-scale modes of variability within the atmosphere. So we were damaging particularly the PNA, the NAO, some of these really important metrics here. However, when we introduced stochasticity, we were able to really balance everything out, and we showed actually great improvement in the modes of variability over just single or control model runs. So I want to show you a representation of that here on the NAO. So North Atlantic Oscillation, a very important pattern for downstream weather, particularly in Europe. And what we've done is what's called a stream function tendency decomposition. Essentially, we were trying to look at all the components that lead to the growth or decay of the NAO. And I want you to focus on, in the bottom, we have the observations. So this is what we want the model to sort of look like. And the top is a control run, so it doesn't have the adjustments that we made to the model. In the middle is a stochastic and deterministic run. So we applied the stochastic component of the increments, we applied the stochastic component, or the deterministic component. And I've highlighted just some contours there on the right. And essentially what you can see in the control is you have this real tripole pattern that you shouldn't be seeing for the NAO. And what we showed was that was really a result of this amplification of some of these linear terms within the stream function decomposition, where it should be, the NAO really should be built from these high frequency and low frequency eddy interactions. And what we showed is by reinserting these increments and improving the background state, is we could really amplify the effect of the high frequency eddies and the low frequency eddies and diminish some of these linear terms, which led to much better growth and eventual representation of the North Atlantic Oscillation. So we know we were inserting these tendencies, improving the model, and improving the NAO, and doing it for a physically consistent way, which we were really excited about. So the big takeaways from this is there are advantages and disadvantages from using the DA and nudging system. DA is physically it's more intuitive. We should be able to be mapping directly from observations to the system, but the observations are sparse. So what ends up happening is you see real representations of our observational systems within the increments, and that led to some problems. However, using the nudging, it's sort of filtered through another product, and then you're able to immediately have increments that are represented across the globe. However, one of the disadvantages of the nudging system is that the tendencies will adopt any biases that are in the reanalysis product. And unless we approve the reanalysis product, we're never going to improve those biases, and we could be introducing them back to the model. I think the big advantage there between nudging and DA is nudging is order 100 less expensive. So anytime we improve the model or we change the model, we can run the nudging system, and we know that these increments that we reinsert will be potentially just as beneficial as running a full DA in order to develop this sort of bias correction. At least that is what this study indicates in our current configuration. This may not be true across every modeling system. So some conclusions here is that the nudging, at least the conclusions for the first part, and then I'll just talk quickly about what we're doing next, is the nudging increments and the DA increments pick up on some of the same general features, particularly in the lower level tropics. Overall, we find a positive impact of this online error representation using both the DA and the nudging, and the addition of stochastic tendencies reduce the bias while creating more accurate representations of major modes of variability across the model. So where we're moving now is we want to, rather than have a sort of dumb representation of these tendencies and the adjustments they make, we want a state-dependent version of this. So we want to say, here's what the model currently looks like right now. Is there a smarter way that we can insert the increments? And an easy way to do that, or I wouldn't say easy, one way to do that is to use a machine learning model that then learns the tendencies, and it takes the input state and adjusts the model actively. So we have this system running now within CAM, and the results are too early to show within this talk, I think. We're still assessing how good it's doing. But I can show you that we are representing the increments fairly well. At least the zonal and meridional wind increments, this is an R-squared value, and I'm showing the full atmosphere vertically on the y-axis, and then sort of this mean state across south to north on the x-axis, and this is the R-squared for those tendencies. So we're saying we are able to represent the U and V winds and emulate that system really well. The temperature field we're not so good at, but the good news is even without adjusting the temperature increment, we were able to show significant model improvements before. So if we just focus on the U and V winds, we should still be fine within the system. So like I said, the results are pending. We have this running online in our model now. So we have what's known as a convolutional neural network interacting with the model space. And those runs I'm analyzing those runs now. So crossing my fingers that it's going to be doing well. So in conclusion, this is the conclusions from before, so I won't repeat them much.
Questions?
You mentioned that nudging was very computationally inexpensive. How expensive is adding a CNN to the model?
It's a great question. Currently, without GPUs, it represents like a 4 times speed slowdown of the model. We just wrote a GPU definition, or machine definition, so we're on the GPUs now, and now it's like 1.5 times slower, so it is expensive. But this is someone who is not a software engineer implementing this into the model, so I imagine we can speed this process up. I'll just need to consult with a bunch of people in order to do that. So undoubtedly it will be more expensive, but how you split that, I think we can lower those costs.
So you mentioned that when you just impose the bias correction tendency without the stochastic addition, the modes of variability degraded.
Mm-hmm.
Because I haven't seen that happen when I've done that in the past. And why would that be? Or are you doing it's a smoothly varying seasonal cycle of tendencies you're just imposing?
It's a smoothly, so it has a diurnal cycle and a seasonal cycle. And what I saw, particularly, so the NAO was bad, but it wasn't that bad. It's almost equal. It was really in the PNA what we saw. And when I did the tendency decomposition, it was really this barotropic eddy, like this barotropic feedback. And it's essentially we saw like this strong enhancement of the gradient of the jet. So there was like a big like positive minus. We were introducing a stronger gradient there, which would feed back into the growth of that elution low pattern. So we saw like this massive deepening of the elution low.
But that stronger gradient was an improvement in the mean state?
It was an improvement in the mean state, but it degraded it essentially made the amplitude of the PNA like way too deep. Yeah.
And this was just one member, or?
This was I did it, you saw it in every member. So I ran it 4 or 5 times. It was technically the same thing over again, but you know.
So like 4 or 5 historical runs, and
Of
you
30
saw
years, I saw
a
it
degradation
consistently.
at all?
Yeah. And then we were also doing this, we were making sure that these were actual significant changes as much as you can in a 30-year run by taking the lens and seeing if by taking 30-year chunks, we saw what was outside of that range. I think it was actually your suggestion.
Okay.
Yeah,
so I make the same suggestion.
Yeah. So, we saw that it was a significant difference, at least using that framework.
I have multiple questions, but I guess I'll ask one. I was wondering, how do you make sure you're so this is all new to me, but I'm wondering how you figure out if you're overfitting, I guess, is like the only word I can think of. Like if data assimilation is kind of preventing maybe if these methods would maybe be an issue when looking at future climate change, and how you think about that.
Yeah, big open question about the future if we're going to go out of distribution. And also very hard to answer whether we'll know if we're going out of distribution. The hope is that you can use these tendencies to point to actual physics schemes and say, this is what we think is actually inherent in there. You can do that with some equation discovery techniques, but they're sort of a summation of a lot of errors, so it's hard to pull out those pieces. But we have been able to identify a couple things that we think are leading to problems. So if I can fix the actual parameterizations, then I feel good about it. Blindly putting it into the future, we're gonna have to figure out exactly what makes us feel comfortable. And I think you can do that with perfect model runs, right? So start to use one member that we know is inerrant, try to correct to a different member that is in the future. And we can say if we represent this climate, say, well, even though we're going out of distribution, then maybe we can take our current climate and still apply these methods, and then so.
Steve, have a question?
I could ask a question. You've asked. Yeah, I'm curious about the state-dependent bias correction. I'm wondering if the NN is picking up really modes of variability patterns, or what does that mean?
So it's hard for it to pick up modes of variability dominantly because it's looking at just like a 30-minute increment. So it's going to be like it'll see an extended jet and I get a geopotential, but that geopotential isn't going to look like PNA, or it'll be some representation of it. It'll have a low, right, or a high across the North Pacific. But what I feed it is representations of the prognostic variables, so UV, TQ, surface pressure, temperature, surface wind stress, bottom temperature, a bunch of variables. So it will have some representation of the current state. Whether it can kind of extrapolate and say I'm in this regime, we hope it will, but I haven't done any direct testing. So the plan is to really say, we're now in a super active MJO. What do the increments out of the CNN look like? Or we're in a super active PNA. What do those increments look like? And then we'll be able to answer those questions. We haven't done that work yet.
Steve?
I don't know if I fully understood, and I'll talk to you after, but it seemed like you're nudging to ERA interim with the stochastic tendency is yielding positive results. Is there potential then to generate a CAM reanalysis based on ERA interim that just, basically they've done the hard DA work. Now we can, use what they've done to generate potentially an ensemble of atmospheric realizations on in our CAM model.
Yeah, I think there's potential there, and folks are looking at this kind of cheaper data assimilation with emulated neural networks. I don't want to speak out of place though, and I wouldn't say I'm the expert in that realm. So I think it's a really good idea, and I know that people are approaching it, but technically feasible, yes, but will it be better than our other products? Who knows?
Right, thank you. And let's thank all the speakers one more time. Now we'll be late, so we will start without 10 minutes late.
No, let's just start, I mean, 50 minutes is long enough, I think, for lunch, so we don't get behind.
All right.
Yeah.
Let's reconvene at 1 o'clock. Yeah.
Oh, wow. So what is it? There's nothing on the
Everyone,
calendar.
thanks for sticking around. We're streaming live again, so just a reminder that everyone can hear online. Okay, so now we have a series of talks on ocean atmosphere coupling aspects of variability. And we're going to start with iShoot on the role of the AMOC in determining the surface climate response in two coupled models.
Thank you. And this work is funded by DOE and it's in collaboration with Jeremiah, Hui, Nan, and Gary, Julie from NCAR, and Luke and Kamala from Los Alamos. The AMA, or the Atlantic Meridian overturning circulation, is the global scale ocean circulation. It transports upward, warmer, and saltier water into subpolar North Atlantic, where it loses heat to overlay atmosphere, becomes dense and sinks to depth, and flows southward and outwells elsewhere of the world ocean. This circulation is important because it transports significant amount of heat into the subpolar North Atlantic. Look at this blue line, that's the Atlantic Meridian heat transport. It is northward at all latitudes, but in the Pacific, it's northward in the North Pacific and southward in the South Pacific. Now, the other thing we're talking about is separation of the internal variability and then from the external forces. In earlier years, when we started the global warming research, at that time the warming is not that significant, so we normally use the linear detrending. But after we found out the linear detrending may not exactly represent the force response, so we proposed to remove the global mean surface temperature. But afterwards, for the global mean surface temperature, actually the internal variability can also contribute to the global mean temperature. That's why some other people propose this remove the quadratic fate of the global mean temperature as the force response. But later on, when we have the similar model, people propose is to remove the ensemble mean of global mean temperature to represent the internal force response. And another one proposed is to remove the local ensemble mean to represent the force response at the local scale. Of course, more recently, the proposed new way to remove the force response is to remove the global warming pattern instead of just a number. Actually, in some sense, it's similar to this remove the local ensemble mean. But the question here we want to ask is, if we remove the local ensemble mean, whether the ensemble mean at the local scale is representing the force response or not. Here we're going to use two models. One is Cesm, the other one is E3SM, which is the Department of Energy's climate model. These two models say that the climate sensitivity for Cesm2 is 5.2 degrees, and for E3SM V2 is 4 degrees C. In this study, we analyzed the historical all-forcing experiment for CSM large ensemble, that's 100 ensemble members. E3SM is 20 ensemble members. And then we also analyzed this single forcing experiment, anthropogenic aerosol only, greenhouse gas only, and everything else, excluding greenhouse gas and anthropogenic aerosol. For CSM, this ensemble member for these three sets of experiment is 20 and 15 ensemble members, and for E3SM is 10 and 4 ensemble members. Okay, first let's look at the global mean temperature evolution. It's the black line is the ensemble mean of observations. We have these 4 observations here, and the blue and red line is ensemble mean of E3SM and CSM. From here, I can clearly see that for CSM, the time evolution of ensemble mean is similar to the observations. But E3SM, there's a significant difference, especially in this time period after 1920. Now, we do a ERF analysis of the ensemble mean, local mean. This is for CSM, this is for E3SM. we identify these two patterns as similar because when you look at this time evolution of this PC time series, we can see that this time evolution is similar to each other. And because this is 100 and some member, this is 20, so this line is more smoother. The other thing we notice is this one we think is represent the false response from greenhouse gas pulsing and also the volcanic aerosol. We can hear here the volcano, this is another volcano. The same for ECSM. And if we look at spectral pattern, CSM, the warming seems like more uniform, but still the warming is less in the northern hemisphere, in latitude. It's similarly as the ECSM. This is the warming is significantly less. And also we can see that the percentage of the variance explained is also much smaller for ECSM than CSM. Next, we look at this UF for CSM, the UF2, for ECSM is UF1. We identify this pattern as similar also because the time evolution of the PC time series is similar. This one basically represents the response of the climate system to the anthropogenic aerosol pulsing, at least this aerosol pulsing. We can see the northern hemisphere, there's a significant kind of cooling, and the cooling effect in ECSM is much larger, but the spectral pattern actually is quite similar between these two models. And this is the third UF. And the pattern response basically for both CSM and ECSM is kind of an IPO-like pattern in the Pacific, and they are quite similar. And also in terms of time evolution, this is also very similar. That means this represents the same pulsing in this UF3. Next, let's look at the single pulsing experiment in comparison with the all pulsing experiment. And here the dashed line is for ECSM and the solid line is for CSM. First of all, we can notice at for pre-industrial control simulation, there's about 0.6 degree difference between CSM and ECSM in the mean state. And in terms of time evolution, if you look at the greenhouse gas pulsing red line and the red dashed line, we can see it starts at a 0.6 temperature difference. By the end of 2014, the temperature difference becomes 0.2. That means the warming due to greenhouse gas actually is higher in ECSM than CSM. On the other hand, if we look at the aerosol pulsing, this orange line and this, we can see it starts also a 0.6 degree difference, but by the end of 2014, the temperature difference becomes 1 degree. That means corresponding to the aerosol pulsing, the cooling effect in ECSM is larger than CSM. This is the lead EUF for the single pulsing experiment and sample average. You can see this aerosol pulsing, greenhouse gas, aerosol, and everything else. From the spectral pattern, we can see it's warming almost everywhere, and land warming is more than ocean. It's pretty much similar, and in the equatorial region, we can see this kind of anneal-like response. They're also very similar. The biggest difference we found out is in the South Polar and North Atlantic region. Here, for CSM, we have significant cooling or negative response, but for ECSM, that is much weaker. Correspondingly, if we look at the aerosol pulsing, we can also see the spatial pattern is also similar. In general, it's a kind of global, almost everywhere is kind of a cooling effect, but the difference still appears in the South Polar North Atlantic. And this is related to change of the AMOC, at least we propose here. Okay, when the greenhouse gas increase, the AMOC weakens in CSM, it will reduce the meridian heat transport or the meridian heat convergence in the ocean, so it causes this kind of cooling effect. On the other hand, with the aerosol pulsing, it will generate the cooling effect. The cooling will cause the surface water become denser, and it enhances the deep convection. Therefore, it will strengthen the AMOC. That's why we have this warming effect. And for the everything else, this pattern actually, especially for E3SM, this pattern pretty much similar as what we see before the UF3. In ECSM, it's also similar, but not that significant. So that means for UF3, for the ensemble mean, it basically represents the false response to the forcing except ultraviolet aerosol and greenhouse gas. Now we have mentioned this effect of AMOC, and next we are going to look at what is the AMOC change in these two models. This is CESM, this is ECSM. First of all, we can notice the mean strength of the AMOC is about 23 story for CESM, is only a couple of story for ECSM. And if you look at time evolution of different scenarios, the different single forcing, different aerosol forcing, all forcing, is everything else, and greenhouse gas, the trend of time evolution is similar, but because the AMOC change is so small, correspondingly, it will affect the meridian heat transfer. Here, I showed is the meridian heat convergence between 40 and 65 degrees north in subpolar North Atlantic. We can see that for the CSM, with the aerosol forcing, we have significantly strengthened meridian heat convergence. That means it will causing a warming in subpolar North Atlantic. At the same time, it will affect other regions. Therefore, it will reduce the response of the climate system to the aerosol forcing. That means the cooling effect will be smaller in CESM than ECSM. Correspondingly, you can see for ECSM, although the aerosol forcing also increases meridian heat convergence, but this change it cannot be seen. We can compare with the Boolean. It's statistically they are different. That means that although there's change, but this change may not be big enough to reduce the response of climate system to the aerosol forcing due to an enhanced meridian overturning circulation. Therefore, we propose that for ECSM, the stronger response to the aerosol forcing may be because the AMOC in this model is too weak. To further demonstrate this, we are currently running simulations by artificially strengthen the AMOC in ECSM and see whether we can reproduce better of the 20th century simulation and to see a better response of the AMOC to the change of the aerosol forcing. Here is our summary. Is the simulated surface climate is much cooler during the 1920 to 2014 in ECSM V2 than observation, but in CESM2 the time evolution is similar as the observation. The UF analysis show that anthropogenic aerosol seems to play an important role in determining the surface climate response, and the weaker mean AMOC state in ECSM may be responsible to the cooler 20th century climate in ECSM. Thank you.
All right, apologies online who didn't catch the beginning of the talk. Is there any questions? If you're online, please raise your hands or post in the chat. I'm looking at that. Anyone in the room? Oh, yeah.
Oh, nice talk. I wonder where you show the UF pattern of the greenhouse gas and aerosol comparing between the CSM2 and the ESM3. So I wonder, like for the Pacific tropical region in the eastern part, where the CSM2 shows a larger temperature response both in the greenhouse gas and aerosol single forcing simulation relative to the ESM3, while much of the change or the other response to other forcings in the ESM3 is much larger than CSM2, and they think that it's because of the ESM3 have a weaker response to anthropogenic forcing. I wonder, is it possible it's the other way around, that CSM2 tend to have a higher sensitivity? I wonder if, what's your thoughts on that?
That's a good question. And for ECSM, Actually, for E3SM V1, it has a similar equilibrium climate sensitivity as CSM2, and both about 5.2 degrees C. But for the E3SM V2, the equilibrium climate sensitivity reduces a bit. And my explanation for the difference here is with a weaker AMOC, that surface climate response, the transient climate response, can be larger, although the equilibrium climate sensitivity is smaller. The reason for that is because the AMOC is weaker, so the surface stratification in the subpolar northern especially and also elsewhere is much stronger. With stronger stratification, the surface warming may be faster than you have when you have a deeper mixture or weaker vertical stratification.
Thank you.
I'm curious how you're going to fix the AMOC problem in E3SM and if you really intend to rerun all of the ensembles.
Right now, we are planning to run 1 or 2 27 simulation with negative very water flood into the southern northern. In this way, we can artificially strengthen the AMOC without changing the heat balance much. And right now, 9 is running this simulation, and I haven't get the result yet. Hopefully, it can fix at least part of the problem.
All right, thank you. So our next speaker is Shuang, talking about the direct and indirect effects of aerosol forcing. Where's the other deck that's on with all the presentations? Are you controlling? Oh, it's not here. Okay, all right. I'll have to look at it there. There we go. You have to hold it for a bit.
Oh, hello everyone. Good afternoon. My name is Shuang, and I'm a postdoc from University of Texas at Austin, and I'm based in Boulder. And I would like to thank my advisors Clara, Gita, and Adam. So today I'm going to present the work about the atmospheric response to time-evolving anthropogenic aerosol emissions from the 2030 to the 2030. So we shifted the topic a little bit, focus on the pattern effect of the anthropogenic emission following the host talk. So where the map on the left are the trend of the AOD taken from the CSM all forcing large ensemble minus the all but one forcing the XAR and XBNB. You can see that the AOD trend has distinct spatial pattern over the different periods in the 20th century. So we are interested in how does the time evolving anthropogenic emissions would impact the spatial pattern of the climate response. So we try to address these questions, we focus on the two questions. So first, what are the dominant radial forcing patterns of the time evolving anthropogenic emissions? And we consider both the industrial aerosols and the biomass burning, while most of the previous study focused on the industrial aerosol only. And secondly, this work focused on the atmosphere response. And we also try to assess what are the relative contributions of the radial forcing versus the indirect SST forcings. And we use 3 sets of Chem 5 1 degree AMIP ensembles. Where the first group is driven by the time evolving Cesm 5 industrial aerosol and biomass burning emissions. So with the ST fixed at climatology, and which is called the red only AMIP. And the second group is driven by the SST response to the same Cesm 5 emissions with the emission fix. So which is taken from the ensemble mean of the CSM all forcing a large ensemble minus the sum of XAR and the XPNB. And the third and the samples is driven by the combined forcing. So both the same CM5 emissions as well as the SST response. So we think that the response taken from the third group as the total response to the same CM5 emission. And we use the EOF analysis to estimate the dominant forcing patterns of the time evolving anthropogenic emissions. And this talk, I will focus on the JJA seasons. And we use the 10-year rounding mean data. And the PC1 time series of the anthropogenic optical depths shows a monotonic increase of AOD over the time and explain about 63% of the variance. And the corresponding AOD regression patterns shows the robust AOD increase mainly over the low latitude regions. And where the PC1 stays nearly constant since the 1990s, and this is associated with the biomass burning in the tropical regions, which shows minimal change during that period of time, and this indicates the biomass burning contribution in our low latitude mode. And where the second PC time series peaks in the late 1970s and followed by a reduction and explain about 30% of the variance, while the corresponding AOD map shows the robust AOD change mainly in the northern hemisphere mid-latitude and accompanied by weak AOD reduction in the East and South Asia regions. So the second mode describes the pattern of the industrial aerosol emissions in the eastern US and in Europe. So we have found the two dominant modes of the radiative forcing in the time involving anthropogenic emissions, and the two modes explain about 94% of the variance. And additionally, we do find similar dominant radiative forcing pattern from the single forcing large samples, driven by the industrial aerosol and the biomass burning individually. And where the map on the left, on the right shows the regression of the SST response, where in the low latitude mode, the AOD change drives the cooling in the ocean surface water, with the North Pacific cools the most. While the Southern Ocean surface water shows weak changes, and in the Northern Hemisphere mid-latitude mode, the AOD change drives the cooling in the North Atlantic and a warming in the North Pacific. The warming in the North Pacific is associated with the weak AOD reduction in the South and East Asia, while the Southern Ocean surface water warms more. And so the pattern of the AOD regression and the SST response regression represents the dominant pattern of the radiative forcing and the indirect SST forcing respectively. And then I will focus on how the atmosphere responds to those dominant forcing patterns. And I will first talk about the low AOD mode. Low latitude AOD mode. So this shows the precipitation regressions. So the full response is given on the left, and the radiative force response is given in the middle, and the indirect SST-driven response is given on the right. So all the response will follow the same order in the remaining talk. So while the pattern of the total precipitation response is mainly dominated by the indirect SST, given their spatial pattern correlation of 0.3. In contrast, the radiative forcing-driven response, the spatial pattern of between the radiative force response and the full response is about 0.3. And in the full precipitation change, a southward shift of the ITCZ is shown. This is associated with the enhanced meridional temperature, hemispheric meridional temperature. And now if we focus on the low latitude region, now the indirect SST-driven response is largely offset by the radiative forcing-driven response. The radiative forcing induced a large precipitation reduction in the low latitude land regions. Well, now if we move on to the East US and the Europe region, so the total precipitation response in these regions is weaker due to the weaker change in the AOD as well as in the sea surface temperature. But I find interesting is that So where much of the precipitation change in the northern part of the North Atlantic is actually attributed to the radiative forcing. Though the radiative forcing only induced a weak change in the eastern US and the Europe. And where we have the bottom panel shows the sea level pressure regressions. So much of the pattern of the total sea level pressure response is again dominated by the indirect SST forcing, giving their spatial pattern correlation of 0.74. While the radiative forcing counteracts the indirect SST-driven forcings, and the pattern of the atmospheric radiative forcing-driven response and the indirect SST-driven response is similar, given their spatial pattern correlation of 0.6. Now, if we focus on the low latitude region in the North Pacific, the radiative forcings only induce a weak SLP response over the East and South Asian, the emission regions, while the much of the change in the North Pacific, so the weakening of the altitude low, is dominated by the indirect SST forcings. So these might suggest that the precipitation change in the East and South Asia land regions, the radiative forcing is perturbed through more a thermodynamic related process, while the indirect SST forcing perturb the precipitation in the adjacent region through a dynamic related process, but further investigation is needed. So in short summaries, so where the pattern of the full response is dominated by the indirect SST, and the radiative forcings modulates the indirect SST forcing-driven response, especially over this low latitude emission region, which can induce a strong local precipitation response. And now we move on to our northern hemisphere mid-latitude mode. And we also find that so the pattern of the total precipitation response is again dominated by the indirect SST forcings, giving their spatial pattern correlation of 0.7. And if you look back to the full precipitation response, and a southward shift of ITCs is also observed. Now, if we focus on the eastern US and the Europe region, so much of the precipitation change here is actually driven by the indirect SST. So even though the AOD change in these two regions is robust, so the radiative forcing only drive insignificant and weak precipitation response in these regions. And now if we move on to the low latitude region, that the radial forcing now plays a more important role, that the much of the precipitation increase in the low latitude land region is dominated by the radiative forcings. But if you look at the total sea level pressure response, again, the pattern is mainly due to the indirect SST forcings. And while the radiative forcing-driven response compensates the indirect SST forcing in the northern hemisphere and counteracts it in the southern hemisphere. And now if we look into these the Eastern Asian and EU regions, so much of the sea level pressure change in these regions is due to the indirect SST forcing, and this might suggest that so the precipitation change in these regions is associated with the change in large-scale circulation driven by the indirect SST forcings. And lastly, if we look at the Asian and the North Pacific regions, we found that the the strengthening of the Aleutian low is attributed to both the radiative forcing as well as the indirect forcing, even though it is dominated by the indirect SST forcing. However, in the low latitude mode, the much of the change of the sea level pressure in the North Pacific is mainly driven by the indirect SST forcing, which is counteracted by the radial forcing driven response. And a short summary. So we have found the two dominant pattern of the time-involving anthropogenic emissions And we have the first mode describe the pattern of the industrial aerosol and biomass burning in the low latitude regions, while the second mode describe the pattern of the industrial aerosol emissions in the northern hemisphere mid-latitude. And the pattern of the atmospheric response to these dominant forcing patterns is dominated by this indirect SST forcings, while the radiative forcings modulates the indirect SST-driven response on a regional scale, particularly over the low-latitude land regions. Well, the mechanism of those response needs further investigations. And recall what the Ayla mentioned, the CSM2 simulation driven by the same semi-fine emission. It would be interesting to compare that emission with the model that we use here. And thank you.
Thanks. Any questions? Yep.
Yeah, very cool result. It's more like a clarification. So for methods, you obtain this leading modes by applying this UF analysis onto AOD, and
Yes.
then obtain this associate asymptotic forcing or SD forcing by regressing SST onto that leading mode of AOD.
Yes,
Is that right?
correct.
I was wondering if you were to, say, apply this UF directly to the fully coupled single forcing round generated SSTs, would you get the same patterns or modes of SSTs? Would that be more appropriate to consider that as a direct SST forcing to the active response?
So I did compare the direct output of the SST from the fully coupled run. So the SST response. Okay, let me go back to the slide. So the SST actually we used here is taken from the fully coupled simulation. So it would be the same as if you're using the same data to regress onto the OD, the same PC timelines. I guess another thing is about the, you're asking is about the linearity, if we kind of decompose them into radial forcing versus SST response to the forcing.
Yeah, the linearity can be also interesting. I was just wondering the leading pattern of SSTs, like regressing SSTs onto the AOD leading mode versus the leading mode or leading UF of SST itself.
Because even though in the fully coupled model simulation, this is still the driver is the emissions itself. So the SST would be any of the change you see in the SST is still due to the emissions. So if you so I did do that. So the dominant mode is very identical to what I did here. It's just using based on the AMA because the data itself is the same. Yeah.
Any other questions? Yep.
I'm curious about the causes of the increased pressure in the North Pacific in the low latitude mode. You have this big increasing high pressure. If you have any thoughts, yeah, that one. If you have any thoughts on how is it caused?
I am not really clear about what causes it because the North Pacific here cools more than all the other ocean basins. I wonder if it's because of the cooling that kind of leads in more kind of enhanced descent, vertical motion. So you have kind of a divergence in the surface, and this is how you're getting kind of a cool high response in the North Pacific. Yeah,
Makes sense. Yeah. Could be a teleconnection. I was just wondering if you had thought about it.
Yeah, that needs further kind of thoughts on what causes it. Yeah.
Awesome. Thank you.
Thank you.
Thank you.
So our next speaker is Pedro on Nino.
It should be called Linia, because it's a cold pattern. We all get confused. What's El Nino? And so I'm going to add to that confusion.
Maybe we need to abandon Linia.
Just a gender neutral. Yeah,
gender neutral.
Anyway. So these are observed SST anomalies and rainfall anomalies for last year, October September, October, November season. And while the rest of the planet was baking, the Indian Ocean was in this cold pattern, which, so here I'm using optimal interpolated SSTs, which are higher resolution, and that helps you resolve this really strong cooling on the equator. It's hard to see in other SST products that are more heavily smoothed and interpolated. And you can see that along with that intensified equatorial cooling in the Indian Ocean, you had easterlies, anomalous easterlies. Recall that the climatology of the Indian Ocean during this time of the year is weekly westerlies. So these were probably close to absolute easterlies, driving, upwelling, reinforcing this cooling pattern. And with it, you have rainfall anomalies that are consistent with the SST anomalies. A lot of drying. Look at the color scale. That's a massive drying over the Eastern Indian Ocean during that season last year, influencing Sumatra and Java. Recall that Java is the most densely populated island on the planet. There's 200 million people living in Java, that tiny, tiny island, almost on the edge of my map. And then West Africa, in East Africa, this season there were torrential rains. This is a part of the world that has been experiencing persistent drought. And so this looks like the Indian Ocean dipole, which is a leading mode of one of the leading modes of SST variability in the Indian Ocean. So how rare are these events? Well, actually, the only time that this happened was in 1997. And this is the same plot for that year, very similar. Perhaps some differences, but I think they're strikingly similar. And actually, these are the only two times that this type of event happened in the Indian Ocean since 1980, when we have these high-res data that can resolve what's going on the equator. So there's this, sounds like the Indian Ocean can do this equatorial basin-wide mode. So if you average all those two events, and then we have the dipole mode, which is the rest of the events in the Indian Ocean. If you compose it based on that box off the coast of Sumatra, you get more of a monopole restricted to the eastern side of the basin with much weaker rainfall anomalies. So there's a lot of confusion on what's the Indian Ocean dipole, and the dipole aspect of this variability is coming from this really strong, very rare equatorial events, and most of the events in the observations, at least since 1980, are these more coastally confined cooling events. There's also warming events. The warming events are like this coastal pattern. There's no warming events that are equatorially intensified, like the ones on the top. So every time there's a big anomaly in the Indian Ocean, I get excited because we wrote a bunch of papers proposing that as a result of climate change, the Indian Ocean could start experiencing much stronger variability associated with the emergence of an equatorial mode that would involve dynamics more akin to El Nino in the Pacific, with anomalies more like this. I would call it La Nina Indian Ocean. So every time one of these events happens, I get excited. It's like, this is happening now. So I'll show you a bit. These are results from one of those papers. These are some idealized simulations of the last glacial maximum in which we got rid of ENSO, we got rid of the dipole mode by just restoring SSTs, and because the mean climate was so altered with a climatology that looked more like the Pacific with absolute easterlies, then this climate pattern started emerging in these simulations. When you start having westerly wind anomalies in the east, in the western side of the basin, it would trigger a Kelvin wave. These contours are anomalies in the thermocline, the depth of the thermocline, and a few months later, those anomalies will turn into what you see on the other panel. These are composites from these very idealized simulations, and we think this happened in the Indian Ocean during the last glacial maximum. We see evidence for this type of mode in CMIP simulations under very high greenhouse gas forcing RCP 8.5. We see some evidence of this mode, but there's issues with the CMIP-5 models. And that's why we've always been skeptical about this idea. And the main issue with the CMIP models is that they're too variable in the Indian Ocean. So that's the standard deviation of SST anomalies during the September-October season in this high-resolution SST product. And that's the same exact calculation for the CSM1 large ensemble. During the same period, the map on the right is the average of the standard deviation maps in all 40 members of the lens during the same exact period. And there's actually no member in the 40-member ensemble that looks like this in terms of amplitude. So the lens is too variable, and most CMIP models are too variable in the Indian Ocean. So then this has a lot of issues, because then it probably affects the sensitivity of this variability to greenhouse forcing, and it's also creating too much climate variability. So we kind of got stuck here, and we spent like a bunch of years not doing anything about this problem until I had to write an NSF report, and I was like, I need to make progress on this project, so what do I do? So that was 3 weeks ago. And we are on the second no-coast extension, so this is, I'm sure you've been there. That's how I roll. And I've been working on the CSM1 high-resolution simulation. So it's like, okay, let me look at the high-res model. How does the model does this variability? So then, if it simulates realistic variability, then we can look at what it does under climate change in the future. We don't focus on the LGM in the future, and voila. We only have, actually we have 3, that number is wrong, we have 3 historical plus RCP 8.5 runs. There's more coming, so I did the exact same calculation, the standard deviation during this season, and you see that it's a lot closer to observed. So, this is great news, and perhaps you're wondering where is the improvement coming from? This is the exact same model, the exact same forcings. It's just increased horizontal resolution in both the ocean and the atmosphere. The atmosphere is 25 kilometer resolution, the ocean is roughly 10 kilometer. And this improvement, there's a mixed resolution ensemble too, with high resolution in the atmosphere, low resolution. And that, I looked into that map, and this improvement comes from the ocean. So increasing resolution in the ocean makes the simulation of the variability. And this is pretty new. I don't think anyone looking at these simulations has seen this. And it's perhaps due to a much more realistic simulation of coastal upwelling. All this variability is generated off the coast of Sumatra by this very narrow coastal upwelling, that when you have cooling, then that cooling weakens the winds, that produces more southeasterlies, that produce more upwelling, because those are upwelling favorable, and there's this local feedback. But if the upwelling is too broad off the coast, you're going to create a bigger patch of cooling, and perhaps that's the explanation for why the lens is so variable. So you can compare the occurrence of these equatorial, these really strong, very rare equatorial events, and I took the values on that equatorial box that I think I showed you before. The box on the top here on the equator in red, and did histograms comparing the observations in red, the 3 high resolution runs, and the average of the distributions from the length, from the 40 members. And you can see clearly what we see in the standard deviation in gray. You can see the length extremely skewed towards this very strong, cold, equatorial anomalies, all the way up to here, minus 2.5. That's clearly unrealistic. We haven't observed any event that cold. And this little bar here, the red bar is the 1997 event, and last year's event is in this red bar. And if you look at the greenish, bluish bars, they're a lot closer to the observations in the distribution of the SST anomalies in this box. There's even one member that looks almost exactly like the observations, and there's no member in the large ensemble, in the low-res large ensemble, that looks like what we observe. So there's a clear improvement in the model in how it simulates the variability much quicker. So now we can see, well, the variability is not over-exaggerated. We can see what it does as greenhouse gases increase and they affect the mean state of the Indian Ocean, and the variability could change. So this is my last slide showing that. So I'm now plotting, it's actually a very simple curve. You can see that index on the equatorial Indian Ocean. In black, you see the observations with the very extreme events, 1997, the last year event. And then each of the color curves is the anomalies from these 3 runs. And you can see that these really strong cooling events are pretty rare during the historical period. Perhaps they're a little too strong in this yellow run, but one of the runs, the blue one, has as many extreme events as observed. And then as you go forward in time, these events become like a lot more frequent. I don't have to do any statistics here, so I just plotted the time series. I don't think I need to convince you that the variability goes up by a lot, and these events start happening a lot more often. In today's climate, they happen correlated with El Niño, like last year. When we go into the future, they start happening on their own. So you can ask me about the mechanisms after my conclusions, perhaps. And so the increasing horizontal resolution, mainly in the ocean, improves the simulation of Indian Ocean climate variability in CSM with a lot more realistic frequency and amplitude of these very rare but very impactful equatorial events. And when we look at the changes into the future, these events become a lot more frequent under a high emission scenario. So perhaps, I don't know the answer for medium range emission scenarios. And so you can imagine an increasing frequency of rainfall extremes in teleconnected regions within the Indian Ocean, but also in the southern hemisphere. A lot of the teleconnections, this variability in tropical rainfall in the Indian Ocean, in convection, drives massive teleconnections to the southern hemisphere, Australia, or even West Antarctica, and all the way to South America. So with that, I'll stop and take any questions.
Questions?
It's really interesting to see in contrast to the Eastern Pacific, where the warm events become more extreme. In the Indian Ocean, the cold events become more extreme. And I guess that's the mean state change. The Indian Ocean is just, if it's 32 degrees, it can't be any more than that.
Yeah.
It can be a lot colder.
Thanks for that question. Okay. The Indian Ocean, right, recall, it's like a bathtub. Today, it's just almost uniformly warm. What greenhouse gases do to the climatology, it's make the eastern side warm less. So it creates room for more variability, if you think in terms of amplitude. And it also changes the direction of the winds from weakly westerly to weakly easterly. So then the mean climate starts having upwelling, and Earth interactions can happen more easily along the equatorial Indian Ocean. So warm events also start happening. Actually, in the time series, if you I should have drawn the median to see that also the warm anomalies become more frequent, not as intense, but it's both become. But you always have the cap of the tropical mean temperature that will limit how big these anomalies
I was
can be.
wondering if there's implications for, fisheries along Sumatra there in an analogy with Ecuador and Peru.
Perhaps, I have no idea, but these are huge changes and thanks for the question.
Yeah, I have a question. So you invoked improved representation of upwelling, but I'm wondering if you think that maybe Indonesian through flow could also be playing a role, which is certainly better results.
Yeah, perhaps, and I've thought about it, and again, I made all these figures 2 weeks ago. So, and perhaps even there's effects on the mean winds during this season, because the models tend to simulate this season, like CMIP models, the low-res models simulate this season where the winds are not clearly westerly as they are in nature. So that's why also the variability it's a little too strong. It's easier to make the winds more easterly because you're starting from a state that is not. It might not be that simple, but I think the first guess is that it's upwelling. And no one is looking at its through flow in these high-res runs. And I think there might be really exciting surprises there.
Okay, I'm going to change the slides, but there is a question online as well.
Do we have time?
Yeah, while we're doing this. He's asking what are the kind of broader impacts more generally of this variability, of our realistic variability?
It's a good question out there. I peeked into what it does to rainfall variability, and I think, again, the Indian Ocean is a place where models predict large increases in rainfall extremes through thermodynamics and through changes in the mean state. So this could be another source of extremes through the SST variability. That's something someone should look into.
All right,
yeah, thank you.
Now we have Brandon Molina on externally forced changes in
Right.
Maybe try holding it at the screen and then moving it over. Oh, yeah.
Perfect. Okay. All right. Well, hello everyone. Today I'm going to present some results from my first project that I'm working on in my PhD. I'm a third-year student at CU, and I'm working with Pedro Denezio on this. And this project could not have been done without his immense help. I also have meaningful contributions from Clara Desser in this project, and so I'm very excited to share some of these results. So today I'll be presenting on how ENSO's oscillatory behavior could be changing under external forcing on the climate. And so we first want to see how the time series of the Niño 3.4 index looks like in our current climate. And so we can see that since 1970, we've had this feature of ENSO, which has this asymmetric temporal evolution between El Niño to La Niña and then La Niña back to El Niño. And so we can see is that since 1970, there's a rapid transition between these strong El Niños, and then we have a longer duration between the La Niña into returning to El Niño. And so that asymmetric feature of ENSO has made it difficult to really forecast when the onset of an El Niño will come, which is different from the predictability of a La Niña event. And so what I'm going to be studying in this project is how could this feature of ENSO potentially change under external forcing. And so first, I want to look at a model that can actually realistically simulate that asymmetric behavior. And so here I have
created a composite of events for the observations with 1,500 years of pre-industrial control from CSM1. And even though the observed observations of an El Nino event are limited to only since 1950, I can still see some features that are being simulated by CSM1. And those are this rapid transition from El Nino to La Nina, and then that longer duration of La Nina, and then just stays in neutral after that. Looking also at the autocorrelation function, we can see this more clearly without any biases on how I choose the threshold of an El Nino event. And I can still see those asymmetric features, especially in the strong negative correlation at a lag of about 2 years. So that represents that consistent transition from El Nino to La Nina. And then after any other lag, that correlation becomes very weak, which represents that lack of consistent transitions from La Nina back into El Nino. And so now that I know this model is is fairly good at representing these asymmetric evolution, I can look at other climates in this in CSM1 and see how the oscillatory behavior can change. And so here I have plotted the tropical Pacific mean state changes of SST and the wind stress. And one thing I noticed is that under these colder climates from the when we had glaciers, it produces an equatorial enhancement of cooling, as well as a strengthening of the trade winds. And then conversely, if we look at climates with increased levels of CO2, this global warming scenario shows an enhancement of equatorial warming, as well as weakening of the trade winds. And so just looking at these mean state changes of the tropical Pacific, it gives me a clue at, or it indicates to me that there must be some shifts in where the air-sea coupling might be, which is involved in the dynamics of ENSO. And so a better way to find or identify where that air-sea coupling is strongest is to identify a center of action. And so far in our current climate, we've been using the Niño 3.4 region, which is from 170 west to 120 west. And this represents the area where SST anomalies produce the greatest variability in the winds. And using this method of EOF analysis by computing where the SST pattern is correlated with the leading mode of equatorial zonal wind stress, I see that for the observations, I get almost perfectly that area. So I find exactly where the peak along the equator happens, and then I just make my box 25 degrees to the east and west of that line. And I do the same thing for the pre-industrial control from CSM1, and I can see that box region is fairly similar to observation, so that's pretty good. The only difference is there's a slight bias towards slightly higher magnitude of correlations. But now, if I look at what this looks like for the two different climates, and so here I've just shown the ones that the colder climate that shows the greatest changes, and the warmer climate that also shows the greatest changes. And so this would be the 15,000 years ago, the glacial climate, shows a substantial pronounced zonal shift of that center of action towards the west. And then in the warmer climates, we see that zonal shift is towards the eastern basin of the Pacific. So that's telling me that the external forces changes of the mean climate is actually driving these center of actions. But what I want to know is how do these zonal shifts of the center of action affect the oscillatory behavior of ENSO? And so now looking back into these composites for these climates, we can see that for these colder climates, ENSO becomes completely non-oscillatory because the transitions from El Nino to La Nina become less consistent. And then for these warmer climates, we can see that ENSO becomes much more oscillatory than it is today, because that transition from La Nina to El Nino starts happening more consistently. And so that's a very pronounced change in the oscillatory behavior between these two climates. Looking also at the autocorrelation function, we see that those pronounced changes are very clear. We see for the warmer climate, at a lag around 3.5 years, that there's a very strong positive correlation as opposed to the pre-industrial. And then for the colder climates, there's no real strong correlation at the lag of around 2 years, where we see that consistent transition from El Nino to La Nina. But we ultimately want to understand what's really causing these changes in oscillatory behavior. And so we must look at how the thermocline variations, how effective these thermocline variations are at actually kicking off the next events. And so if we look at these hopular plots with the longitude at the x-axis and then time going up, we see at the peak of El Nino for our pre-industrial control that this produces a delayed thermocline response that then travels back as a shoaling of the thermocline. And so this brings a cooling of the surface layer, and this is what ultimately transitions El Nino into La Nina, because these cooling tendency of the thermocline is able to cool the surface within the region that the air-sea coupling is strongest, and that would be the Nino 3.4 region. However, if we look closer at what happens after a La Nina event, we can see that the associated delayed thermocline response, that is deeper thermoclines, brings a warming tendency to the upper ocean, but that only happens in the far east term basin, which is outside of the Nino 3.4 region. And so in that region, only the thermocline is coupled with the SSTs, but the SSTs are not coupled with the atmosphere. Therefore, those slight warming you see doesn't keep growing, because that region is too cold to actually produce any convection in the atmosphere. But now if we look at what happens in a warmer climate, we see the similar pattern after El Nino. But then what's more interesting is what happens after La Nina, is that those warming tendency from the thermocline actually produces those warming anomalies within that new shifted region of center of action. Therefore, those anomalies can actually be coupled with the atmosphere and can keep growing into a fully fledged El Nino. And then lastly, looking at the colder climates, we see quite complete opposite, that our far western center of action has these shoaling of thermocline that produces cooling only still in the eastern Pacific, but that's way outside of the region where the SSTs are coupled with the air, and therefore we don't see any signal of El Nino after an El Nino event. So in conclusion, I see that in my analysis that these zonal shifts in the center of action can affect the oscillatory behavior of ENSO. And this could be very important for future predictability of El Nino events, as if ENSO becomes more oscillatory, then the onset of El Nino will become more predictable, just like La Nina is today. These results can also help us understand how ENSO is simulated in other coupled models. And so I would also like to understand how this signal, if it's robust in other CMIP models. And so far I've only done it for CSM1, and so something that I really want to keep working with is just trying to find if this is a robust signal. But ultimately, these results really depend on the pattern of warming of the Pacific. that I showcase in the mean state changes. And as we all know, so far CSM1 has been a little on the bias of being warmer than what we see happening in observations. But it's still very insightful results. Yeah, thank you.
Any questions? I had a question. I mean, you focus on coming back to the El Nino, but it seemed like you had a double El Nino. Do you think that really happens in individual events, or is it kind of you're averaging different events that end up in an El Nino?
You mean like a double capture there?
Yeah.
Yeah. I made so the shading represents all the events that I've made the composite of. And yeah, it really is just the events that get composited together that produce a 2-year El Nino, which is very interesting actually. I have not had a chance to look into it.
If you could composite the ones that give you the El Nino in the first year and see whether those also give you it in the second, as opposed to it being ones that just don't give you the El Nino until the year +4.
Right.
Any other questions?
I'll have a very naive one because I don't have any clue about ENSO. So you always talked about the center of action, where the ocean is coupled to the air much more than outside of the center of action. And without having any idea what the role of this center of action is, to me it seemed like this coupling does not depend on the absolute temperature of SST. So maybe you could give me a hint how to understand this better.
So what do you mean by the absolute temperature, like of the Pacific?
I saw that outside of the center of action, sometimes you can have quite extreme anomalies, but still it's not defined as the center of action. So what?
Like like in this part right here, right?
For example, yeah.
For example.
So how should I understand that there is for sure less, but why is there negligible for your theory?
That's a very good question. I'm not sure how to respond to that, but that's a very good question. I'll look into it.
Is it because it matters how warm it is relative to the rest of the tropics and the extent to which that is changing? Is that Pedro?
Yeah, the Eastern Pacific is so cold that you can warm it, but the atmosphere will never know. So that's why you have those big, the SST anomalies can be there, but they are not, the atmosphere will not respond to those. Just to have to be warm enough.
Okay.
Yeah.
Does it matter like how the SST anomalies influence the zonal SST gradient?
Well, I think you need mean surface wind convergence to get any kind of convection. I think that's what you're talking
So
about.
it's both a gradient and the magnitude, right? There's these two mechanisms how you drive winds. Wind responses to SSTs is more like the Gill type, which is just the magnitude of the SST anomaly and the heat convergence, and then more the Linsen and Negan mechanism, which is the SST gradient that will create a pressure gradient, and that will also affect the trade wind. And perhaps in climate models and in nature, it's a mix of both mechanisms. So it's the anomaly and the gradient of the anomaly. But in the far Eastern Pacific, like in those plots that Brandon was showing, the gradient cannot drive westerlies, will drive easterlies because the SST anomalies decay. And the absolute anomaly, or the SST anomaly cannot excite the atmosphere because the mean state is so cold that it cannot produce convection.
Thank you.
I hope that explained it.
All right, thanks. So our next speaker is Hang Bui, did I say that right?
Yes.
On the response of the MJO to global warming.
So, hi everyone. Can you hear me well from here? I just worry that I can't speak loud. So, yeah, thanks so much for having me here. I'm Im Bui. I'm currently a research fellow of the Center of Excellence for Climate Stream at Monash University in Melbourne, Australia. So, before starting my presentation, I just want to acknowledge the call to the work that including my colleagues at Monash, ECN and Peter, and also one is from PNNL. I also want to thank the IBS Center for Climate Physics in Busan, South Korea for providing the data for the report. Okay, so I think in your own study, you already know about the Madden-Julian oscillations, or MJO, or at least you have heard about it. But in case that you are not familiar with the MJO, so it's a phenomenon that causes the tropical precipitation to alternate between the intense and suppressed periods. So you have more rain and less rain. And the intense of rainfall is associated with the MJO star in the Indian Ocean, and then it moves slowly eastward into the West Pacific. And it's complete the circle like around 30 to 90 days. So my background and research interest is more on the global warming. So on the global warming, previous study, including my work with my postdoc advisor, Eric Maloney at Colorado State University. So we have a series of papers examining how MJO change under global warming. So at the time, we analyzed the CMIP models, like CMIP 5, CMIP 6, and we found that under global warming, MJO precipitation amplitude tends to increase, but MJO wind amplitude tends to weaken, or it's increased with a slower rate compared to the MJO wind. We also run our planet models from the Cesm 2, and we also found that the MJO propagations tend to be faster under global warming. And it's also extend further into the Central and Eastern Pacific in the warmer climate. However, we also noted that it's not just the mean SST change, but also the patterns of the change can regulate the MJO. So, for example, that I think you probably noted that like during the El Niños, the MJO tends to propagate faster, but during the La Nina, it propagates slower and tends to detour over the maritime continents. So, I think in the next around 10 minutes or so, I will focus on the impact of warming patterns on the MJO. And in particular, we will try to answer these two questions. So the first one is what's the possible warming patterns in a warmer climate, and how these warming patterns can impact on the MJO. And to answer these two questions, I'm using the Cesm 2 large ensemble. So it has 100 ensemble members around 1 degree resolutions. And I will focus on Ebola winter, where the MJO is strongest. We will comparing the difference between the future SSB 370 scenarios and the current historical simulations. Okay, so let's move to the results. So here's the map showing you the SSD difference between the future and the historical simulations average for 100 ensemble member. So you can see that the patterns look like the El Nino patterns with warmer in the Central and Eastern Pacific. Yeah. And what we did is that we applied the K-mean cluster analysis into these 100 ensemble member, and here's what we get. So we have 3 different groups of 3, what I call these 3 potential warming patterns in the future. We call it moderate amino-like group, the weak amino-like group, and the strong one with the number of ensemble members in each group. One thing that I want to notice is that these are the difference relative to the total, and it's not the absolute from each group. And we did a few statistical significant tests just to make sure that each group, the pattern is different from the total. And also each group is different from the other group. And we also justify the number of the group that we use by using the L4 method, just to make sure that the 3 clusters are the optimal number of yeah. So after classify 100 ensemble members into 3 groups, we go further into examining the temperature change in each group. So in the first panel here is just doing the tropical mean of the SST change. And as you can see that for the 3 groups, the changes is very small. And also the meridional gradients, the differences between the northern and the southern hemisphere is also quite small. However, the zonal gradients of SST changes is quite large and significant, which is the differences between the Eastern Pacific and Western Pacific. So we then examine how the difference in the SST change, the pattern change can affect on the mean state. So here I'm showing you the vertical structure of the specific humidities and also the wind. I'm not going to discuss further on the mean state changes, but we have some more discussion in the paper, because here I want to focus on how the patterns of the SST change can affect on the MJO. Yeah. So here's the MJO amplitude. So again, this is the MJO precipitation amplitude and MJO wind amplitude that I average from 100 ensemble members. So as you can see that in the future warmer climate, we have the enhance of MJO rainfalls. And for the MJO wind, we have some increase in here, these regions, but over the Indian Ocean is tend to weaken, which is consistent with our previous CMIP 6 model and CMIP 5 model too. Then for the first group, the first warming patterns, we call them moderate warming patterns, we see that the enhanced of rainfalls tend to be here and also in the Indian Oceans. But for the weak El Nino warming patterns, it's that to be quite different, that you have a negative anomaly here and enhance over the regions. And for the strong El Nino like warming patterns, for MJO precipitations and MJO wind tends to increase everywhere, especially in the Pacific Oceans. And yeah, again, these patterns are the difference relative to the total. So yeah, it's relative to the total, not the absolute one. I think, yeah, and I think the next question is why they have such kind of difference in MJO precipitations between clusters. So to answer the question, we use ANFA framework. Not sure that you are familiar with this, but I will talk more about this in a few minutes. But here I'm just doing the domain average for the MJO precipitations, just like I showed you in the previous map. And on the x-axis here is the zonal gradient SST change for each 3 group. So you have the strong, the moderate, and the weak SST warming patterns, and see how the MJO precipitations vary with this. So, okay, so the ANFAR is just a quantity that's proportional to the vertical moisture gradients and reverse proportional to the vertical dry static gradients. And we have more detailed paper talking about the alpha and using it to examine the MGL precipitation in the other paper. So check it out if you want to look for the details. But here, given the short time for the presentations, I'm just quickly show you how the alpha difference between cluster. So here's the vertical structure, the anomalous vertical structure of alpha. So three different colors for three group of one patterns. And like for here, the red color is for the strong amino-like patterns. And you see that this have a positive from the lower to the upper troposphere, which imply that they will have a stronger vertical moisture absorptions. And then we can expect that we have a stronger MGO activity. And then I'm just doing the vertical integrated of the alpha and then plot it again with the MGL precipitation change. So you can see that the change of alpha and MGL precipitations fall along the straight line. Yeah, the straight line and offsets from the origins. Which means that we can use alpha to explain for the change of MGL precipitations between different warming patterns. In the paper, we also go further and kind of decomposing the alpha to the changes of the vertical moisture gradients or the changes of dry static energy gradients. And we found that the change of moisture gradients got a dominant one. Okay, so that just showing you again that the change of MGL precipitations for the warming patterns, and similar, we also have the MGL wind changes. We also examine other MGL characteristics like the MGL, the eastward extension, and also the MGL propagations. So for the eastward extension, we found that the signal is quite significant between the patterns, and that the strong amino-like patterns, we will have the MGL kind of propagate faster compared to the weak amino-like patterns. But for the propagation speed, as you can see, the bar here showing one standard deviations across all the ensemble member. So it's insignificant, and we thought that this may be used to a strong inertial variability signal model. Okay, so okay, yeah. So given the impact on of the SST warming patterns on the mean state and also the MGL characteristic, we thought that it's very interesting if we examine the impact of warming patterns on the MGL teleconnections. So here's against the map of MGL's induced geo potential height 200 hectopascal for the total 100 ensemble member, and also for the three different warming patterns. Unfortunately, we don't see a significant signal at the regions without protection one, especially in the West Pacific regions. But if we focus on the ensemble mean for each group, you will see that, like, if you focus on the moderate or the strong group, and the blue one is for precipitation, and the red one is for the geo potential high. So it shows that in the future warmer climate, the MGL teleconnections tend to become weaker, at least for 2/3 of the ensemble member. Okay, so summary for what I'm just presenting. So first of all, we have three potential warming patterns in the future warmer climate. And then we're examining how the warming patterns can impact on the MGL characteristic and also MGL teleconnections. I hope that I didn't go so fast, but I guess I did. So just check out our paper, just published earlier this year for the details. Yeah, thank you.
Time for one quick question. I had a very quick one, but I'll get the next slides up at the same time. This alpha parameter and the interannual variability, could you look at that in interannual variability and connect it with the MGL and observations and kind of if the models are doing that kind of connection correctly? Or do you think you really need big changes into the future to be able to?
Yes, that we can do some comparison with historical simulations with observations. So, yeah, that's a good point.
Okay, yeah, that would be interesting, maybe to see, have some confidence as to whether the models are doing things right or not.
Yeah.
All right, thank you. Okay, so our last talk before the coffee break is James Larson on impacts of Western boundary currents.
Thank you. Okay. Oh, great. Thanks everyone for being here and for the organizers. So today I'm going to be talking to you about the Western boundary currents, which are narrow, relatively warm ocean surface currents that exist on the western boundaries of most, if not all, of the oceanic basins. Here's an example. You can see the Gulf Stream current coming up, and down here in South America, the Brazil current, and the Agulhas current coming off the southern tip of South America. I'm going to be talking today about 5 different western boundary currents, and these are just a few examples. Starting off with some motivation, though, I'm going to briefly highlight Shoshiro Minobe and his collaborators' work from a 2008 study where they started by looking at precipitation over the Gulf Stream, which is in the colored contours, and overlaid are the black SST contours. And this is all for the time mean over 4 years for observations. And they found that precipitation tightly hugs the sharp SST contours of the Gulf Stream. When they prescribe those sharp SST contours in an atmospheric model, they get a very similar precipitation response. However, when they smooth over those black SST contours into an SST gradient that's more similar to what you might see in the internal ocean basin away from that boundary current, the precipitation response largely disappears. And this kind of paper is kind of what's really motivating us, is how is this underlying ocean boundary current, which is really driven strongly by internal ocean dynamics as compared to maybe the rest of the global oceans. How is this driving the atmosphere above? But it's moving a little more ways, how is it impacting atmospheric variability? Because they focus more on the time mean response. And we are focusing on the variability because a lot of the literature has focused on some of that time mean response, but the variability is less clear, largely due to the fact that the mid-latitudes are just so noisy. There's so much going on, especially in the wintertime, which is what's driving our research question. I pretty much just said that. Data and methods. I'm going to start off by showing you Error 5 reanalysis. We're going to specifically look at 2007 to 2022. We found that our results are sensitive to the spatial resolution of the underlying SST forcing data set. Error 5 is at 1/4 degree. And then I'm going to be ending the talk looking at the IHES experiments, which is CSM version 1.3, fully coupled, comparing the 1 degree low resolution, more like a standard resolution, right, of like your CMIP runs, to the high. And I really want to emphasize high being what we found to be interesting is that the ocean resolution is at 1/10 of a degree, which is really important for our results. And we're going to be focusing on the 250 years of the pre-industrial control data forcings. All results have had the seasonal cycle removed, monthly mean anomalies, and all results are going to be for the extended winter time for the respective hemisphere. I'm going to go through this actually pretty quickly. This is essentially just a reproduction of that Minobe result for the Error 5, showing that not only is it just the precipitation, but also the vertical motion really tightly hugs SST contours in the time mean. But I really want to focus on other things today. Okay. So here we have the standard deviation of SST anomalies for the Gulf Stream. You can see that where those SST contours were before, we're seeing a heightened SST variability. When we then bring in a regression of local to local grid cells, what I mean by that is regressing a grid cell within the ocean to the grid cell just above it in the atmosphere, not any spatial averaging or indices, we find that the atmosphere, the vertical motion, really tightly co-varies with SST anomalies within that western boundary currents. Meanwhile, though, if you look to the rest of the internal ocean basins, you find that a lot of that co-variability largely disappears. Knowing that a lot of these, that the Gulf Stream is driven by a lot of internal dynamics, SST contours, or excuse me, sharp SST gradients, mesoscale eddies, we're seeing that this is sort of suggestive of the ocean driving a lot of this variability. And the same thing comes through with the precipitation. This is showing Era 5 precipitation, but we've also looked at GPM precipitation, looking at more satellite-derived product. Very similar story. Yes, and it's not just the Gulf Stream. So here are the same 3 figures I just showed, just slightly different layout. And now when you look at 4 other boundary currents, 5 in total, you can see that for the Gulf Stream, the Kuroshio, the Agulhas Current, the Brazil Malvinas, and the East Australian, we're seeing this consistent air-sea signal occurring that where away from the boundary current, that tight local-to-local covariability is not really there, but within the western boundary current, you really see it coming through strongly, suggesting that these ocean dynamics are playing a prominent role in driving these localized circulation changes. And I'd really like to point out the East Australian. This is a current that is known for having a lot of mesoscale variability, but if you compare it to the other boundary currents, it's not on the same scale as far as SST variability. But then that even with lower amplitudes of SST variability, we're still seeing this really strong signal of the dynamics at play at the boundary current. But these are sort of parameters that are relatively close to the surface. This is vertical motion at 850 hectopascals, I should have clarified. If we take a spatial average of the area just over the western boundary current, and then look at vertical motion, not just at 850 hectopascals, but higher up into the atmosphere, and perform the same sort of local-to-local regression technique, we can see how air-sea covariability is extending up into the middle and upper troposphere. So here on this left panel, I've got the 5 different boundary currents over different colors. And it's just a spatial average of that same regression technique I just showed, where, of course, naturally, as you might expect, close to the surface, we're seeing the strongest regression coefficient, the strongest coupling of air-sea covariability. But that covariability is not remaining just close to the surface. It's extending beyond the planetary boundary layer, extending up into at least the middle troposphere. On the right panel, we have confidence interval derived loosely from the student's t-test. We've played around with a little bit, and I can go into those details if you'd like to know more. But you see that, like following the 90% confidence, that's extending up to like 400 hectopascals, really showing that suggesting that these ocean dynamics are driving these localized circulation changes. But we're here at a CSM workshop, not an Era 5 workshop. So here are the modeling results that you guys want to see. Okay, so now I'm showing you the regression of vertical motion at 850 hectopascals. Left column is going to be Era 5, this is what you've seen. Middle column is that high resolution CSM, and then comparing it to the low resolution. That high resolution is comparing quite nicely, showing that fundamentally the dynamics within CSM are sound, but when you're simulating at that 1 degree resolution, which is sort of the standard workhorse resolution that we see a lot of the CMIP and other style experiments being run at, they're not really getting that air-sea covariability, and that is true amongst all the boundary currents. I really love the shape of this Brazil Malvinas current, that you get this cool lobster claw that you would really, to think about how the atmosphere might form that shape is hard to wrap your head around, but the way the underlying oceanic currents run, it's just so cool how you can see that in the high resolution and then just poof, and grow. And so this result is kind of what's going to motivate us moving more into the future. We plan to take these results for digging deeper into the modeling studies, looking to see how these underlying boundary currents might be driving changes in the clouds, radiation, not just localized circulation changes, but how it might be impacting jet stream variability and the storm tracks as a whole. This work so far was in my master's, and I'm planning to continue moving forward with it into my PhD. Conclusion, really just that we're looking at how these oceanic-driven dynamics are changing localized circulation changes. And I also would like to point out that for those of you that aren't really deep in this air-sea interaction literature, it's normal for most papers to maybe just look at 1 or 2 boundary currents. It isn't always normal that people are exploring all 5 of these boundary currents across the globe, seeing these consistent signals across the different regions. So with that, I'll end and take any questions. Thank you.
Questions, lots of questions.
Yeah.
Yeah, Kirsten.
I was just curious if you've looked into how persistent these precipitation anomalies are over these western boundary current regions.
Yeah, so we're looking at timescales of month to month, not sort of decadal. Once maybe like the warm eddy that's driving these localized changes kind of dissipates, it does tend to disappear. And that also holds true when you move away from the winter season into the summertime season, when all of a sudden that cold continental, there's not as much contrast between the cold continental air and the warm ocean. Given it's not that it completely disappears, we are seeing subtle hints of this in the summertime months, which is kind of exciting. We're thinking about looking at that more.
Steve?
Yeah, in addition to the boundary currents, there's the Southern Ocean, so I'm wondering if you're going to be looking at that as well.
Yeah. Where's the mouse? Okay. Is it this one? These are the standard deviation. Here's the regression. It's not clear, and I think I don't know why. My intuition leads me down 2 different paths. One is that the Southern Ocean isn't as warm as the western boundary currents are because they're transporting a lot of the heat. I think that might play a role. And 2, because of the Rossby radius of deformation, the eddies in the Southern Ocean get really small. I'm not sure if the Era 5 reanalysis is of resolving that. So, I'm with you. I think there should be a response to it. I'm not sure. Frenger et al., 2013, looked into that though.
Yeah, it just was a nice, very nice talk. I was just making sure I understood what you were doing. You're taking monthly anomalies, you're doing these local regressions, and then you're averaging over the winter season. Is that correct? Or are you first doing the winter anomalies and then doing local?
Yeah, so I dropped the summer, yes, first I formed the seasonal anomaly, and then I dropped the summer months from my data set. I don't do any time averaging. It's not like a seasonal average. So I'm doing monthly regressions, month to month. Yeah, does that answer, I think?
Yeah, so you're including intra-seasonal.
Correct.
And year to year.
Yes.
So I think coming to your point, it was a similar point. I think it'd be interesting to take those apart.
Oh, yeah.
Yeah.
Yeah, that's a good point. That's break time.
Thank you. Yeah, so, thanks, everyone. So, we have a break now till 3. It's going to be some more cakes, so you have to eat those. But the coffee's probably cold at this point, but you're welcome to that as well.
There's some cake, yeah.
So today I'm going to talk about subpolar North Atlantic responses to increase the stratospheric aerosols in 2 climate model sensitivity experiments. And this is in collaboration with Yaga, Aishan, Jerry, Beard Unkar, and also Doug at Cornell. A little bit of motivation. So talk about stratospheric aerosol injection is kind of has been proposed as a strategy to kind of offset some of the negative consequences of global warming. However, the impact of these stratospheric aerosols are largely uncertain. So one of the regions that's critical for the global climate is the subpolar North Atlantic. It is important because it is the region for ocean deep convection and dense water formation, which is part of the Atlantic Meridional Overturning Circulation, or AMOC, which is crucial for regulating global heat and carbon transport. And also, there are significant interactions between the hydrological responses of the subpolar North Atlantic, I'll just call it SPNA, it's a very long word, and the strength of the AMOC and also the Arctic climate. So it is critical that we understand the impact of these stratospheric aerosols on this region. So we're gonna use 2 sets of climate simulation ensembles to investigate this problem. We're gonna use these 2, they're called GLINS SAI and ARISE SAI. So basically in both models, stratospheric aerosols are added in order to counteract the effect of elevated greenhouse gas. And the stratospheric aerosols are added in a strategic way. So for example, these are injections at different latitudes with different colors, and they also vary with time. So the goal is to kind of add these aerosols in a prognostic manner. So for the GLINS simulation, it uses the Cesm1 WACOM 5 physics. The reference simulation without SAI is under the RCP 8.5 forcing. And then the SAI simulation, the aim is to keep the global mean temperature, equator to pole, and pole to pole temperature gradient near the 2020 levels. And then the ARISE simulation is very similar to GLINS, but uses an updated version of CSM2 with WACOM 6. The reference simulation is a more moderate forcing scenario, it's under SSP 245. And then the aim of this simulation is similarly to keep the global mean temperature and temperature gradient at about 1.5 degree above the pre-industrial control level. So first of all, we're going to take a look at the simulated climatology. And it turns out the responses in these 2 models are quite different. So, here are the anomalies of sea surface salinity at the top 2 panels and sea surface temperature at the bottom. These anomalies are defined as the difference between the end of the century to the beginning of the simulation. And on left, the 2 panels are the changes in the RCP 8.5 scenario. And we can see that with global warming, we have a general increase of global temperature, but in the SPNA region, we have a warm and salty response. And when we're adding that stratospheric aerosols, first of all, the global mean temperature is indeed kept at a stable level. But then if you look at the SPNA, there is still a very significant response, and it remains warm and salty. And for the GLINS simulation, interestingly, in the reference climate, the subpolar North Atlantic actually becomes cold and fresh. It's quite the opposite from the CSM1 simulation. And when you add in the aerosols, the responses also stay relatively consistent. So just by comparing the results of these 2 SAI simulations, we find that despite the fact that we're using similar SAI approaches to counteract the impact of counteract a rising global SST, the response of the different models to these increased stratospheric aerosols can vary significantly. And in this case, it's quite the opposite. And this we find out is it's mainly due to intrinsic model differences. And then the AMOC responses are also very different in these 2 models. In the CSM1, so this is, the red is under the reference climate, which is the RCP 8.5. We see the AMOC weakens with the warming temperature. And the orange line is under the GLINS SAI. So when you add in the aerosols, the AMOC strength actually increases, opposing the weakening trend. And the end of the simulation, the difference between the two is actually 10 severe drop, with around 50% of the control AMOC strength is a very significant change. And then looking at the CSM2 sets of simulations, again, under the reference climate, you have a decreasing AMOC strength shown in the green curve. When adding the SAI, the weakening trend is somewhat mitigated, but the change is quite small. It's only 2 severe drop of change. And then we also take a look at the subpolar North Atlantic freshwater content. It's kind of similar, consistent with the salinity change we saw in the previous slide. In both CSM1 simulations, we have a decrease of freshwater content corresponding to the salinification in the subpolar North Atlantic region. And then in the CSM2 sets of simulations, we see an increase of freshwater content. But if we take a look, if we compare the SI simulation with the reference climate in these two sets of simulations, we find that general impact of SAI is to kind of decrease the freshwater content. Oh yeah, here, if you're not familiar with the freshwater content, the definition is here. It's actually the salinity anomaly compared to a reference salinity, and is integrated over this region and over the 300-meter depth in the vertical direction. So far we have seen that these two sets of SAI simulations have very different responses. But again, our scientific question is to try to, just a reminder, try to understand the impact of SAI on the SPNA region and their connections with the Arctic climate and their connections with the AMOC. So in order to do that, we kind of have to isolate the impact of SAI. So from now on, all the analysis you will see is the anomalies induced by SAI relative to the reference simulations. For example, for the CSM1 simulation, it will be the difference between Glenn's SAI and CSM1 RCP 8.5, and the ARISE is similar. And also, and we're going to understand the processes, especially associated with the enhanced salinity, through the lens of SPNA freshwater budget analysis. We will focus on understanding the sources of the freshwater in order to understand whether these changes originate from the AMOC variations or from other sources. Okay, so the freshwater budget analyses, basically the tendency of the freshwater. The total term is comprised of these different terms, including the surface freshwater flux, the advection in the horizontal direction, and then vertical advection, and also vertical mixing, and then the last term is horizontal diffusion. This term is quite small and is negligible in our analyses. So we're going to take a look at all these terms in our simulation. Oh yeah, I need to mention that the horizontal advection term will also divide it into the impact from the transport from the northern boundary, which connects to the Arctic Ocean, and the transport through the southern boundary, which connects to the Atlantic Ocean. So this figure summarizes all of these terms. Again, I want to emphasize these are showing anomalies, the difference between the SAI simulation and the reference simulation, and these are averaged over 2050 to 2069. So if we just look at the Glenn's sets of simulation for now, the black shows the total freshwater tendency. This is negative, which tells us that the subpolar North Atlantic is now losing fresh water. And if you look at the contributions, we see that the negative term mainly comes from, first of all, the blue, which is the vertical processes, including vertical advection and vertical mixing. And the most significant contribution comes from advection term from the northern boundary, meaning that the main term that contributes to the reduction of fresh water in this region is actually a reduction of freshwater import from the Arctic region, which is quite surprising to me, at least, because at first I thought the increased AMOC may have contributed to the reduction of freshwater in this region. Yeah, this is what I said. And for the ARISE simulation, we found a similar response, although the contribution from the surface freshwater is different in these two simulations. So now we see that in both cases, the freshwater decrease in the subpolar North Atlantic region are both closely connected to the Arctic climate. So what happens in the Arctic? Why do we have a reduced freshwater transport from the Arctic to the subpolar North Atlantic region? So next, we're going to take a look at the Arctic Ocean. We're still going to use a freshwater budget analysis to look at what happens. But the main terms in the Arctic freshwater budget include, first of all, the surface freshwater flux, and also advection through the Bering Strait in this part, and the advection through the SPNA region, which is the part we care the most. So here these two panels are showing what the budget terms look like in the reference climate. Just to give you an idea that in the normal climatology, the total freshwater budget in the black is mainly balanced by a positive term from the freshwater surface flux. You got freshwater from surface fluxes, and then it's largely balanced by the transport outside the Arctic Ocean into the North Atlantic. That's what happens in the reference climate. And now here we're looking at the differences, the impact induced by the SAI. So first and foremost, for the black, the total change we see is negative, meaning that the Arctic is also losing fresh water. So the main term that leads to this decrease of fresh water we saw is this purple. Purple is the surface freshwater flux. So this tells us that there is a significant decrease of surface freshwater flux into the Arctic Ocean. And in order to balance this freshwater loss, we would have this green term becomes positive, which is advection through the subpolar North Atlantic. So from here, we see that the reduced freshwater export from the Arctic to the SPNA is because it has to compensate for the freshwater loss from the surface. So the same process is found in the ARISE simulation, just because this one has a more pronounced response, so we just focus on this one. But then we're also curious to what happens to the surface freshwater flux, what causes this significant reduction. So we take a look at this different component, mainly the sea ice processes, sea ice melting minus brine rejection. The second term is river runoff, and the third term is precipitation minus evaporation. So again, this purple is the same as this purple is the total freshwater flux decrease. And then we see all of these three terms actually contribute to this decrease. But their contributions kind of vary with time. In the first half of the simulation, the sea ice processes contribute most to the reduction of freshwater flux. But then later on, the river runoff and PE kind of caught up. Okay, that's quite a lot. To summarize what just happened, we found that compared to the reference simulations, the Arctic Ocean has significant loss of fresh water from the surface. And then we found that the reduced surface freshwater input is due to partly sea ice growth, partly due to the changes in surface precipitation minus evaporation, and also river runoff. And then in the Arctic, to compensate for the surface freshwater loss, your freshwater export from the Arctic to the subpolar North Atlantic decreases, which ultimately leads to the decline of freshwater content in the subpolar North Atlantic. And that's why we see a salinification in that region. So surprisingly, at least to me, the connection with the Arctic is actually key to the SPNA hydrological responses we saw in these SAI simulations. This needs to be more dramatic, so. Okay, if we still have time. Okay, maybe not. But anyways, we're also interested to find out, the solidification we saw in these SAI simulations. Are they contributing to the AMOC strengthening, or if the AMOC strengthening contribute to the salinity? Well, at least for this part, we already know it's not the case because the Arctic is the main player. But the other way, we kind of want to understand this process by analyzing the surface density flux. So I'm just going to go briefly. The SAI induced increased surface density flux into this region, which will lead to stronger ocean deep convection and probably lead to stronger AMOC. And we decompose this part into the contribution from the surface heat flux and the contribution from the surface freshwater flux, and found that the majority of these changes are actually due to surface heat flux. So even though we're seeing the hydrological responses act to reduce the upper ocean freshwater content and increase density, it only plays a small part. The heat flux is what drives the AMOC changes in this case. Okay, that's all I have. This is the summary. I'll just leave it here in case you want to look at it.
Do we have one quick question. I guess, oh yeah.
I have a quick question. It seemed like in both SAI experiments, it basically like, it seems like the effect was just a lot smaller in that region than like the rest of the globe. So like it seemed like, is there a reason why SAI impacts that region so differently than the rest of the globe? It seemed like a very bullseye place where SAI was doing something different.
Yeah, so from actually John and Yaga's paper, they actually look a little deeper into this region. It seems like it's the differences in the rapid response of the clouds to the CO2 and to the aerosol forcing. So essentially, it's because of the model of physics, I would say. Yeah,
Okay.
yeah, and that also explains why these two models kind of have opposite responses because they.
Yeah.
Our next speaker is Ivy Glade, sticking with the theme of geoengineering, the impact of stratospheric aerosols on warming zones.
Okay, hi, I'm Ivy. I'm a graduate student in the Department of Atmospheric Science at Colorado State in Fort Collins, and today I'm going to be talking about the potential impact of stratospheric aerosol injection on the characteristics of warm spells under one scenario of SAI. And so to start off, what are warm spells and why should we care about them? Warm spells are periods of anomalously high temperature that can occur at any time of the year, and we should try to understand these events in a context of both like a current and future climate, because they can have impacts on things such as human mortality and morbidity, ecosystem vulnerability, and crop and livestock yields. So warm spell events are actually projected to increase in frequency as the climate continues to warm, and this is shown in this figure I have on the right, which shows the CMIP5 change in warm spell days at the end of the century relative to the beginning of the century. And we can see that warm spells are increasing everywhere across the globe, and that the increases are largest in the tropics, where sometimes the increases could even be in excess of 200 days. So these sort of events are increasing a lot as the climate continues to warm. And so to more specifically define warm spells in the context of my work, I used daily maximum and minimum 2-meter temperature to define these events. And I used daily minimum temperature in addition to daily maximum temperature because it's an important, it can provide like some insight into potential human health outcomes. And I used these temperature metrics to find when these warm spell events occurred, which I considered to be any period that was at least 6 days in length, where the 90th percentile threshold of daily maximum or minimum temperature was exceeded, and I calculated the 90th percentile of daily maximum and minimum temperature using the 2020 to 2039 time period. And in addition to looking at just the occurrence of warm spells, I also looked at several different characteristics, which included warm spell days, warm spell duration, and warm spell amplitude. And so because climate risks are increasing as the climate continues to warm, and one of those risks are that warm spells are projected to increase in frequency, it's important that we potentially understand how these might be impacted by potential climate intervention methods. And so, as sort of presented previously, I'm going to be looking at how warm spells might be impacted by the deployment of stratospheric aerosol injection, or SAI. And SAI would cool the planet by injecting particles into the stratosphere that would reflect a small amount of incoming solar radiation away from the Earth. I also just wanted to note that methods of climate intervention such as SAI are just seen as a method to potentially avoid the worst negative consequences of climate change, and also to provide more time for the development and deployment of climate mitigation strategies. And so there have been several sets of Earth system model simulations that have
looked at the potential impacts of SAI on things like global mean temperature and precipitation, Arctic sea ice loss, as well as ecological responses. Additionally, some research has examined how SAI might impact things such as extreme weather phenomena, but none of this research has specifically looked at how SAI might impact warm spell events and their characteristics at a global scale. And so I did that using the ARISE SAI 1.5 simulations, and these were run using CSM2 with WACM 6 as the atmospheric component. And these simulations feature two 10-member ensembles, one which follows the moderate and policy-relevant SSP 24.5 emissions scenario that runs from 2015 to 2069, and the other one which also follows SSP 24.5, but that has SAI deployment beginning in 2035. And so the deployment goals of ARISE SAI are to maintain global mean temperature at around 1.5 degrees Celsius above pre-industrial, which corresponds to the 2020 to 2039 mean in the model. And that's shown in this figure clearly, which is a time series of global mean temperature, where the red line shows future projections of temperature under SSP 24.5. And then the blue line shows the time series of temperature in the simulations where SAI is deployed. And so yeah, I just also wanted to note that I used the 2020 to 2039 period as like my reference period for calculating these events in order to be in line with the deployment goals of these simulations. And so to hop straight into the results, these two figures are showing the annual mean warm spell occurrence for 2020 to 2039. And the top figure is showing this for warm spells defined by the daily maximum temperature, and the bottom figure is showing this for warm spells defined by the daily minimum temperature. And so I guess what I just wanted to note with these figures is that during this time period, warm spells are relatively rare events, but they do occur most frequently over regions such as Saharan Africa, the Indian subcontinent, and Western North America. And then we can see that under SSP 24.5, warm spells are projected to increase in frequency, where this center column of figures is showing the change in warm spell event occurrence for 2059 to 2068 relative to the base period. I also just wanted to note here that the frequency of warm spell events increases more for warm spells defined by the daily minimum temperature than for warm spells defined by the daily maximum temperature. And then in the simulations where SAI is deployed, most future increases in warm spell events are avoided. And I also just wanted to note here that the stippling on my figures indicates regions where the 2059 to 2068 period is not statistically significantly different from the base period, and I calculated this significance using the two sample students t-test. And so I also looked at how warm spell days are projected to change with climate change, and so you can, where I defined warm spell days as the count of days in a year that occurred during a warm spell event. And so we can see that warm spell days increase in frequency in a way similar to that of warm spell event occurrences, where the magnitude of change over the time period is relatively large. And the future changes are also widely statistically significant. And then again, when SAI is deployed, we see that most of these increases are avoided. And so I also looked at warm spell duration, which is the longest warm spell event in days that occurred in a given year. And so again, we see that under climate change, the length of these events are increasing, but I wanted to note that the relative change compared to a warm spell event occurrence in warm spell days is relatively small, where the increase is only about 2 times the highest magnitude of the base period for warm spell duration, but for warm spell occurrence and warm spell days, it was as high as an order of magnitude. And we can also see that some of the changes are not as widely statistically significant. Again, though, when SAI is deployed, most of the future increases in warm spell duration are avoided, although there are still some subtle regional changes present. And so the final warm spell characteristic that I looked at was warm spell amplitude, which I defined as the largest deviation of daily maximum or minimum temperature from the 2020 to 2039 mean of each parameter. And something to notice in the baseline is that warm spell amplitude, like climatologically, is largest at the higher latitudes. And this is sort of in contrast to with the other warm spell characteristics that I've looked at so far. And then with climate change, again, we see that warm spell amplitude is projected to increase in magnitude, but similar to with warm spell duration, the relative magnitude of increase is less than with warm spell occurrences or warm spell days. And then when SAI is deployed, similar to with warm spell duration, most of the increases are avoided, although there are still some regional changes. And so I also looked at future projections of warm spell occurrence using a different model, but that ran simulations with the same SAI deployment and climate change scenario, and that is the UK System model. So this figure shows, these figures show future changes in warm spell occurrence for warm spells defined by the daily maximum temperature in UK ESM on the top row, and then CSM2 on the bottom row. And if you look at the middle column, which is the changes at the end of the simulation period relative to the reference, we can see that there are some distinct differences in the future changes in warm spell event occurrence, where, like, firstly, what you can notice is that the magnitude of increase in event frequency is greater in UK ESM1, and this is just likely due to the fact that UK ESM1 has a higher climate sensitivity than CSM2. And then the other thing I want to point out, which is probably more interesting, is that in some regions, such as like this sort of like sub-Saharan Africa region, as well as Southeast Asia, you see that in UK ESM1, those areas have some of the highest magnitudes of projected increases in event frequency, but in CSM2, the magnitude of change is actually relatively small. And there are also some differences in how SAI deployment might impact future projections of warm spells in these two models, where you can see distinctly that in the UK ESM model simulations, SAI deployment seems to like slightly overcompensate for future increases in warm spell occurrence under SSP 2.4.5. And so to conclude, future changes in warm spells defined by daily minimum temperature show greater changes than warm spells defined by daily maximum temperature. Increases in the frequency of warm spell events projected under SSP 2.4.5 are mostly avoided when SAI is deployed in these simulations. And there are distinct differences in warm spell projections under two identical climate change and SAI scenarios using CSM2 and UK ESM1. And then future work might investigate physical drivers behind the differences in the spatial pattern of warm spell events in these two models.
Any questions? Yeah, Kate.
Yeah, great talk. For the CSM versus UK ESM differences, I'm trying to remember, was the controller for the arise in the UK ESM, was that responding to changes in that model, or was it the same amount of sulfate?
Oh, yes.
As in CSM, because that could account for some of the.
Yeah, it was responding to, like, in UK ESM specifically. So it was different amounts of sulfate in both models.
Okay.
Yeah.
Yeah.
So yeah, that could potentially be a part of it.
When you were looking at the SAI scenario in the first metrics for CSM2, it looked like the Amazon was a region where it wasn't statistically significant, but there was still a lot of red under SAI. And I'm wondering, is there a reason for that? Is there like land use changes? Is there like some kind of non-reversibility in that region?
Yeah, so I think that's a great point, and we've noticed that as well. I haven't looked into it yet, but I'm hoping to look into it, and I think that like you're kind of on the right track of like it could be related to like potentially like land use or like land cover changes. I just haven't looked into it to confirm whether or not that's true.
Yeah, Felix, one quick. I'll move the slides over.
Thank you. Could you comment on? I'm putting it out there, and you can correct me. Is basically your work a sanity check that preserving global mean preserves the extremes?
I think, like, at face value, yes, but I think there are some, like, other insights to be gained from, like, some of these simulations. Also, like, the UK ESM simulations of global mean temperature. So in UK ESM, basically the global mean temperature has risen above 1.5 degrees Celsius above pre-industrial before SAI deployment begins, and so there's actually like a decrease in temperature when the deployment begins, and so I think that could also have an impact. And so like looking at how like just like the overall temperature trend and over time matters too, if that makes sense.
Yeah, thank you. So last but not least, before the discussion, we have Daniel Lehuho on ecological risk and climate change.
Yeah, thank you. So I'm Daniel Huhel. I'm a PhD candidate at Colorado State University, where I work with Elizabeth Barnes and Jim Hurl. And this is work that I've been doing in collaboration with a postdoc in our group as well, Ariel Morrison, about ecological risk in climate change and climate intervention scenarios. Ecological risk in the future can come from a ton of different sources. And so to start, I just want to walk through the example that we're going to have today, which is about thermal niches. So in general, species want to stay in the thermal niche or the temperatures in which they're acclimated. So you can imagine if you're a hummingbird and you spend the winters in Central America and it starts getting warmer, then you can move north to the Gulf Coast. And if it keeps getting warmer, you can even move further north to the mid-Atlantic. So this is how climate change can redistribute ecosystems if those ecosystems or species are able to move quickly enough to keep up with those changes in temperature. But this time, let's imagine that you live in the tundra near the poles or in the boreal forest near the poles, and it starts getting warmer, and you can't move that much farther north without hitting the edge of the continent, and you can't become aquatic. So where you have a transport barrier, this is where climate change actually endangers ecosystems, or also this occurs if the rates of change are so fast that the species can't keep up with that change in temperature. And a similar process occurs around topography. You can move up the gradient to escape climate change, but only as far as the top of the mountain, and then you can't move off the top of the mountain. So this movement of thermal niches poses risks for a wide range of terrestrial and marine species, and one way to express these rates of change is called the climate velocity of 2-meter temperature, which is just the rate of change in time divided by the local spatial gradient. We didn't come up with this. This is from the ecology community. And just by unit analysis, that gives you space per time, like kilometers per year. So a vector velocity, which we analyze the magnitude and call it the climate speed in this case. So pulling from the ecology literature, speeds greater than 1 to 2 kilometers per year on land or 7 kilometers per year in the ocean are a problem for species. Greater than 10 kilometers per year are a big problem, no matter whether you're on the land or in the ocean. And this is a metric that's most suited for linear change on a timescale of greater than or equal to 10 years. And climate speeds already affect ecosystems globally. Those examples from the beginning were based on true stories, and they're expected to redistribute and endanger species under all future shared socioeconomic pathways. So risks such as these motivate research into climate intervention, as Hui and Ivy have already talked about. And stratospheric aerosol injection is not a substitute for decarbonization, but in this work I want to talk a little bit more about how it could complement its goals. So the framing, two framings of SAI that are frequently thought about would be SAI to maintain temperature at some value, like 1.5 Celsius, for example, in the Arise 1.5 scenario, or potentially SAI to actually reduce temperatures because the response to stratospheric aerosols is quite fast. In a recent UN Environmental Program report, these kinds of scenarios were highlighted as a potential way to alleviate some climate damage within a few years. But from a rate of change framework, SAI is adding an additional potential dimension of rapid temperature change at the deployment or termination of an intervention. Previous work has emphasized the termination piece. If you shut off climate intervention while you're masking a higher radiative equilibrium, you snap back to that higher radiative equilibrium within a few years, and this is called a termination shock. Here we're asking the question, what specific strategic design choices lead to harmful climate speeds following deployment from cooling? To investigate these questions, we're using two scenarios from the Arise SAI project. The first one is Arise 1.5, which Hui and Ivy have already talked about. In this scenario, You deploy SAI in 2035 to maintain global mean temperature at about 1.5 degrees Celsius above pre-industrial. In a rise delayed start, you have a very similar temperature target, but you begin 10 years later in 2045. Because of the warming that's occurred in the meantime, and because of a slightly lower temperature target, you have to rapidly reduce temperature to return it to that target of 1.37 above pre-industrial. And we also use as a baseline the CESM2 last millennium simulation, which is a 1,000-year simulation from the year 850 to 1849, as a baseline of what kind of climate speeds would be experienced under climate variability and natural forcings and anthropogenic land use changes before greenhouse gas emissions become large. All of these simulations, and then of course the no SAI control, SSP2 4.5, as a moderate mitigation policy relevant future scenario of climate change. All of these simulations are in CESM with WACM, with the caveat that the last millennium simulation is in a middle atmosphere configuration of the model, but that doesn't matter because we're not looking at chemistry here. But the key point in these scenarios is that a rise 1.5 maintains temperature, and a rise delayed start is very similar in design, but it begins 10 years later. So to begin, these are the climate speeds over 10, 20-year periods of the last millennium simulation, and this kind of matches your expectations. Natural forcings evolve quite slowly, so you do have climate speeds. Climate variability exerts very significant influence on ecosystems naturally, but they're very small overall. And in a rise 1.5, where you're maintaining temperature, your climate speeds over land are quite similar in magnitude to what you saw during the last millennium simulations. And this is the 20-year period immediately following deployment of the SAI intervention. Over the ocean, your climate speeds are negative overall because that 2035 deployment year is slightly above the 1.5 Celsius temperature target, so you do have a small negative temperature trend during that 20-year period following deployment. In SSP2 4.5, climate speeds are large and positive everywhere except over the North Atlantic warming hole. And this pattern matches our expectation of ecosystem risk from the ecology literature. You have your largest climate speeds over the tropics, particularly the tropical ocean, where your spatial gradient in temperature is quite small. So even a small perturbation to temperature means you have to move a very large distance to keep up with it. And the climate speeds are also high in the Arctic, because here your warming rate is highest. So those are the two parts of that climate speed calculation and how that gives you a large climate speed everywhere. Then in a rise delayed start, your magnitudes are as large or larger than SSP2 4.5 with no SAI, and the potentially dangerous climate speeds occur over greater than 2/3 of the land area because of this rapid temperature reduction that's forced during the 20-year period immediately following deployment of the intervention. Climate variability still plays an important role in the presence of the forced response. So here, each one of the dots represents an ensemble member or a 20-year period under these simulations. The dots that are filled are past those thresholds that are of concern from the ecology literature, and the bars denote the ensemble mean. And the take-home point is that a rise 1.5 is actually statistically indistinguishable from the last millennium on this planetary scale, but there's no overlap between a rise delayed start and 1.5 or the last millennium. That's how large the difference is here. The minimum member of delayed start over land is greater than the maximum member of a rise 1.5 over land, and similarly over the ocean. And again, the biggest difference between these two scenarios is the 10-year delay in deployment. So these climate speeds provide one way to think about relative ecological risk between a range of future scenarios. So here we have a phase space where on the x-axis you have the rate of temperature change per year. On the y-axis you have the area exposed to a climate speed greater than 10 kilometers per year. So again, this is a kind of threshold of extreme ecological risk from these climate speeds. And the area exposed in the last millennium is, your warming rate is quite small, and there's never a very large area exposed to these climate speeds under the last millennium. That horizontal bar is the maximum in the variability of 20-year periods, excluding large volcanic eruptions. Climate change and recent historical observations or reanalysis cluster on the right side of this figure above that last millennium variability. This scales more or less as you would expect. The more mitigation you do, the less areas exposed to these climate speeds. So a lot of mitigation, you're bringing that down. Moderate mitigation, you're a little higher up. and then no mitigation at all, you're way up here on the top right. And then this is where we've been in the recent 20-year period in ERA 5. Rapid temperature reduction, SAI scenarios, cluster above that last millennium variability on the left side. And what's useful here is that because of how these ARISE scenarios are designed, we can connect these rapid temperature reductions to specific design choices. So for the CESM simulations, here's your no SAI control, SSP2 4.5. This is that ARISE delayed start scenario, so that's a 10-year delay, and then you have to reduce temperature, and that rapid temperature reduction gets you to the purple dot. In ARISE 1.0, you're starting in 2035, but you have a lower temperature target, so you have to rapidly reduce temperature to reach that temperature target. This kind of follows up on one of Ivy's points in the UKSM simulations. Because climate sensitivity is so high in UKSM, you've actually overshot 1.5 Celsius significantly by that 2035 deployment time, so you have to bring down temperatures again to reach that temperature target. And in each one of these simulations, the area exposed to these extreme climate speeds is greater in the SAI scenario than in the no SAI control scenario. And then the final class of simulations here are those scenarios with SAI where you maintain temperatures, sometimes called peak shaving. And here we have the ARISE 1.5 and the GLENS scenarios. Both of these are temperature maintenance scenarios. These are the only products we have here where you're within that last millennium variability. But again, the primary difference between that ARISE 1.5 and the ARISE delayed start is that 10-year delay in deployment. So a relatively small change to your scenario design has created a very large change in your ecological risk. And that's not necessarily intuitive when we think about designing these scenarios. At a very high level, this is all just coming from the temperature trends. So if this is a problem, because that's no SAI climate change, then on this one specific metric, ARISE 1.5 might not look so bad, but this could also be a problem because it's very rapid temperature change just in the other direction. And you could imagine scenarios to avoid this so-called deployment shock. You could do delayed start, but with a higher temperature target to maintain temperature, or you could do a delayed start with a lower target, but have a slow deployment of SAI in order to make sure that your climate speeds are never too quick. So in summary, these ARISE simulations allow for outcomes in different scenarios to be connected to specific strategic design decisions, which is really, really useful. Climate speeds when global mean temperature is maintained with SAI in ARISE 1.5 are similar to those experienced over the last millennium. A similar SAI strategy, but with deployment delayed by 10 years, yields large planetary scale climate speeds, which are far beyond last millennium variability and greater than climate change without SAI at all. And avoiding these potentially dangerous climate speeds may help us constrain future scenario design. So thank you for listening. I'm happy to take any questions, and feel free to take a look at our preprint, which will hopefully be published soon. Thank you.
Any questions? Yeah, Sam?
That was really interesting, thanks. I'm trying to wrap my head around this idea of, like the birds example, not being able to adapt fast enough in these kind of decadal rates of change when you have seasonal migrations that cross like continents. So I'm curious, like, are the implications for these climate velocities specifically for species that don't migrate, or is it also applied to these migratory birds?
Yeah, so it does apply in general. Seasonal migration is just a very, very different process than adjusting the range that you breed in or the range that you're used to wintering in. Those are just really different biologically. And so being able to migrate large distances seasonally doesn't necessarily mean that you're able to move your breeding or wintering range far distances to keep up with a climate change. And there's a lot of precedent for this in the historical climate variability literature and the climate change literature. Lots of examples of this.
Yep, Felix?
Could you maybe comment on different, what do you call it, tolerated speeds, differing between vegetation and animals?
Mm-hmm. Yeah, so this is a really complex point, how kind of different species and different families and different classes of species have really differing abilities to keep up with climate change. Obviously, something that's sessile, like a tree, you can't move at all. Like the range can move over time based on like seed dispersion and that kind of thing, but an individual tree, literally, I mean, it's not gonna just walk to up the mountain, like, no. So yeah, that varies a lot by species. It's kind of, getting granular with analysis like that is really difficult to do from a climate perspective, because as soon as you start thinking about individual species, there's questions about, can it adapt through evolution? Is it, just tough and doesn't really care about climate? Is it out of phase with the climate, but it's not gonna notice that until it gets burned down? Like, it gets really complicated. So that's why we kind of don't get into the species level questions. Climate speeds excel as a high level metric to talk about basically how big of a hammer are you hitting the ecosystem with. But for kind of a granular species level analysis, you're going to need to do a lot more work to talk about that. Thank you.
Yeah, have you thought about, so like if you were doing something like we didn't start deploying SAI until like the 2060s, and so like temperature has warmed so much more, like what would happen if like the ecosystem that animals are accustomed to living in like has already been destroyed by climate warming? Have you thought about that at all? Or like if there's a way to quantify if there's like a if there's like for different regions, if there's like a maximum amount of warming that we can have before like the damage is kind of done?
So we think those ecosystems are really where this sort of deployment shock would be most harmful. So for example, the Mediterranean ocean ecosystems have swapped from being a kind of mid-latitude environment to a much more tropical environment over the last 30 years. And then if you suddenly snap temperatures back colder, what happens to those species? I mean, yeah, that they're not going to love that. Or another example would be like ecosystems in the Rockies that have transitioned from being forest dominated to grassland dominated. If you snap temperatures back, what does the grassland do? So I think those ecosystems are the ones that would be most at risk in this kind of scenario. Those that have survived climate warming by being tough or living in a microclimate would probably love it if temperatures suddenly snapped back. So that kind of analysis would also get really complicated really quickly. But there's clearly large forces pointing in both directions, so I kind of suspect it comes out on net to be similarly risky to large climate speeds from conventional climate change. And just one final point on that is that in the paleoclimate literature, the closest analog you have to something like this would be the onset of the Younger Dryas, we think, where you had very rapid decadal scale cooling, and where you have paleoclimate data, it looks like the regional climate anomalies during the decades following the Younger Dryas are relatively similar to what you see in a delayed start, and that is accompanied by a planetary scale redistribution of ecosystems. So we think that this would be noticed if it happened.
One last question, then.
Yeah, I was wondering if you could do something similar but with a different variable, for example, precip or some, I don't know, other things that species care about, and if you've thought about doing that.
Yeah, so thanks for that question. I actually, that now completes that every time I've given this presentation, I've gotten that question, so thank you for that. But yes, you can define a climate velocity of literally any variable that you want. One that you see commonly is called the bioclimatic velocity, which is the climate velocity of the species potential distribution you get out of an ecological niche model. But one that people ask about frequently is the climate velocity of precipitation. And the answer that comes out to a lot is that, yeah, you can define that. It's just that climate velocity works best when you're confident in the sign of your response and you're confident that the spatial gradient of the variable is represented well in the data that you're using. Other authors have published and looked into climate velocities of precipitation, and that's great. We didn't have that confidence in the precipitation data that we had here, so we stuck to temperature. But you can totally define that if you want to. Yeah.
All right, great, thank you. So now we have our discussion. And I'm gonna try and bring up the slides from this morning in case there's anything you want. So we have about half an hour. We don't have to take that whole time, but it would be good to have some discussion on either the plans for the coming next 8 months or so, or I guess a bit less than that now, of the rest of our allocation, which is kind of the gray points there. And then also any things you'd really like to see the working group do in the next allocation. So these are typically, big projects that are useful for everyone. So things like ARISE that was just talked about, that wasn't a climate variability and change working group project, but it's those kind of things, big data sets that everyone can use for a variety of problems. Or if there are very specific things that you feel like need to be understood in the model, that some targeted experiments would be useful for, that also is a good idea. So I don't know if anyone, just any thoughts anyone has on any of these things. Danielle.
I was wondering, it's not a big idea, it's just a question for you guys, why you decided not to do a land use only simulation. I know that there was some issues with the CSM1 land use one, but
Yeah, that was legally wrong. So it was a conscious decision just based on the amount of computing time. So we wanted to have all the forcings represented so that linearity could be assessed. But if you start breaking it up into land use, volcanoes, solar, and ozone, we would have had very small ensemble sizes with the amount of computing time that we had. So we decided to go for what we did, which was 4 ensembles, one where everything else other than the aerosols and greenhouse gases were together. And the motivation was kind of maybe the spatial locations of the influence of those forcings and the time at which they're relevant was different enough that people could still try and parse out their influence. But if you think that is not true and that having an ensemble of land use only simulations would be good, that's definitely glad to hear that. It's probably not something we could necessarily do in this allocation, but we could propose it for the next time around if we felt that was needed. Do you feel like that's needed?
I haven't done what you said we should do first, so I don't know. Maybe do that first and then decide,
Yeah, I mean, one case that I mentioned where I feel like we don't have enough information is in this global warming in the green line, which is the everything else run, and where is that coming from? And the guess is that it's volcanoes just because of the time series, but that may not be true. It could be land use changes, and so there are things maybe that we do want to end up pulling apart in this everything else run. And so if you find motivation to do other runs, that it would definitely be good to hear about that. Yeah, do you want to?
I don't know if it would apply to this allocation, but it seems like it took a little while to figure out how important the change in forcing between CMIP 5 and CMIP 6 was, and it turned out to be really important.
Yeah.
Are there plans kind of with when the CMIP 7 forcing or when CSM 3 is finalized to kind of immediately run one of those, like that style of experiment to pull apart how important the forcing is in the model architecture?
Yeah, I would hope that would be the case. I feel like we learned a lot from what happened last time. I guess I can't speak for exactly what CSM3 would do, but I think, right now all we have is CMIP 6 forcings, and then at some point we'll change to CMIP 7. And that's kind of what happened last time, is the model was running fine with CMIP 5 forcings, then we got CMIP 6, and it didn't warm anymore over the 20th century. So those weren't like, really clean runs, they were development runs, but you could kind of already see the impacts there. I know that DAMIP is going to propose a CMIP6 simulation, so running the historical with CMIP6 forcings as part of CMIP7. So hopefully multiple models would end up doing that experiment, and hopefully we would be one of them. Yeah, so, yeah, I don't think, I had not appreciated how important the historical forcing uncertainty could be until last time around. So I think we need to do that. Yeah, Osama?
Wonder what the possibility is of running more ensembles with the globally high resolution. I know Pedro has some results, like 3 ensemble members. Is it possible to add more members to that?
Yeah, I think they are running more right now on the Texas machine. There's gonna be 10, yeah. I don't know when the
Those are
date.
gonna be public this year,
Oh,
the 10 members, probably soon.
Yeah.
So, but I don't wanna take too much air from this discussion with my obsessions. But I was thinking how to frame this question is, I don't think the working group allocations are large enough to run usefully large ensembles with a high resolution model, but perhaps we can have a conversation of what could be useful and apply for computer time on Frontera, or find a way to do it here on the ridge on some bigger allocation. If we think there's something that is complementary to what is being done.
Yeah.
So I was wondering, pacemaker runs, single forcing runs. The advantage of the high-res model is that the ensembles don't need to be so large because the force signals regionally tend to be larger. So you don't need 40 members. Perhaps 10 members is, for some of the stuff we're looking at, 10 members can isolate force regional changes.
Yeah. Do you have a rough idea of how much 10 members is in millions of core hours?
It can be done on those Frontera on those allocations on Frontera. These are community allocations, so they have to be submitted by a group of people from multiple institutions. I mean, so there's 2 sizes. I got one of the smaller ones to do paleo with a group of paleo people.
Yeah.
And it was not that difficult to do it. I mean, it requires some coordination. But so my question perhaps is, of all these experiments that we do with CSM, with the standard res model, which one is the most important? Other than the full forcing runs, right? Those are going to be available, the full.
Yeah. I mean, I feel like what would be nice is to pull apart the role of the atmosphere versus the ocean in what is seen in the high
That's exciting, yeah. And there's a 3-member ensemble for that from, what's the name of that other project? Catalyst.
Catalyst, yeah.
Perhaps enlarging Catalyst is a good idea.
Yeah, but also maybe doing the opposite to test for linearity, whether are there non-linearities when you have both.
High res ocean, low res atmosphere. Yeah.
And then I feel like a big question is what would CSM2, but maybe we should be going on to CSM3, what would that look like at high resolution? Because Steve, you had results showing that there are improvements in predictability in the tropical Pacific at low res with CSM2. And then there are other, Sarah Kang's paper showing that the cloud feedbacks give you a better connection into the tropical Pacific in CSM2. And so the combined influence of resolution and physics, does everything get better in CSM2 at high resolution? I don't know if we can afford to do that.
It's going to be so expensive, Steve. What do you think?
We don't have the models to do
Well,
that.
right, but there is a plan, I think, to make a CSM3 quarter degree, 10th degree model. So
I mean, I think if you're thinking ahead to the next proposal, it makes sense to think about CSM3 high-res experiments.
yeah.
And you know, maybe like Pedro is suggesting, if we can't do it on derecho, you know, maybe working groups need to collectively submit a proposal to TAC. I mean, if that's the only place that we can run them.
So that's something we're allowed to do.
Yeah, I mean, NCAR people, university people, we can do it.
Right.
Yeah. I think you can. Go. You guys are on Ping's proposal, right? In the computer time proposal.
You know, if we're on it. I mean,
If you have access to the users on TAC.
yeah, but through Ping. I mean,
Yeah. I'm happy to I'm kind of obsessed with it.
The Catalyst does that too, right?
I mean, I think we've seen enough compelling evidence.
I think there's plenty.
The process representation is greatly improved.
Yeah.
And now it's just depending on when CSM3 high-res model will be available.
Yeah.
It will be the end of 2025 or even further.
Yeah, I don't know. I mean, Julio was talking about trying to start some runs the other day, because there's things to look at in terms of like gravity wave drag that it could help with solving biases that we currently have in the low-res CSM3 development version. So I guess it depends how difficult, how many challenges come up.
I think there's a catch on all this conversation that no one has looked at ENSO in the high-res model. And I think it's pretty crappy. It's not that great. My superficial exploration. So, and again,
sounds like something you should be looking at
high-res
in
ENSO.
conjunction with your Indian Ocean.
I know, yeah, but the day only has 24 hours.
Looking for you to tell us what it looks like.
No, I mean, perhaps it's something.
We're talking about high-res ENSO, right? Then the ENSO variability seems like very close to observation in the high-res.
The amplitude, the patterns are wacky. Yeah, I think, again, I don't want to get ahead, but perhaps we need to do that homework. Don't look at me so hard. But yeah, perhaps a mix of resolution. I think perhaps think about single forcing, at least aerosols. Yeah.
Yeah. But I guess our question in that case, would we build on IHESP?
I would do it on, yeah. We don't even know the cost of CSM3 on.
Yeah, it's expensive.
This is gonna take years to know.
Yeah, it has 3 times the number of levels, so. But it has a QBO, so. Maybe we get a QBO MGO connection at high res.
Yeah, but there's so much to learn from this. I mean, there's already a 10-member ensemble, right?
Yeah.
So I think to leverage that ensemble with anything else we could do, could produce so much science.
Yeah, maybe we can propose some single forcing simulation using the high-res.
And perhaps they don't have to be 10 members. Perhaps with 5 members, so 5 and 5.
Yeah.
It's still a ton of. It's depressing when you see the numbers. It's totally depressing.
Yeah, I haven't fully grasped like what even order of magnitude are we talking about? Like.
So I'm running a mixed resolution run with a 4th catalyst member, and it's 10 million core hours on derecho. Just one run.
We have these other large, what's it, NSC. I think they have to be over 10 million. But I don't know, maybe you could get 3 members or something on those. I'm not sure, do you know how big those are?
How big
Is it NSC, or is that what they're
it has to
called?
be over 10 million.
Yeah.
Okay.
Yeah, what's the, how?
I don't know what that upper.
Okay.
Perhaps.
Yeah.
One on one computer. Again, it's a lot of computer time.
Yeah.
This is a group that should do that.
Yeah.
Who else is going to do it?
Do you have space for the data that comes out of it?
Yeah, that's a pain.
About analyzing
It is a
the data.
pain because these things have hurricanes. So then you need the hourly data or the 6-hourly data. But I think the common theme is that we're seeing that both increased atmospheric resolution and also oceanic resolution matter. Depending where you are, one is more, and we still don't know exactly which one is more important where, but a lot of physical processes are better represented.
I mean, another thing we could do if we don't have enough computing time is try and leverage the regional refinement more. If we knew which area we thought was the most interesting.
Is that difficult to set up?
Yeah, I think setting up the grid takes some time, but it's not impossible, and there are some that already exist. There's this, yeah, but I guess there's less being done with coupled, regionally refined simulations.
But you don't have a high-res ocean in those, and it sounds like the ocean is important. Yeah.
Yes.
But we could take like, I don't know, SSTs from IMF.
Yeah. I mean, that's essentially where we got stopped. Is we're thinking that perhaps the way to do those experiments that we were on the past allocation is to take the SSTs from IHESP.
Yeah.
And then see if increasing the atmosphere even further gives you bigger atmospheric responses.
Yeah.
That's where we're stuck.
Any other thoughts? Doesn't have to be about high resolution.
Yeah, I think like single photon rounds, well, for IHAS, for high resolution would be very valuable, but even for low res or standard resolution, like existing CS1 or 2 single photon rounds, it would be very valuable to have the a corresponding arithmetic type of rounds, not only for studying like climate sensitivity or the feedback or the forcing, but also like motivated by students' work, like having those prescribed ST rounds allow you to study broad atmosphere response to direct radial forcing versus SST forcing.
Yeah, so which, if you had to choose your top forcings to have those fun runs for, what would you choose?
Yeah, like we have CSM2 single forcing rounds, will be great to have the associated or corresponding arithmetic rounds for each single
For each of
forcing.
them, okay. Yeah. But if we only had allocation for, say, 2 forcings, would you choose greenhouse gases and aerosols, or if you were to prioritize?
Yeah, we have both forcing right now, right?
Yeah.
Aerosol forcing and, yeah, greenhouse gas forcing.
Yeah, because I think we could manage to do some of those in this allocation, even though we haven't really proposed it, but it's related, to what we've done already, so it's kind of okay to change in that way, but whether we could do all of them, I mean, we would just start with the high priority ones, I guess, so it would be aerosols is probably the highest priority.
Yeah.
Followed by greenhouse gases, followed by the others. Yeah. Well, I guess biomass burning aerosols would maybe be above greenhouse gases, or?
Yeah, the single forcing rounds has the most biomass.
Yes.
Yeah, I have to think more about like
Yeah.
total aerosol or like individual aerosol.
Yeah, we can talk offline about it, but I feel like it would make sense to kind of pair them with the forcings we've done, so I would separate out those two just because that's the way it's being done in the single forcing large ensemble.
Yeah, eventually it would be great to have the paired rounds with the full couple rounds.
Yeah.
Steve?
Have you thought about like global GOGA AMIPs forced with IHESP SST? Like you're doing the regional refine, but what if you did global high-res atmosphere only?
So this would be global quarter-degree atmosphere forced with IHESP SSTs.
Yeah.
Even the GOGA runs with observed SSTs is not, it's only 5 members, so even making that larger could be useful. Right, there's only a 5-member, CAM5, high-res, AMIP run.
Yeah.
Ensemble.
And I guess they would have not that high-res SSTs in them.
And not, yeah, perhaps after seeing today's results, it sounds like perhaps one run with observed the optimally interpolated SSTs.
Yeah. So what would be the primary thing that would tell us that beyond what we just know from the coupled runs? Would just be boosting the ensemble size or?
What would be historical? Right?
Yeah. But, so we're talking about taking coupled model SSTs.
No, I'm talking about taking high-res FOSSI SSTs.
Oh, okay, yeah, okay.
So it would be like, a historical AMIT, but it would
okay.
have, some of the high-res coupling, at least one-way coupling.
Yeah, that's a good idea. So that would complement the existing AMIP simulations because it would have higher resolution SSTs.
So for high-res FOSSI, what kind of atmospheric resolution you use for the atmospheric forcing?
What did say again?
For the high-res FOSSI run.
Yeah.
The atmospheric forcing resolution is a quarter degree.
50 kilometers, generally 55.
And ocean is 1/10.
Ocean is 1/10. But it's a pretty good global reconstruction of observed SST coming out of that.
Yeah.
With a lot of fine scale feature.
Yeah, and then you could do smoothing experiments built off of those. Yeah, they don't have to be too long then either. If you don't need to spin them up from 1850, you could just run 1980 to 2020. Yeah, that would be good. Yeah, someone?
So we have a tropical band regionally refined. I wonder what people think of having the rest more like latitude band refinements, like mid-latitudes and then a polar cap or something like that. That might be more, that might be of broad interest to a wider group of people than having a specific lat-long area regionally refined.
Yeah. Yeah, so there is work going on with this polar grid, which is regionally refined on both poles. Adam Harrington is running simulations right now, and there are already interesting results that have helped with the development of CAM7, showing all those missing gravity waves in the southern hemisphere high latitudes at low res compared to that regional refinement. I think it's going down to quarter degree at both poles. So I guess the one that would be missing would be a mid-latitude band, which would like complete the set.
I'm just combine them all together.
Yeah.
Any thoughts? You'll have, oh yeah.
I have no idea if this is the right NCAR working group to bring this up in, but the last millennium simulation, so with CESM1, there was a last millennium ensemble, which was done with CAM. And then with this simulation that we used, it was it's the WACA middle atmosphere, but it's just the one ensemble member over the last millennium. Well, just the one ensemble member over the last millennium and a perpetual 850 as well. And I guess just the last millennium ensemble in CESM1 was a pretty cool data set. We're sort of obsessed with the CESM2 last millennium simulation. We have like 50 ideas on what to do with that. So I guess I was just wondering about kind of whether there were plans. I know the simulation was really recent, whether there were plans to do an ensemble with the new last millennium.
Yeah, I don't know. That would be the paleoclimate working group, but I can take a note of that and ask them or tell them that you like the simulations.
Yeah, we've been emailing with, I guess it's Betty Otto Bleisner over there. Yeah.
Okay, yeah, she would be the person that
Cool.
would probably would either know whether they're planning to do that or that you would try and persuade. So there's more chance to have input. So really August is going to be the time where we really start to make these more firm plans, and there'll be the summer meeting where we'll have another discussion. And then there'll probably be some emails sent out to gather input as well. So if you're on the mailing list, you would hear about that sometime in the summer. So if there are any last thoughts? So I guess we're gonna go to Under the Sun for those who are interested. Does anyone not know where Under the Sun is? And does anyone need a ride? Okay, and there were some other things that I was gonna, yeah, well, so thanks all to the AV people for helping us out, and then also Elizabeth and Daniel and Kaylin who helped us on the administrative side. And thank you all for coming and for doing really great talks. We hope you'll continue to kind of engage with the working group for other meetings that come up, and join the mailing list if you're not already on there. So, thanks a lot.
Thank you.